At MIT, we tend to view the world a bit differently than most. Maybe it's our need to see past the obvious, or our dissatisfaction with the status quo. Maybe we're just obsessed with asking the next question and solving the next problem. Whatever the case, we believe that there's nothing in the world that can't be made better, stronger, cleaner, faster, smarter, more life-affirming, life-saving, life-improving. So we discover, teach, ponder, and manage. We build, design, and explore. We invent, innovate, create, and cure. We apply science, and we engineer the future. Because it is exploring and solving that moves us forward. It lifts us. It's what makes the world better. It's what makes us MIT.
When you're a leader, you have to set the tone. When you're a leader, you are a driving force to bring about meaningful change. When you're a leader, you have to anticipate in order to create sustainable mobility for new generations. As a leader, our mission is to design systems, solutions, and services for the mobility of the future in harmony with our planet. As a family-owned company, we pass on our vision from generation to generation. As game changers, our teams constantly reinvent themselves, explore new paths, and embrace change to imagine the new generation of mobility. Serving car makers, serving all mobility providers, serving all users. Because what moves people is what drives us. Plastic Omnium, driving a new generation of mobility.
So, ladies and gentlemen, very warm welcome to you, all of you. My name is Alexandre Corjon from Omnium, and together with Olivier Cadet from MIT, we'll be your host for the day. We are very pleased to welcome you in this auditorium, as well as online, since this event is live streaming. It's the first MIT Omnium Symposium, sorry for that, on innovation for the next generation of mobility. We are very pleased to welcome you in this, let's say, new setup for us. And as Omnium is a worldwide company, we decided to join the MIT Industrial Liaison Program and to leverage the MIT capabilities to develop further our innovation portfolio. Mobility is being reinvented in a very transforming world and faces also a very striving needs for innovation. Decarbonization is one of the new drivers to select the path for this, let's say, this improvement, but also modification in economics, social, energy, and smart city access, where the transformation of the mobility will take place. Today is a day of exchange. You will learn how generative artificial intelligence models are supporting the creation of innovation. You will hear from experts, from startups, with what game-changing technology will emerge, what energy can enable the move to a more sustainable mobility, and what is the progress in terms of new materials supported by nanotechnology and biosourcing.
You know, Alexandre, I remember back in February this year, you came over to visit us at MIT on campus, and we were sitting down, and you came up with this idea of doing a symposium. And here we are, 8 months later, and we're delighted to be here with you and bring a small part of MIT and its innovation ecosystem to Paris. And we love doing these types of regional events because it gives us a chance for us to share and exchange, and we create connections during these events. So in that spirit, we really would like today to be as interactive as possible. And you'll have 2 ways of doing this. First of all, you can interact and connect with a lot of the startups who are here with us today. We have a wonderful startup showcase just outside this room, so please engage with the entrepreneurs and the founders from those startups. Second, when you hear the speakers, you'll have a chance to interact and ask questions using Pigeonhole. So you can either scan this QR code or go online at pigeonhole.at and enter the code 23PO to interact with our speakers and ask great questions. And we expect a lot of questions from you.
So let's jump into this very exciting agenda. And I would like to call on stage Laurent Favre, CEO of Plastic Omnium, and Félicie Burel, our Managing Director, to give some opening word for the day.
So, good morning, everyone. So we have quite a gathering this morning with us. So dear guests, dear PO colleagues, dear MIT friends, dear people online, welcome to this Plastic Omnium MIT Symposium on innovation for the next generation of mobility. So at Plastic Omnium, we are firm believers in the power of innovation to really push the boundaries and drive progress. Today, we are not just attendees. We want you, us, to be architects of this new generation, next generation of mobility. And as you have seen in the video, it is also our purpose. So this symposium really demonstrates our commitment to innovation, to push the frontier of science and really to turn those ideas into real, tangible solutions for a new mobility. And this is especially important in a world where the pace is so fast, the technology, everything is going so fast that we need to adapt, and it's key that we keep up to date. So in an industry where those new ideas can really push us to reinvent the way we connect, the way we move, the way we think cities and the ecosystem and the infrastructure, it's really important that we take part of it. So why are we here today? It's more than just a gathering. It's a conjunction of researchers, industrial players like us, startups, and it's really a unique occasion for us with the MIT at our side, and it's a first for us to really have a different approach and explore differently the options of this new world of mobility. So it's not just another event, it's also for us a call to act, a call to collaborate differently. You said it, we want it to be as interactive as possible, and we wanted to have it not only among us, but generally speaking, with any people, player willing to take part in this new mobility market. So with Laurent, we really believe that together we can drive this new generation of mobility.
Thank you, Felicie, and warm welcome from my side as well. I'm very happy to be here. I had a look on the agenda before, you as well, I assume. I'm not sure I understood all the topics, but I'm sure it will be very exciting. It's the first time for us today. You heard about that before. We wanted to do something different because we do see that everything is accelerating around us. That means the world is changing. We know that in the way we are living in our private life, in the way we are experiencing the changes in our business life as well. It can be scary sometimes, but it is also very inspiring, very motivating if we understand those changes and if we make those changes opportunities. And that is the ambition of Plastic Omnium. You have seen our purpose before. It's about driving. That means about driving the changes as well. And to drive the changes which are happening in the mobility industry, where we are a major player, as you know, it is important to understand what's happening outside and how to embark maybe people coming from different areas, industries, or like the MIT. That's the reason why we are here today. The success of the day will depend on you as well. It's also the way we are interacting together. You are asking questions, you are reacting, and so on. And for sure, it's only the start of a journey. And really, many thanks to the MIT to be here today and to continue the journey with us in the coming days, months, and years, hopefully as well. Coming back to the mobility, we all know that the mobility is really at the heart of the transformation of the world, of the industry. The mobility of tomorrow will be for sure more sustainable. There is no question about that. That is a high expectation, especially from the young generation. The connectivity, the mobility of tomorrow will be also safer because nobody wants to compromise on safety. The mobility of tomorrow will be also more connected because the first question everybody asks today is, where is the Wi-Fi? I have to be connected. It's the same in the mobility of tomorrow. There is no question about that as well. It will be, in terms of design, potentially also more appealing because all the OEMs, the car makers, they want to differentiate, and they have also to differentiate with the design. And the mobility has to be affordable because it's a mass market, and therefore it's also about affordability. And it's kind of paradox to link sustainability, connectivity, new design, new features with affordability, and we are convinced that it's only possible through innovation. We believe, or we are convinced, that only innovation can make this complex equation feasible, meaning mobility of tomorrow will fit to the consumer needs, but will be also in line with what the planet needs as well for the long term. That's the reason why innovation was always important for PO, but will become more and more important in the future. I think we have to be inspired as well about what's happening outside, meaning in our industry, like the newcomers, like Tesla and so on, disrupting the market, having a different approach. And our ambition is not only not to be disrupted, but to potentially disrupt the market we are in, to be the winners of this transformation. That is the reason why we are starting this journey with you, and that is the reason we are very happy to welcome you today.
So indeed, a lot of changes, disruptive changes, and you said it, all of that is triggered by a lot of the combination of different events, the environmental concerns, the change in the way consumers are actually willing to have the mobility, change in technology, and obviously also the regulatory frame that is impacting a lot our industry, and we can't ignore that all those trends are having a different impact at a different pace. So today our agenda is very rich and dense. We'll be listening to pitches from startups. We'll get into the intriguing Industry 4.0 topic. We will also have a panel discussion on going vertical, exploring what you mentioned, Tesla being a good example of it. So a lot of very exciting topics that we will discuss together. But before getting into the session, I will ask John Robert from the MIT Industry Liaison Program to come on stage and say a few words for us.
Thank you very much. It's great to see all of you today. If I can have the first slide. So why would I start off with a picture that I took yesterday from this angle when there are so many lovely places in Paris to take a picture of. So this spot in Paris used to be a lovely place to look at the back of Notre Dame. And someday in the future, it will again be a lovely spot to look at the back of Notre Dame. But let me tell you why I took this picture and why I'm talking about it today. In around 1984, 85, something like that, I was here with my wife, and we were in our early 20s. And we came to Europe for the very first time, and the city that we flew into was Paris. And we had all sorts of plans to travel all around Europe. We had friends in Munich that we were going to visit, friends in Athens that we were going to visit. We were going to meet with her grandfather in Torino, who was doing a sabbatical there. We had it all planned out. There was one problem. We just couldn't leave Paris. We came for planning on 1 week. It turned into 2 weeks, which turned into 3 weeks. And in order to save our European trip, we finally just got on a train and got out of town. And at the end, we were supposed to finish our stay with 1 week in London. And we ended up spending 1 week in Paris once again. So this picture was taken from the place very close to where we were in the Latin Quarter at a very low-end hotel, very, very cheap. And so we ended up spending a lot of our time actually on this bridge looking at this view. So that's why I show it today. So just, I'm going to use that as a background. I'm going to go through a few slides here. So welcome again to the Plastic Omnium Paris Symposium. We're super happy to be here, as everyone has stated. So why MIT? And this is to shape and create our future. That's something that we all have an aspiration to do in some way. So people go to MIT for research, people go to MIT for technology, and people go just to make connections with others who have a common interest that's worth exploring. But ultimately, it's to shape and create our future. This is President Sally Kornbluth, and she has been in the role for less than a year now, and she's articulated 3 themes that are important to what we're talking about today: climate, AI, and biotech, and even biotech. We'll hear probably a little bit about how biotech fits into some of what we're going to be discussing further on. So why ILP and Startup Exchange? Why do people work with us? Well, we are about connections, we're about relationships, and we're about global impacts. And I'm going to explain a little bit about that. Who are we? We are 57 people who are diverse in terms of expertise, in terms of experience, and in terms of cultural background. And this is a picture of us at an offsite this summer. So you might ask the question, why are we so darn happy? Well, it's all about what we do. We amplify MIT's expansive global network and create an inclusive community. And when I say inclusive, what I mean is, in terms of MIT, it's all of the institute. In terms of corporations, it's global corporations across all industry sector. And in terms of startups, it's MIT-connected startups across all of the different technologies. So where do we engage? We do a lot locally. So at MIT, people go to MIT, but it's true that we also go out into the world. So we do things globally, like we're doing today. You might not think of Paris as acting globally. That feels pretty local to you, but to us, it's global. And then, of course, virtually. So how do we engage? We engage through publicity, we engage through events like these, and we engage through custom meetings. We do about 2,000 meetings between people from corporations and people from either academics or in the entrepreneurial world every single year. And these are ones that we curate, we schedule, and we facilitate. Beyond that, of course, there are the introductions that happen by email and introductions at events like these. But there's a context here that's very important for everything we do, and there's been some allusions to it already, which is the innovation ecosystem. So this arrangement of the people that we work with is intentionally to put on display the 5 stakeholder model for the innovation ecosystem. That is, you have to have these 5 stakeholders minimally to have a successful innovation ecosystem. So entrepreneurs or startups, risk capital, corporations, government, and then academics. And in our case, of course, our focus is on MIT. We bring to the table more than 200 corporations that we're working with at any given time on a fairly intense level. Sorry, I should just say that the top 5 countries in terms of corporate members that we have is the United States, Japan, Korea, France, and Brazil. And France dropped way down during the pandemic, but it's coming back. So I'm looking forward to seeing even more companies get involved with us in France. And then at MIT, we clearly have more than 1,000 people, but in terms of faculty, there are about 1,000 faculty. And they come from 60% engineering and science, 40% from humanities, management, architecture, and our brand new Schwartzman College of Computing. And then there are the startups, and we have a steady state of about 1,000 startups that we consider to be both MIT connected and ready for engagement with corporations. And if you look at the years that the startups were founded in our current set of about 1,000, you can see that more than 50% of them were founded between 4 and 8 years ago, which is really what you would expect when we talk about being industry ready, even though there can be different timelines for different startups. So since when have we been doing this? We've been doing this for 75 years, connecting MIT with corporations. And in terms of connecting startups with those same corporations that we have deep relationships with, we've been doing that for about 8 years. Loosely speaking, that's MIT and ILP and Startup Exchange. And my name is John Roberts, and I lead and support that fabulous, happy group of people that you saw on an earlier slide that put all of this together and make it possible. I do want to just say one thing about Kendall Square. If you are in a place that you aspire to have as an ecosystem, probably somewhere outside of Paris, this may be inspirational for you. So right now, Kendall Square is very, very high density, but this is what it looked like in the 1980s. And I was a graduate student at MIT during the 1980s, and it really did look like this. This is not from the 1930s or something. Lots and lots of empty space. So this is the east end of campus looking towards Boston. The east end of Cambridge looking towards Boston. And only 20 years later, or so, it looked like this. So it all filled in, or at the time maybe we thought it had all filled in, but actually much more of that has filled in since that time. And in addition, some of those buildings that were built have already been taken down and something bigger has been put in their place. It's just an extraordinary and continuous explosion that is happening. So we work here. This is the east end of Kendall Square. This is the east end of MIT campus, and that includes most of where research is happening. And then we have 12 large corporations that are just examples of the many large global corporations that are right there in Kendall Square, choose to have a major presence there. And of course, there are thousands of startups in that area as well. And I'm going to bring my comments to a close, but just to say that these are 2 very integrated programs that we run, ILP and Startup Exchange. And again, that ecosystem concept is extremely important for the notion of what Olivier alluded to is we pick ourselves up and we drop ourselves off in other innovation ecosystems, and we're able to interact in a way that's very difficult when you don't have the 3 knowledge creators being brought to the table and that kind of thinking being brought to the table. So I'm going to stop there. I hope I didn't run over.
Thank you, John. Thank you, Laurent. So let's make the most of this day, and we declare officially open our symposium.
Thank you.
So thanks a lot, Laurent, Félicie, and John, for this very inspiring word to open the day. So I will hand over immediately to Olivier, just for the first session on the trend on surface mobility.
All right, thank you very much, Alexandre. So we're delighted to kick off this symposium on innovation for the next generation of mobility with insights from John Mohanvenzadeh. So John is the executive director of MIT's Mobility Initiative, a global resource to accelerate transition to a safe, clean, and inclusive mobility system. John is truly an expert and thought leader on the future of mobility, and we couldn't think of a better person to open up this symposium, telling us a little bit about some of the mega trends going on around the world, specifically on mobility. John has spent over 15 years at the World Economic Forum in different leadership capacity. So John, we're super excited to have you on stage, and the floor is yours. Coming up.
Such a pleasure to be back in this beautiful city. When speaking with Olivier last week about the planning for this event, we thought that it might be helpful to actually take a step back and reflect a little bit on some of those transformations, some of those disruptions that Laurent just alluded to. So what we wanted to do is to actually run through what we see as some of the key, you could call them trends, but I actually like to think of them more as tensions that we see playing out on the stage in mobility, because we see that sometimes the pendulum swings left and sometimes the pendulum swings right. So let me just a word to highlight a little bit about what we do at the MIT Mobility Initiative. As Olivier just mentioned, there's really just 3 goals: safe, clean, and inclusive mobility. I've spent a lot of time thinking about this. What should our goals be for the mobility system? I'm an engineer, and I often speak with engineers, and they always like to put in this word efficient. They want the system to be efficient. But I would ask, efficient toward what? What is it that we are trying to achieve, and for whom? And that's why I actually think inclusive is a better word. Inclusive reflects the notion of cost, the cost of mobility in terms of money, and the cost of mobility in terms of time. So I think that's sort of an important concept. Now, I mentioned research at the core of our focus at the Mobility Initiative. So we have member companies, they contribute, we fund research, and this is just to give you a sort of sample of the types of projects that we're working on. I'm not going to run through all of this, but just to maybe highlight a couple interesting ones. So in this lower left here, you see we're working on a project that we call Data Centers on Wheels. Now, this project is asking the question about how much energy is required to power autonomous mobility. So if you think, for example, about data centers, if we all constantly use data, we're using our phones, you're streaming, data centers globally consume somewhere between 1 and 1.5% of total electricity supply. So that is a significant burden that is imposed, an energy burden. So now we're asking a similar question. If we have a future that is predominantly autonomous, 10 years, 20 years in the future, how much energy is going to be required for the computing power, not the propulsion power, the computing power of those vehicles? And according to some early estimates by our researchers, the answer is not insignificant. So that's something that we're having a look at. This question about electric vehicle charging infrastructure. in the United States, if you pull up to a public electric vehicle charger and it's outside of the Tesla network, there is a 20 to 30% chance that it will not work or it will not deliver the power that you are expecting. This is a problem. And we looked at why, what causes this challenge with reliability. And there's a host of reasons for this. It comes down to everything from bugs inside of the charging station. Literally, I'm talking about insects, spiders, things like that. But the most important driver of it is a systems challenge. There are many data handshakes that take place in the system of electric vehicle charging. You have electric vehicle manufacturers, the auto companies, you have utilities, you have charging service providers, et cetera. You have many stakeholders in the system, and they don't coordinate well with each other. So these are just some examples of the type of work that we're doing. Let's talk a little bit about the 10 trends. So the first trend, it's interesting that I would start with something more political, but I actually think that we're at a sort of geopolitical moment where the influence that we're seeing in this sort of these emergent two camps in the world, the US-European camp and the Chinese camp. And we're at a moment where politics is profoundly influencing industrial structure. China has moved from being an imitator 2 decades ago to very much being an innovator. And we're seeing political influence enter this space, the automotive space, in very profound manners. So, some headlines from just this past year, the announcement by the president of the European Commission to investigate subsidies for electric vehicles. In the United States, this controversy with Ford, with CATL is a Chinese battery supplier, an amazing company, and they signed an agreement with Ford to build a plant. And there has been a sort of, political backlash to that. So the point here is that politics is influencing industry in a profound manner. We've always seen this, but it feels very, very pronounced these days. A second trend is around what I would call the autonomous backlash. So this is, we have lived through the Gartner hype cycle in autonomous mobility. We have climbed to the peak of expectations, and we have plummeted to the trough of disillusionment. And yet we come through that, and we realize that this is harder. To implement this technology is harder in many ways than we thought. And in the United States, a rather serious public dialogue has finally emerged about why. Why do we actually want this technology? Not for technology just for the sake of, wow, that's cool, but what does it actually enable, and for whom? What problems does it really solve? And so we have seen these kind of, unfortunate incidents with some of the robotaxi providers, having, yes, let's just call them unfortunate incidents. But I think, long term, this is an example of the pendulum. Long term, this technology delivers so much capability to be truly transformative. And I think we will get through this, and we will thoughtfully figure out how to deploy this technology in a way that really creates true social value. And I think these numbers that you see here, the sort of loss of value that we've seen from so many of the companies that are playing in this space, I think we'll see a reversal. Okay. Third trend. Many of you are intimately familiar with this in this room. I started my career, 35 years ago, as an engineer at a car company. I worked at Ford. And at the time, we made engines and we made transmissions. And we did that because we thought that was core business. It was absolutely essential to what the company does to engineer and manufacture those products in-house. And today we see something a little bit similar with batteries, with system-on-chip design. I mean, just walking through the Munich show last month, I was amazed at how many people were displaying these little chips. Remarkable that automakers are moving into this business. And we know that the goal here is to deliver more functionality into the vehicle, to make the vehicle your next device, to complement your phone and other such devices. It certainly involves moving from a mechanical-led platform design, which some would argue Volkswagen perfected, moving into a kind of software-led design, which is very difficult for vehicle manufacturers to actually achieve, to actually make that transition. But these are some headlines just from the past year that reflect what's going on there. Okay, the fourth transition. Micromobility. I personally believe that micromobility holds tremendous potential to transform how we move around in cities. And no city in the world has received more attention than where we are right now. People are really talking about this city, your mayor, trying to understand, has it gone too far? Is it too little? What will the Olympics be like, etc. And I characterize this as well as a kind of pendulum swing. You know, maybe we have swung too far in one direction, but we're understanding that certainly we've moved beyond the days where companies just dump scooters on city streets. That's not the way to do business. And we've moved from this kind of competition in the market, where a whole bunch of scooter companies move in and dump scooters, to a kind of competition for the market model, where cities actually put out requests for proposals and they decide which provider we are going to work with. So that's a tremendous development. And I think, again, a little bit like the autonomous path, we will find our way through this, and we will find a way for micromobility to be an important complement for the urban mobility solution. A next big trend is around moving ultimately toward a dynamic pricing model. So we so often have these kind of economic externalities in transportation that are just not reflected in the cost that the user is paying. So if you think about a large SUV occupying precious space on a city street during rush hour, is the occupant, is the driver of that vehicle actually paying the full cost? And what we've seen, I think, is an interesting evolution toward congestion pricing. Congestion pricing where we say we will charge more at 7 o'clock in the morning to use the road, moving toward dynamic pricing, which is to say, we will charge a lot more at 7 o'clock in the morning if there is a major event happening here in the city of Paris. So actually, excuse me one moment. I'm just going to grab a little sip of water. Désolé. So I think where this is another sort of evolution where we will make that transition into a sort of dynamic pricing world, and we've seen it happening. We've seen it happening with highways in the United States. Now there are 5 different highway systems where you do pay depending not on the time of day, but depending on the level of demand. And we will see that, I think, happening in other parts of the world. A 6th trend has to do with our shifting mobility demand patterns. And here, this is not a trend, this is a stabilization. This is where we are in the post-COVID world. These data that you see on the right, this is from the United States, this shows what percentage of people are actually working from home, and on a sort of percentage basis, full days worked from home. And what you can see is that we've stabilized at roughly 30%. And so we are in this new reality of what you could call hybrid working, and that has, of course, a profound impact on the mobility demand, has a profound impact on the mobility system. A 7th trend has to do with what I would call hesitation in electric vehicles. So we have seen, I mentioned some of the challenges around the EV charging infrastructure. There's this issue of securing the supply of the graphite, the cobalt, the nickel, the lithium, the things that you need to cook a battery. How do we actually secure that we can get those materials, much less build up the gigafactories? I mean, it takes 10, 20 years to bring a new mining facility online. So these are very long time cycles, and it takes a long time for the market to respond to that demand. And I mentioned, of course, this issue about the charging challenge. So, what we've seen is a year ago, at least in the US market, a year ago today, people couldn't buy electric vehicles. They were paying a premium. Right now, at this moment, there's an oversupply of them. Again, it's a transitional issue with the pendulum, and I think long term, it's unquestionable that we are moving toward an electrified personal mobility system, but there are some bumps along the road. An 8th trend has to do, and this is, again, apologies, this is a very sort of US-centric issue, but I think with some reflections in European countries as well. Why does it cost so much to deliver transportation infrastructure? We see thousands of these across the country in the US. This takes 3 years to deliver. The actual implementation of the roadway itself, where the road is shut down and the bridge is put in place, takes 72 hours. It takes way too long to build some of the basic transportation infrastructure, and it's way too expensive. Why is this? There are so many reasons, so many reasons. It has to do with the capacity that we have in state departments of transportation in the US. Do they have the right people? The capability to manage some of these large engineering projects, oftentimes they don't. They outsource it to consultants. There are some very complex procurement, or I would say odd procurement requirements. Labor costs are expensive. The democratic process allows people to challenge projects, that's people's right to say, I don't want that project, but it adds delay and it adds cost in the long run. So this is a really important issue. As you know, in the US, we're spending $1 trillion on infrastructure. The question is, how much value will we actually get? Will we just get $100 or $300 billion worth of value for the $1 trillion that we're spending? Okay, a 9th trend has to do with the cost of the capital flows into the mobility tech sector. So if you had told me, let's say 4 years ago, if you had said, there's going to be this thing called COVID, it's going to be a global pandemic, everybody's going to stay at home, and during that period, oceans of capital are going to flow into the mobility sector, I would have said you were crazy. But in many ways, that is what we saw. We saw a lot of frothiness. We saw the rise of these special purpose acquisition companies, the so-called blank check companies, a lot of excitement around electric vertical takeoff and landing, battery tech, electric vehicle, and so forth. And now what we've seen is that the capital is flowing out, or maybe there's a realization that mobility is hard to do. So we'll see. Again, pendulum swings one way or the other, but I think long-term, very bright future, but we're seeing a little bit more of increased skepticism on the financial side. And then finally, regarding the social contract, the relationship between business and society, we see, I would say, some significant transformations there. Automotive companies are really struggling to get the talent that they need to make those disruptions, those transformations that Laurent spoke of, to hire software engineers, to attract that talent versus to other tech players. In public transportation, we can't find bus drivers in the United States. So there's a number of workforce challenges that are playing out. And of course, I think most notably this UAW strike, the United Auto Workers Union, is very significant because it has, in many ways, opened up the public dialogue about CEO compensation and a number of other issues. So these are some of the trends. Let me just say maybe just a word about the great challenge in transportation, which is decarbonization. I'd say there's two camps out there. How do we decarbonize transportation? There's two camps. So one camp says, what we need to do is we need to fix the car. The car is dominant in society, and we need to move toward electrification. Maybe we need to move toward hydrogen solutions for long-haul trucking, things like that. We need to fix the car. And then there's a second camp that says, actually, the car is the problem. So we need to change our entire paradigm, particularly for urban mobility. And these folks say we need to put in more bike lanes, we need to enhance public transportation, we need to change our zoning and land use policies in cities that allow people to live closer to the things that they need, the things that they need to access, like healthcare and education for their children and employment and so forth. And I would just say that we're in a situation where I actually firmly believe that both camps are correct. We actually do need both. When I moved to Geneva to work at the World Economic Forum, I did not speak a word of French. And I was listening. I knew how to say bonjour and merci and things like that. And I'm listening, and I kept hearing this expression. I'd try to go grocery shopping on a Sunday, and I heard, ce n'est pas possible. What does that mean, ce n'est pas possible? I kept hearing that. So that was one of the first expressions I learned in French. And I would say, this is life in Switzerland, I'd say, well, actually, c'est possible, right? In fact, it is possible to have both camps realize their objectives in a way that coordinates and makes sense. So I think that's a little bit of food for thought to open the symposium for today. I hope that was helpful. Thank you very much.
Some of them, especially in Paris area, and mobility is quite complex. So now I hope you remember what has been told by Olivier at the beginning, that you had the possibility to ask questions on Pigeonhole, and we will see the first one of the day. No questions?
Do we have any questions from the audience then, without Pigeonhole? Maybe you can come back on stage, John.
Yeah.
Yeah. All right, we just need to find a way to display those questions. Otherwise, we'll make up questions. Anyone from the room asked a question and wants to repeat it before we get the system working? Yeah, in the back. Hang on, the mic is coming.
So I have a question about you talking about the pendulum swinging, and oftentimes you refer to the fact that right now it's just the trough in the Gardner's curve. How do you know when, do you have any tricks for identifying when it's just the dip and when it's maybe not a good idea?
So, you know, the Gardner hype cycle is based on something that also another MIT engineer said, Ray Armora, who's the president of the Institute for the Future. He said we consistently overestimate the impact of technology in the short term, and we underestimate that impact in the long term. And that's fundamentally what drives the hype cycle. And so to your question, it is very difficult to know when we have hit the trough. But I will say this on, for example, autonomous mobility. The famous question used to be, when is it coming? Well, we know the answer to that now. It has come. It is here. We have robotaxi deployments in cities across China. We have robotaxi deployments in several American cities. There's 300 cruise vehicles on the streets of San Francisco, navigating around, Waymo vehicles. It is here now. And in a way, if we take a step back, that you have to say that is incredible, right? I mean, I know that many of you have ridden in these vehicles, and I have seen just in 1 year, the calibration improve significantly. It feels far more natural to be in these vehicles now. So I would actually say for autonomous mobility, we have moved beyond that trough, and now we're sort of moving toward that plateau of productivity. And that is a long haul. That will take time to run through that sort of technology adoption curve, the famous S curve. But I think we will get there.
Thanks, John. I think we got the first question, and so you have a very few time to answer. So you see, for sustainability, the shortage of mineral resources and water becomes more and more critical. How do you deal with this constraint and the switch to the new models of cars?
I wish I had a good answer. That is really the part of the systems level challenge, because the actors involved in the mining industry are very, disconnected from our day-to-day existence here, working in the automotive industry. I think governments have become far more aware that you can't just say we're going to mandate electric vehicles. I think governments around the world have started to understand these geopolitical implications, these supply implications that I spoke to. And in many ways, people are also becoming better educated about these transformations. People today understand that, for example, driving an electric vehicle is a fundamentally different customer experience in terms of refueling, recharging the vehicle, than driving an internal combustion vehicle.
Thanks a lot, John, and a big round of applause again for you.
Thank you. Thank you.
So I think artificial intelligence is in the news continuously, and especially with generative AI. We were thinking it was very important to have a dedicated session for that today. So Olivier, perhaps introduce the speakers of the day.
Very good. Before I do that, I noticed a lot of questions on Pigeonhole that did not get answered by John. So 2 things. You can connect with John during one of the breaks. That's why we have breaks. And second thing, we'll make sure every speaker responds to the questions. So keep them coming, and we'll submit the list of questions to the different speakers. So don't stop because your question hasn't been answered. So to your point, Alexandre, yes, AI has been in the news. There's been a lot of discussions on the effective use of AI and the ethical use of AI, to be honest. So with this in mind, we're delighted to kick off a session on artificial intelligence with Professor Patty Mays. Patty is a professor in the iconic MIT Media Lab. You've heard about that lab for sure. Coming from a background in AI and human-computer interaction, she's particularly interested in the topic of cognitive enhancement, and I'm sure she'll tell us a little bit what's behind that. Her more recent research focuses on generative AI specifically. So that's why we're super excited to have you with us, Patty. The floor is yours.
Good morning. Bonjour. Good morning. Bonjour. So I actually grew up not that far from here in Brussels, where I got my PhD in artificial intelligence over 30 years ago. And so in that time frame, I've actually seen artificial intelligence being hyped, but then disappointing several times. We call these AI summers and winters. And I want to talk a little bit why in previous times that AI had some promise, shown some promise, it did not live up to its expectations, and how we risk falling into the same trap today with generative AI. So will today's generative AI live up to its promise? Well, I'll tell you what one of the changes are, or one of the things we have to pay attention to for it to be successful. So back when I started my PhD at the University of Brussels, expert systems were all the rage. And I don't know whether anyone in the audience was already looking at expert systems at that time, but they were actually in laboratory settings. They did very well in helping with diagnosing problems or solving problems, decision-making, etc. Of course, these systems were built differently than today's systems. They were hand-coded rules that would encode the particular expertise or knowledge in a certain domain. Now, when these systems were deployed in a context, in a human context, they typically failed. And the reason that they did so was not so much their decision-making power, but it was actually that the target users, the people in the company or in the organization that had to work with the AI system, they typically didn't trust the expert system. They didn't trust it because they were not involved in creating the system. These target users could not update the knowledge of these systems if there was some new knowledge available. The explanations weren't perfect, so the users didn't know, like, why did it make that decision? Should I trust this or not? The fit in the workflow was unclear. For example, if you take a doctor, a lot of the expert systems were meant, is the mic going in and out? Maybe I'll use this. Can we turn this one off? Okay. So a lot of these systems were actually basically helping people like doctors with decision making. And the reason why doctors also didn't want to use these systems is that doctors, would feel like some computer system was second guessing their decisions. So a doctor, like my father was a doctor, he had studied for 13 years to be an expert in his particular specialty of medicine. If you give somebody like that an expert system and you say, here, this system may know things better than you do, I mean, all the pride that you have in your job, the fulfillment that you get in doing your job and so on, suddenly you lose that and you don't feel good about your job. I think that this is a major risk actually of today's systems as well, that the people who get enjoyment from their job, who are proud in doing their job well, will actually resist using these systems because this is their life, this is their identity. They don't want to just be the manager of an AI system or the supervisor of an AI system that does all the fun work or all the exciting and interesting and challenging work. So AI is not just a technical challenge. It is not just a question of deciding. One isn't working either, I think. Is it? Hello? Yeah. It is not just a question of deciding on accuracy and avoiding limitations, avoiding bias, things like that. It is also very much a human factors problem, a problem of designing the AI to work with people and people to accept, for people to accept the AI. So I think some of my slides were translated, and I think some arrows and text is missing. But basically, so it's good you guys can guess, or maybe ChatGPT can guess what text would have been there. Basically, while the majority of people in artificial intelligence are still working towards AGI or general AI, that is sort of the ultimate goal that they have set themselves, to build systems that can surpass or outperform human experts. My goal has been to build systems, and not just my goal, but increasingly more people are arguing that we should work on intelligence augmentation rather than general intelligence. We should build and design AI to augment people, to work with people effectively. And this is a totally different problem. You're not optimizing the AI to not make mistakes or be biased or whatever. You're optimizing the combined human plus AI system, and you want to look at how that combined system performs rather than the AI alone. Now, Professor Erik Brynjolfsson, who until recently was at the Sloan School, actually refers to this problem of the field of AI as the Turing trap. Of course, Alan Turing is one of the founders of the field of artificial intelligence, and he set the goals for the field, and he said, well, we will have accomplished AI when AI systems can basically do everything as good as people or better, and we can't really tell the difference. And this is still the goal that leads most of AI researchers. You may have seen just yesterday, actually, OpenAI, maker of ChatGPT, changed its values and its mission, and their mission is general AGI, or general artificial intelligence. It isn't to do good with AI in augmenting people and benefiting society. It is matching or surpassing people so that ultimately people are less needed in a lot of the jobs. So Professor Erik Brynjolfsson is an expert in management science. He's now at the Stanford Management School. Before this, he was at MIT. And he has written a really interesting article. I highly recommend all of you reading that article, where he looks at historical data of other innovations that people have come up with, technical innovations, and he shows systematically, based on historical data, that if you augment people, you ultimately create more economic opportunity and also better social conditions than when you replace people with machines, basically, or with tools. So take a look at that article. It is very much the message from my talk as well, although my argument is more one of ultimately, I believe that AI will only succeed in deployment if we design it to work in a human context. So how might AI amplify human intelligence? Well, of course, every day we see examples of AI systems helping with information gathering and processing, with decision making, with creativity, creating images, etc. But I think that once we sort of think of AI as augmenting people, it can do more than that. It can also help with some of the problems that are very human problems, like often we have attention problems, especially with our devices these days, distracting us, motivation, grit, memory. All of us, as we get older, our memory gets less good and we have to remember more and so on. Learning, we have to be able to learn, of course, continuously throughout our career, but that becomes harder and harder. Just managing our emotions can be a hard issue. There's more and more anxiety, stress, burnout, things like that. I think AI will go beyond just helping manage and create information and make decisions based on information towards really more personal types of assistance in helping people with these more soft skills or emotional skills that are important for people to optimally perform. So I'll give you some examples of that from my work in a minute. So in our work at the Media Lab, we look at a whole range of issues in how to design AI systems to work optimally with people. We look at issues like how should the interaction be designed, how should explanations work, personalization, what happens if you personalize or customize AI systems to a person, personification, what if you create AI systems that look or talk and so on like a person, pretend almost to be a virtual person, other types of issues. So let me give you examples. We'll dive in from here into the studies that we do in my lab to clarify how all of these issues make a huge difference. So take first decision making. We're, of course, all bombarded with information all the time, especially persuasive information, whether it's politicians or advertisements or business meetings. And again, apologies, the slides were adjusted from Keynote to PowerPoint, and I did not get a chance to see them, so there's some funny things on the slides, funny fonts. So when assisted, we did an experiment. When a person is assisted by an AI, trying to decide whether some headlines are true or false, people actually, and you don't have to be able to read the graphs, I'll just give you the results or the punchline. People basically, if they're assisted by an AI, they improve their decision-making accuracy, especially when the AI gives explanations. If an AI just tells you it should be this way or that way without an explanation, people don't necessarily change their own opinion. So we do these types of human experiments in our lab where we, often it's remote, have tested hundreds of people in these types of experiments. And so we ask them, here's a headline, do you think this is true or false? They say their answer, then we have the AI give them advice, saying this is true or false, and possibly giving an explanation as well. And we notice that when the AI gives an explanation, people do change their opinion. and they do better with the AI than without. If it doesn't give an explanation, they actually don't change their opinion. But then we started thinking, well, what if the AI is wrong? What if the AI gives malicious advice or just wrong advice because it's just not accurate enough? We all know that these systems hallucinate, and some people argue that their performance may actually go down over time because they are training on data that is produced by other AIs and so on. The information quality that they train on is going downhill, and as a result, the decision-making accuracy may go down. So we learned that in gray here, you see both for true and false newspaper headlines, you see how well a person does in deciding whether a headline is true or false without AI, is the gray bar for true and for false on the left and the right. In blue, you see how well a person can discern true from false headlines if they have an accurate AI with explanations. If the AI then tells them, no, this is false because blah, 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 or something. But then we built an AI that gives you wrong advice. People's accuracy level dropped to 50% from their own innate ability to discern true from false. So what does this show? People basically believe AI systems too much. They stop thinking. They stop thinking when an AI system gives an explanation. This is true because blah, blah, blah. And it's always super convincing, these natural language-based systems. And they have an enormous persuasion impact. So they can very easily convince you to say something different than what you normally would have said without the AI. So this is scary, actually, that people become too reliant. They stop thinking for themselves when they are assisted by an AI that gives them convincing explanations. We actually have been designing other interfaces where the person, the user who works with the AI, is forced to still think about the problem before making their judgments. So we force them to do some deliberation about the problem in question before the AI actually gives its answer. So instead of the AI just saying, I think this is true because this, or I think this is false because that, it first asks some questions of the user. And we showed that in this, and again, I'll spare you the details, but that people then perform better even if assisted by a malicious AI, if they are forced by the system to think about it. Just recently, 2 weeks ago, we published a paper on how prior beliefs affect AI interaction. So all of us, of course, some of us are AI optimists, some of us are AI pessimists, maybe based on what movies you've seen, Terminator, whatever. And it turns out that your beliefs about AI matter a great deal about in interacting with AI. So we did another experiment where we had 3 conditions, 3 groups. We had them all talk to ChatGPT, but we didn't tell them that they were talking to ChatGPT. We told one group, you are talking to a neutral chat system that doesn't have any negative or positive motives to help you. A second group, we said, you are talking to an AI that has caring motives, that cares for you and will try to, and will really do its best to help you. And a third group, we said, well, this is a malicious AI that may try to manipulate you. But in reality, they were talking to the exact same system. We noticed significant differences having people work with these systems to solve a problem in terms of the outcomes. People saying, like, I would recommend this system, yes or no, I trust this system is helpful, etc. We had significant statistical differences in all these areas, only based on that one sentence that we told people in advance. So these are all issues we really have to think about. We also analyzed the conversation people had with ChatGPT, and it turned out that the conversation trend in terms of emotions in the conversation was completely different given the three different groups. In the neutral group, it stayed kind of neutral, but in the positive group, it tended more and more positive. People believed the AI and were happy with the AI and trusted it. In the other group, the interaction went downhill and the sentiment went downhill. A lot of our work in my group is about personal AI. We don't see this as much yet, but you may have read in the newspaper that there's definitely a lot of interest in this area from, for example, OpenAI. Personal AI means really AI systems that soon will be helping you, just like in the movie Her. Many of you may have seen that movie. Personal AI systems that will just always be with you and will know about you and your interests and your friends and this and that will help you in all sorts of ways with decision-making, learning, doing things on your behalf, etc. So one area, for example, that we have been doing a lot of work in is memory augmentation agents. All of you have to remember more and more information, also people in the research field, etc. I rely on my students to help me remember things, but increasingly we will have a personal AI that can help us with remembering important things. So I'll just show you the video of a system that we have been building. So it's basically a system that works with your phone, and it records conversations if you have permission to do so, and you can talk to it, to your personal AI. And the system actually tries to predict what you will say. Just like, ChatGPT just predicts words that come after certain words. Well, we do this for an individual in a mobile context. We are very interested in the aging population, but really this is meant for the aging population as well as for knowledge workers.
Hey! Hi, nice to meet you. I'm Robert. I'm an investment banker from Trade Investments.
Oh, and what do you do there?
So we invest in biotech startups that help with rare diseases, but you should reach out if you're interested.
Thank you, I will. Oh wait, what was his name again?
Robert.
So everything is recorded, so the system, you can just talk to it.
Hello. Hi, Grandpa. So once you're done with your walking, can you please get a dozen of eggs and a packet of bread and about 6 bananas, please?
Okay.
Okay, see you soon. Bye.
Bye. Taken bread and eggs. I don't know the third thing I have forgotten.
Bananas.
So you just have a click on your finger. Whenever you need help, you can't think of a word. Whatever you click, the system can tell the word, the name.
Oh yes, I actually just met this guy last week. His name is Robert, and he works in Fluid Investments, and they specialize in
rare diseases.
Biotech startups working in rare diseases, actually.
So you get the idea. I think this is the future that we go to for in terms of our personal devices, that increasingly our interactions with everything around us, the environment, the other people, remote communications, will be mediated with artificial intelligence. We've been testing these systems. We have another related system, for example, which augments conversations not with past information that you have come across, but with information that may be of interest to you based on what you're currently talking about. So if you were to come to the Media Lab, we would show you our room 244, where when you meet there with a group of people, basically there's an AI system that listens to the conversations, transcribes them, gives you notes of the meeting at the end, but it does more than that. You can run different agents that interject and proactively give information that may be relevant. Some of them just give definitions, like if I were to mention in that room plastic Omnium, it would give me a definition of what your company works on. We have other agents like the facts agent. Every time some fact is mentioned, the AI agent goes and looks for the data and brings that up on the wall, projecting it where everybody can see it. We have a devil's advocate agent. The devil's advocate agent basically tries to disagree with things that are being said and give other perspectives. So it becomes a very interesting system where AI is sort of an additional group meeting member that is trying to be helpful given whatever decisions are happening. We also have a version on the left that runs on smart glasses, where again, based on what you're talking about, you see interesting information that may be relevant based on whatever agent you want to run, the devil's advocate agent, a facts agent, etc., that gives you information about whatever topic you're talking about. We've also looked at how AI personification or anthropomorphization affects the interface. You may have read 2 weeks ago, Meta, the company Meta, Facebook, introduced agents, 24 of them, that look like human actors, basically are sort of deep fakes of human actors that are interactive. So they decided to anthropomorphize their chat agent systems. And we did a study that shows that which face you choose for an agent makes an enormous difference, again, in the outcome. So we have this system where we can easily make interactive deepfake people of historical figures or whoever. We published a paper about that.
We will learn about quantum mechanics. It is the description of the behavior of matter and light in all its details and, in particular, of the happenings on the atomic scale.
You get the idea. You can basically, for example, when you're learning or for any kind of agent interaction, choose whether you want Marilyn Monroe or Einstein or Harry Potter. And we did a study again with hundreds of people to test what effect the choice of character has. So we had two people. People, of course, recognize the infamous person on the left, Elon Musk. And then on the right, we have a non-existing character, same age, gender, race, etc. And we did.
I am a virtual agent generated to help provide.
We did an experiment where we had these two characters just teach a lesson in vaccines. We just picked a topic of vaccines. It was the exact same soundtrack. And we told people, this is a virtual agent. You're not being taught by the real Elon Musk. It's a virtual agent looking like Musk. And what we learned is that based on whether people, sorry, can I bring up the next slide? Yeah. Based on whether people liked and admired Elon Musk, the whole experience was again different. And note, we did the experiment back when Elon Musk still had some people that liked him many years ago, before he took over Twitter. But so yeah, the people who admired Elon Musk, because as you know, back then at least he had a serious group of supporters, they actually said, oh, I want to learn more about vaccines, and this teacher is so effective, what a great teacher, etc. The people who hated Elon Musk, of course, said the opposite, and the people in gray on the right, that had the neutral character, they did not do as well as the people who admired Elon Musk. So all these things make an incredible, significant, statistically significant difference in outcomes that we have to be mindful of. Actually, I'll skip a couple of slides here. I'm sorry. I can talk about it later. We've also been looking at how personal AI can help support attitude and behavior change, which is a very hard problem often. We work with Hal Hirschfield, who's a professor at UCLA. Before this, he was at Stanford. And we wanted to see whether we could make people think more long-term. Many of the biggest problems are problems of people wanting to do or taking short-term actions and decisions rather than thinking much more long-term. For example, climate and climate crisis is a long-term problem, but also people not, saving money for retirement is sort of this future discounting problem. So we made this system where you can talk to a future version of yourself. You just upload a picture and we create a 60-year-old version of you. You also tell the system what you are interested in accomplishing by the age of 60. You can say, like, I think maybe I want to become a biology teacher if you're still studying. And so you can say whatever you want to be, and I want to have a family, I want to live in the suburbs and have enough money to go on vacations and this and that. And then we generate the future version of you based on all that information, and you can talk to them. And you can ask, if you said, I want to be a biology teacher, then you can say, well, what is life like as a biology teacher? What are some pros and cons of being a teacher, and specifically in biology? And because ChatGPT has so much wealth of knowledge about people saying what it is like to be a firefighter, a biology teacher, a cardiologist, whatever, this is actually really useful knowledge and information where hallucinations matter less also. And we have people talk with their future self about all these pros and cons of the life they think they want. And we show that this actually changes people's behavior after the experience, more so than spending the same amount of time thinking about your future and what you want to accomplish. So it makes it more real, more tangible, and it has a more emotional impact, and therefore really changes people's attitudes and behavior. We want to do the same thing with more like sustainability, climate related behavior as well. We also use these agents to change attitudes by having people talk to agents that are different from them. You may remember that business schools have published lots of studies that show that a diverse group of people, diverse social backgrounds, but also diverse backgrounds in terms of what people have studied, etc., ages and so on. Typically, groups that are more diverse come up with better ideas. There's many studies showing this. And there's even people like Edward de Bono, who for many decades has been advocating a particular process to really think about a problem from different perspectives with this 6 hats method. Now, we can automate the 6 hats method with agents. So we have been building systems where when you have to solve some problem, first you do a little questionnaire, and the system determines what type of thinker you are, not just what your whether you lean more this way or that way, but what is your style of working and so on. And then we give you complementary agents that are good at the things that you are not good at. And it turns out that the results actually are better solutions and so on, because people are forced to work with someone who's different from them rather than someone who's the same. So I would like to conclude, and I hope you will get the message that AI, when designed to work with and for people, can be really effective and can go beyond just augmenting and improving work decisions and work performance. It can really help people at a personal level as well, with being or operating at their best level. Of course, I do have to say there's still many unresolved issues in generative AI, so use it at your own risk. These systems don't have real understanding, or they don't really reason very well yet, although there's progress being made every day on these issues. They always sound convincing, even when they're not right. That's one of the big problems. When an individual, not all people you work with will, like some will, confidently claim that they know the answer to a question, even if they don't know the real answer. But a lot of people will tell you, like, well, I don't know completely or whatever, but AI systems are just very convincing, even when they're wrong. Controlling their hallucinations and behavior is still an issue. They have biases based on the biases in the data that we're not always aware of. We don't understand how these models work. Even the people that built them don't know how they work and when they will fail and so on. We don't have good methods of auditing them. There's no, or there's the transparency and interpretability are limited. The rights of original creators of data are often not respected. The regulation and oversight is sort of still coming, is not there yet. And as a result, many legal issues are still being decided, liability, copyright, etc. So use at your own risk. What can we expect going forward? Many people always ask, will we accomplish AGI, general intelligence, again? With today's approaches of generative AI, it's unclear whether we will get there. There are limiting factors like data. We don't have enough data to train on. We don't have enough hardware to train these systems. We may not have enough energy to run these systems. But I would argue, I mean, should we even aim for AGI? That's really, again, the message of my talk here. Should we aim for AGI? I don't think so. I don't think it's necessarily the best for economic and social outcomes. We should also care more about how AGI and AI will impact society. Things like emerging abundance of fake news, which I'm sure you'll see, you're already seeing it with the Israel-Gaza conflict, but you'll see it in the American elections next year. AI content is polluting the web and our data. It may no longer be the case, but just as a few weeks ago, when you said, show me a painting of Johannes Vermeer in Google, guess what came up? An AI-generated painting, not a real thing. But it claims, or it says like Vermeer, and it's actually not a real thing. So this is, the outputs of these systems are being put onto the web and are polluting web content. Increasingly, these systems are running our lives, even though we don't totally understand them, making decisions about whether you get a mortgage loan and things like that, without, again, complete understanding. They are selecting as well as creating content, the content that we consume, Hollywood content, newspaper articles, etc., often with mistakes in them. They, of course, use massive amounts of energy and contribute to global warming in a significant way. And last, I would argue that they are eroding the fun and pride and fulfillment that we get from human work at the highest intellectual level. It's not the boring jobs that are going to be automated potentially if AGI ever exists. It's the fun or the intellectual jobs. And maybe all of us become baristas or something. or supervisors of AI who have to like double check that the AI did indeed do the real thing, which is a boring type of job, basically. So I do believe AI is here to stay this time, but will it live up to our expectations? I think that depends on us. I think we have to design and optimize AI for optimal human outcomes rather than falling into that Turing trap. Thank you.
So very impressive talk, Patty, and thanks a lot for all the insight. I think it's frightening in some sense. And there is no AI for the agenda, so don't worry. Fellow will talk just after. It's there is 1 hour delay on the break compared to what is displayed on the screen. So many questions to you. Is that okay? The first one.
Oh.
Can you? I don't read it for you. I think it's enough.
Yeah. Protecting company IP indeed is another issue. I didn't mention it in my list, but I should probably have listed it that sometimes these models actually do not protect information that you give them, which is of course in the case of a individual as well, but for a company a huge concern that some of your company's data may disappear. And there are solutions to this actually. There are now increasingly we are using more complex architectures for AI systems, not just using ChatGPT to do everything, but using what is sometimes called as retrieval augmented AI, or sometimes it's called vector embeddings and AI. Basically, you keep your company's data and knowledge bases separate, and you look up information using traditional information retrieval techniques from that data. And then you just use ChatGPT or these systems, large language models, to turn the information that is found there into a conversational answer to a question that was asked, or to summarize it, etc. So there are new techniques for building systems that protect the data.
Thanks. I think there's a new bunch. I will say it because in saying I always forget that people online watching to us, so sorry for them. We started quantifying the impact of access to generative AI from a sustainability perspective, and those tools are very demanding from an engineering perspective. Could it become bad for environment? So globally, AI and sustainability.
Well, the companies that make these models, of course, want as little talk about that as possible. I can't point you directly to one of the studies that does this. Maybe somebody else in the audience does. But indeed, this is a huge problem. And sadly, for example, Google had a group of ethicists working on the ethics of AI inside Google. They published a paper on the energy consequences of these systems, and they were immediately fired. Yeah. Timrut Geru is one of the people. So unfortunately, we cannot rely, even though maybe even the American government and our Biden thinks so, we cannot rely on these companies to regulate themselves. Their motivation is, of course, a commercial one. So we have to have external regulation and entities that supervise what they are doing with AI and how it can best benefit all of us.
Yeah, perhaps last one. I think I see one which is already Paris related. Do we trust too much? I will take the one. We trust too much AI and sometimes being, let's say, trapped in traffic jams. If you are using Waze, for example, you have the feeling to be rats sometimes.
Yeah, well, we already saw back in the 2 elections ago when Trump was elected, the whole Cambridge Analytica scandal was basically personalization algorithms that were driving people to be more and more sort of in two poles or two camps that no longer talked to each other. And I do think we risk the same thing with AI, that AI will reinforce or will be used to reinforce our beliefs. And we will become, again, even more polarized, which then results in countries not being governed and so on, and not finding a Speaker of the House, for example, and in the US. So I'm afraid it may get worse if we're not careful. Yeah.
Thanks again, Pasi, for this talk.
Patty, we're going to stay at the interface between humans and machines. And I'm very happy, Laurent, in your speech, you used the word design, because our next speaker is really an expert in design and design thinking. We know it's a key part of customer experience. And innovation in the field of expression and collaboration between humans and machine in particular is what our next speaker is focused on. So we're delighted to welcome on stage Dr. Marcelo Coelho. Marcelo is a computational designer working on objects, installations, and live experiences. And he's going to share with us some absolutely mind-blowing examples of some of the work that he and his team have accomplished. So Dr. Coelho, the floor is yours.
How's it going? Can you hear me well? This is good. If there are audio problems, just wave your hands and we'll figure it out. Cool. All right, so let's start. So hi. So my name is Marcelo Coelho. I'm head of design of Formlabs, which is a 3D printing company that has come out of MIT in the last 10 years. I'm also faculty in the MIT Department of Architecture, where I teach courses on design and artificial intelligence. And I run a lab called Design Intelligence that's focused on design and artificial intelligence. So this is a car. There's a car that was generated by an AI. I think it's a pretty cool one, actually. And as you probably know, like in the last few years, deep learning, and in particularly generative AI, have completely revolutionized the way that we do sort of technical and also the sort of creative aspects of AI. But this is not an actual car. This is an image of a car. And to make a real car, as you probably know, and as we've learned yesterday during the tour of Omnium, you need to think about things like materials, fabrication, physics, how do you deal with human experience, how do you deal with environmental impact. And I think most importantly, in many ways, is how do you address manufacturability? How do you make these things at scale so that everybody gets a chance to have and use them? So in my lab, we really focus on this gap, on this problem of how do you tie artificial intelligence to the physical world by inventing new forms of collaboration between people and AI. So we did this by working across 3 levels: objects, interactions, and networks. Starting with computational materials and objects, supporting new kinds of human-computer interactions, and scaffolding to sort of larger scale, kind of human collaborative work. Is my audio okay? I feel like it's going in and out. Cool. So let me give you some very concrete examples. I have about maybe 30 videos in this presentation, and Olivier told me to go kind of quick. So if you have any questions, if I go too quick through something, you have more questions, you can ask me later. So I'm going to start with 640 by 480. This is a project that it was a commission from an organization called Design Miami that does a design and art fair at Design Miami and Basel every year. And it's a project that I actually did when I was still at Patty's group. I'm actually Patty, old student, so it's quite an honor to speak right after you, Patty. So 640 by 480 is actually an experiment in trying to make computation physical by literally making physical pixels that you can use and interact with to create. So let me show a little bit of how this works. Do you have audio? Perhaps not. Doesn't matter. So this is what the pixels look like. So there's a bunch of little sort of cubes. They're kind of like litter-independent computers. Every time you touch one of these, they change color, and they cycle through a series of different colors. There's like a kind of a color palette. And what's really interesting is that also if you touch one of them and you hold it, you can transfer color from one to the other. Your body becomes a kind of wire and it does a sort of a physical copy and paste. You can see it here. There you go. Yeah, I don't know if you have audio for the videos. I think the future videos are going to need audio. No? Okay. All right. Maybe I can sing next time. And they also work with a remote control, so you can interact with them at a sort of a very local level, physically interact with them, but you can also step back and you can interact with them at a global scale. And in this case, with the remote control, with infrared light, you can paint them with light. So you're literally using light to control light at a kind of a large scale. And you can create all kinds of animations and sort of behaviors. You can make them animate faster or slower. And eventually you get lots of this together and it creates this much sort of larger scales and behaviors. So let me keep going, I'll show you. So in a project like this, almost everything is custom made, from the enclosure to the batteries to the electronics. And what's particularly interesting in this one is that the glass is quite custom and it's quite sort of special. There's actually sort of a glass composite that's made out of two pieces of glass. One that's a kind of a flashed opal glass that acts as a diffuser, and there's a glass that's ITO coated that's conductive. And that allows you to create a really nice sort of light appearance, while at the same time being able to touch it, to change colors, and transmit and receive data through the actual glass. So I've been quite lucky to show this work all over the place. So this is an exhibition at the Creators Project in San Francisco that was supported by Vice and Intel. And it's really actually quite cool to see what people do when you have lots of these in a very big space and the kinds of things that people create. This is another one at Ars Electronica in Linz, not too far from here. And it's interesting because when you start thinking of computation as a kind of material, you end up creating all these things that we're sort of used to doing in the physical world. So in many ways, I think that this project is kind of a digital graffiti. When people first interact with it, and you might ask, why would you want to play with this in the first place? It becomes a sort of digital graffiti. Like, people move them around, they write their names, they make little drawings, and then over time, it becomes a sort of very complex kind of medium, and people create very complex kinds of compositions and designs. This is actually a very interesting exhibit. This is at the Corcoran Gallery in Washington. And this is a very traditional museum, right? So typically when you go to a museum, you're not allowed to touch anything. There are barriers. You have to stay away from stuff. And the security guard would come to people and be like, hey, you can touch this. This is different. And there was a group of about 10 teachers that came to see this exhibit. And they discovered that they could clone colors with their hands without no instruction. And they also discovered they could hold hands and clone color across people. So when I got there were about 10 people doing this, which is a very different kind of sort of interaction and behavior that you typically have with an artwork in a museum, where you don't touch anybody, you don't touch the work, and this is sort of much more communal and physical. When you get a lot of these together, you start creating all kinds of different behaviors. So this is what it feels like to paint with light. You can literally just sort of kind of brush it with the remote control. And then this is something that we discovered afterwards. So if you actually covered the light coming from the remote with your body, you can create this kind of digital silhouettes. And I think that that's what's like one of the biggest motivations for me behind some of this work is that once you create smaller units of computation that sort of physically exist in the world, and you put them together, new kinds of sort of emergent behaviors come out of them that you couldn't quite predict it from the beginning. So Silverlight is another project that explores the future of design and fabrication and how we will be able to make products in the future. So this is a commission by the Museum of the City of New York, and it was a collaboration with this design studio called Randall Ash. And the Museum of the City of New York asked us to reimagine the use of silver in the future. So in the past, silver used for making household objects, like plates and candlesticks and bowls. And today, silver is primarily used for making electronic circuits and semiconductors, just because it's one of the most, it's actually the most conductive of the metals. The material scientists can correct me on that one if I'm wrong. So this is what it looks like. So it's basically a sort of a plastic sheet where we inkjet print silver, and then LEDs are added to it, and then it can be sort of rolled up into kind of a tube that resembles a candlestick. Yeah. And I think that this sort of way of thinking about products is very powerful and very fascinating. So you can imagine, right, in the future, you can 2D print a car. I'm pretty sure one day we'll be able to get there, and even just looking at the way that the tanks today are made through blow molding. And then, you ship it flat, and then when it arrives to you, you just kind of expand it into a three-dimensional object that you can then use it. Actually, this happens with the drones today. You can get flat-pack drones that you can expand into full functional objects. The pop-up factory is another example of looking at different ways to design and manufacture objects. So this is an example of creating a fully generative product that's designed, 3D printed, assembled, and customized by users in real time and on demand. So it starts like this. Users can assemble their circuits using a pick-and-place machine and silk screening. The kind of the units or the devices are 3D printed. And this is a bank of 3D printers. And from the same design, we generated multiple variations of the enclosure. So when you arrive there, you can pick one, and you can assemble the one that you like. And then you can put your own sort of profile and software into it. So everything is customized from top to bottom. And in this example, what the device does is it's for an event. So if you bring them close together and people share things in common, they light up to indicate that you have something in common with somebody else. The technology behind this is both quite simple and quite complex. There's an RGB LED that sends a light on, but there's a radio that does mesh networking. So every single device talks to every single other device. And using proximity, they can tell how far you are from each other and what person you're communicating with and what kinds of things you should show. So you could think of this as a way to sort of have a kind of a crowd visualization that's not on a screen, but it's actually overlaid onto the crowd itself. So going from objects towards interactions, I think AI is going to be, has already sort of been a very big change in terms of giving us new kinds of input modalities and new kinds of creative tools. So I'm going to give you a few different examples. Being Material is a book in a collaboration with Skylar Tibbetts and Ru Kang. So at MIT, we had this event called Being Material. There's an event about computation and materiality that brought folks from all kinds of different fields to speak, but then also write articles for the book. And we're very interested, when we're putting this book together, thinking about what is it like to augment a book while still preserving the experience of reading a book. I don't know about you, but if I have a Kindle, I have an iPad, but I still buy actual paper books. I really enjoy reading books and newspapers. Maybe that's going to end at some point. But what this does is we really wanted to preserve this experience while allowing you to go deeper into the articles and get more information about each one of them. And typically the way that you do this, right, you have a QR code, you have some electronics, it adds a lot of complexity to the device, it makes it more expensive, and it kind of changes the typical production processes that you have when you make a book. So what we did was a little bit radical in some ways. We took about 150 photos of every single spread in the book for account for different kinds of angles and lighting variations. And then we trained a classifier that can recognize exactly where you are in the book by using a camera. So I will show you here a little bit how it does this. So if you go to this website, the beingmaterial.mit.edu, and you point your phone at the book. The videos are a little slow for some reason, but I'll talk on top of it. And in this case, and then it pulls up videos or whatever content. Sometimes it's music, sometimes it's video, sometimes it's image. So in this case, this is an article from Tal Danino about the aesthetics of bacterial growth. And we're pulling up videos of different bacteria growing in petri dishes. This is another example that I really enjoy. So with the book, we ship this sort of green bookmark. And you can actually use the bookmark by moving it around to kind of edit the designs that are in the book. So it's kind of a sort of a generative designed cover. Cool. One area that I've been super excited about recently is exploring the use of large language models for creating objects. We've been calling this large language objects. So it's sort of creating physical interfaces for large language models. So they can use them without using a screen or without using a keyboard. So this is an example from two students of mine, so Ara and Yubo. And they made this project called the Nawatron. It's a small little projector. It has, you can see this sort of lens on the front of it for a camera. So it's a projector, camera, a little hand crank, and a button. And what it does is it allows kids to tell stories by using shadow puppetry and using a series of different machine learning models. So I'll play this video that shows how it works, and I'll explain to you. So you start it, it gives you some screen kind of instructions or some projection instructions. And then you can create a shadow. So this case is like a little dog. And then once it registers, it then goes on to kind of generate a story and generate images that can support the story. So there's a series of models here. There's ChatGPT or GPT for creating the story, the storytelling. There's DALL-E for creating the image that you see. And there's also a classifier for recognizing the different shadow puppets. Can we get audio on this one? No audio. All right. Once upon a time, there was a little dog named Max. It actually kind of intonates it quite well too, which is really fun to see. It's very compelling. All right, I'll keep going. We're kind of you can check this up online, and you can see all the details as well. Here, cool. Another one that I've really that I really like and I really enjoyed is a VBox, which is a project done by my students Artem and Danny, and they basically created a radio. But it's a radio that allows you to sort of travel through music or go through this kind of musical journey by how the music feels rather than a particular sort of musical style. So the way it works is you start with a card that kind of gives you a style or perhaps even a song, and you insert this into the radio. And then it goes to GPT, says, hey, this is the song that I want, or this is the style, give me a song. It then goes to Spotify, grabs the song, and then plays it back so you can hear it. And then what it does is you see, once it picks up a song, it plays it, and you get a series of words that describe the song. And those are human descriptions that it has gotten from a large language model what the song is sort of all about. So, it's based on emotion, sort of background, social context. And then there's, on the other side of it, there's a little crank that you can use to sort of navigate through these words, and then pick the one word that you perhaps like or that you wanted to continue kind of your navigation on. And then from that word, it then picks up another song. So what's really interesting about it is that you can go from song to song, navigating through styles, but always keeping kind of the same vibe and the same sort of style of music, which in a social context is exactly what you want. You want a particular kind of sort of mood and environment, and not a particular style or particular kind of song. So it's a very different way to think about how to navigate through music. All right. So doing a lot of this work, one thing that became really obvious to us is that we need to have better tools for working with neural networks. So NNN was a collaboration with Philips Lighting, to design new tools for architectural lighting that allows people to create interactions and animations for lightings that are in buildings, in facades, in a much easier way than they do today. So what we did is we created a node-based programming language. So typically when you program, you can write code, just text, but you can also do it visually. You can get little blocks of little bits of code and you can connect them together into complex behaviors. And what we did is we created a system that allows you to connect like a bunch of different neural network models together. So let me give you a few little examples. So this one is, there's a main kind of block in the middle that picks up colors from an image, sort of predominant colors. So one thing that Philips wanted to do is to allow buildings to celebrate different events in a city. So in Boston, for example, during the 4th of July, we light up the buildings with the colors of the flag. So you want to be able to load an image, pick up the colors automatically, and then display those in the building. This is another example. This is Diego from my lab, and there's a model that tracks his body position and his hand, and then by moving, he can move the kind of red dot back and forth in the image. A lot of times, Philips will light up facades, and they want to be able to have very simple, like easy to put together software that allows them to make those facades interactive. And of course, you can make this very, very complex, where you can combine multiple models together. So in this example, you're picking up a color, we're tracking his position, he's also training the model and like to do different things depending where he is on the screen. And then by combining all these different things together, you can create these really complex behaviors. All right, I'll keep going. And what we're doing now is actually expanding this back to the physical world. So we're using phones as proxy for lights. It's a little crazy to think about it, but you can get a full phone with the Wi-Fi, camera, I mean, you name it. That's actually the same price as buying a little LED box, which is insane to me. And what we're doing is we're actually distributing these neural network models across all of these different devices and have them work together, both operating independently, but together creating behaviors that make sense and that work to create single experiences. And I think this is the kind of stuff we're going to be seeing more and more. I think that looking at how we're creating objects today by sort of designing them with large language models, running large language models in objects, and then having them interact together across objects, it's the kind of experiences we're going to start seeing to the future. So scaling up from interactions to networks, one thing that we are looking at as well into is how to distribute agency across people, parts, and tools. Like, where do you put intelligence exactly? Is it in the human? Is it in the parts, in the tool? Is it how we work together? So let me give you a few examples of how this works. So Window to the Heart is a project that we did for Times Square for Valentine's Day. So every year, Times Square celebrates Valentine's Day by putting sort of a big heart sculpture in the middle of Times Square. And we were very inspired by Fresnel lenses. So Fresnel lenses, you probably know this from cars or from car spotlights. So it's a technique to get a very large piece of a lens, like a very large piece of glass, and you sort of geometrically split it up into pieces and you flatten it. So that way you can have a sort of a much smaller piece of glass. It's easier to transport and install, and you can create very giant pieces of optics. But instead of you doing glass, which you have to cast and you have to polish, and it's really difficult to work with, we use some generative 3D printing combined with sort of the human flexibility in assembly. So combining sort of two techniques, the digital and the human, we could create a very large lens. So this is how it started. So we designed a lens that had a heart in the middle, and that's made out of 13 different kind of tile types that are 3D printed and assembled into sort of a substrate. It's fun. The video is super slow. It will speak very slow too. So this is a 3D printer printing one of the lens pieces. So this is a clear material that's optically clear, and this is a form cell, which is basically a kind of a cabinet of 3D printers that you just send your entire sculpture to, like thousands of pieces, and it progressively prints all of them and does all that management for you. I like to think of this as a future of injection molding, but a kind of injection molding, there's no tooling. You don't have to spend any time tooling. You can change production like on the spot whenever you have a new design. Your design can even evolve based on feedback and changes or things you've learned during production. And then went through a process of assembly. So this is my team at Formlabs, and we're putting the lenses together against this sort of large kind of acrylic backing that gives it structural rigidity. The conditions at Times Square in February are very, very tough. It's cold and it's lots of people, so I have to be very safe. Cool. All right, I'll keep going. And it's really interesting when you do this kind of work, because we simulate the stuff or render it just to see what it's going to look like, but you never really know exactly what it's going to look like. And until you take it out and put it out in the world, it's like you don't really know. So it was a very sort of nervous and exciting moment for us. But so what it's doing here is that this is not lit. So it's just a piece of giant plastic that's like 3D printed and shaped to behave like a lens. Because we didn't want to add any more lights to Times Square. There's too many lights in Times Square already. So rather than adding lights, we decided to just capture the light that's already there and kind of reconfigure it into a new experience. So what this does exactly, you can kind of see a little bit on this image, but at the top of it, you see this sort of little red mark, and that's coming from the Coca-Cola sign that's right above it. So what it does, it gets all the light that's kind of around it and sort of funnels towards the heart that's at the center. And yeah, so you can see it here. It's interesting too because it's Times Square. Like millions of people saw this. There were people there morning to night, and it became sort of a little bit of sort of selfie portal because folks would go in and kiss and take photos in the heart, and it was quite lovely, actually. All right, I'll keep going. So this not about follow sort of some kind of trajectory, looking at ways that humans and computers can collaborate to work on large-scale forms. So this is a project that was done in anticipation for the World Cup that happened in Brazil. And what we're trying to do is to do something that could celebrate soccer and sort of the soccer ball at a very large scale at a stadium. So we started by writing some software saying, hey, can we create an image made out of soccer balls? How many balls do we need? How big should this be? And in the end, we ended up having about 10,000 soccer balls to make an image with. It's actually a lot of soccer balls. And we've designed a custom soccer ball. So this is, I don't know if you're familiar with e-ink, but we've made a soccer ball that's very similar to e-ink in some ways. It has sort of a white and a black kind of component. And by flipping the soccer balls up or down, or by rotating them, we can get white or black colors. And you can kind of leave it in the middle so you get it sort of anti-aliasing. This is actually a really horrible soccer ball to play soccer with, because when somebody kicks them at you, you can't tell how fast it's spinning. It's really difficult to play with. It's good for art, not good for soccer. And we're inspired by this image from Leonardo da Vinci for Luca Pacioli's book on mathematics. This is a really interesting kind of moment, actually. I think it's one of the first images that we could find that an image of something that looked like a soccer ball. And this is a moment in time, a sort of mathematical description of forms, and their visual representation came together. So this is kind of how we did it. So we were at the stadium, we had the software. We projected the image that we wanted to create into the field that night, so we could see it. And then we traced it with a bunch of lines, kind of, you can think of it as kind of a sort of a framework for the creation afterwards. And then we gave, we had a series of volunteers that helped us build this project. So we gave everybody some instructions that were pulled out from the software that we wrote. But they're very local instructions. So everybody gets an instruction that says, hey, here's what you should do based on what you know about your local position. And that way you can work completely in parallel. You have multiple people building this together. So these are the two, this is the sort of first image that we did. We did two. One is Stadio Steca and one in Brazil at the Favela Vidigal. And it's interesting because even throughout the day, like because of changes in temperature, it's quite hot in Mexico. The balls would kind of inflate and would kind of pop out, and people had to sort of adjust them in real time. And what's really cool is that while we were making it too, it was really hard to see the image and making sure that what we were doing was going to work out. But eventually, when we actually took sort of the kind of a final photograph of it from above, from the exact same perspective that Da Vinci had when he drew it, you could actually see it pop out in 3D. And you see it in 1 second. There you go. And so this project was a collaboration with this Brazilian artist called Vic Muniz, who's been a long-time collaborator. And there's a Netflix movie about actually the entire project. So this is Vic taking the kind of the final shot from above at the end. There you go. I don't know if there are any big soccer fans here, but the Stadio Steca is a very kind of emblematic place for Brazilians. This is where Pelé made his had his big kind of World Cup moment. And I'm not a soccer fan, and it's too emblematic for me. And these are the two images we made too. So there's one at Stadio Steca in Mexico, and then the other one in Rio. And they have this sort of Renaissance composition to kind of reference back to the original image. And finally, I want to show the sort of Paralympics work that we've done. I was very, very fortunate to be part of the team that directed the Olympic ceremonies, or the Paralympic ceremonies in Brazil. And it was a very special moment to both be able to tell the story of Brazil, but also to be able to work with Paralympians and understand a little bit how the world is not designed for Paralympians, and the work that they go through to overcome the sort of technical challenge that they have in the physical world that we live in. A big part of this, and it was really important to me that we told this story that was about this combination of humans and technology working together. So this is Amy Purdy, who has actually done quite a bit of work at the MIT Media Lab with her. And she is a Paralympian, she's a snowboarder, and she's wearing a 3D printed dress, and she's dancing samba with a KUKA robot. Neither Amy nor the robot are very good at samba. And this is the one of the segments in the ceremony that I was mostly focused on kind of at the end of the project, and I was mostly interested in. So what we did here is we have this very interesting kind of collaboration between people and computers. So as you can see with the performer on the right, she's wearing a little headphone with a little wire, and she can hear just a series of radio pulses that are coming over the radio system, and the exact same pulses are heard by this light sticks that they're holding. Literally the exact same pulses. And where the performer knows where to go on the stage using those pulses, the sticks know what kinds of animations to play. And that combination between the sort of human position and the light animations creates the final show. And I'll play here a little bit how it works. It's too bad you can't hear the sound. Maybe I'll give you a little bit of the technical details behind it. So we're actually using FM radio, which is kind of a very old technology in some ways. And on top of that, we're driving it with DTMF pulses, which is basically the sounds. And it's kind of a very simple, old, but yet very robust kind of communication technology. So you can see here a little bit of the sort of coordination of both people's movements and the lights. All right, I'm out of time. Done. Thank you. If you have any questions, you're curious about the stuff, you can go to our website, or if you could just send me an email as well. Thank you.
Very impressive, and I think you give hope after the talk of Patty on the usage of artificial intelligence with humans. So thanks a lot, Marcelo. I think we will go for the first question. So in your opinion, how to prepare and train our collaborators to be ready to use artificial intelligence?
I think the first step is to start thinking about AI as something that's really unique and different and special. It's a technology like other kinds of computing technologies that we've had in the past, and I think we need to integrate that into the way that we learn about technology, that we learn about design. So for example, at MIT, I usually talk about teaching as I teach my students to go from woodworking to AI. We start with wood and a chisel, and we end up building neural networks. So all of that knowledge, all of those tools are kind of very highly integrated. They all work together with each other. And I think that's really the way to do it. It's like just by learning, collaborating, sharing knowledge, and making it all kind of part of the same thing.
Thanks, Marcelo.
Let's take the next question. So design is human-centric, thus a great lever towards augmented, not replaced, human capabilities. How do you see the collaboration between designers and AI developers?
In many ways, kind of I think a very similar answer as well. I'm not a big fan of disciplines. I hate when people talk about designers versus developers. I'm a designer. I'm a developer. I think in many ways that's a fault of our educational system. I think that we should learn about development and design and aesthetic and technology and science as sort of as just knowledge, and be able to put those together. So we stop having those boundaries of disciplines. I think in many ways AI will help us doing this. I think computation has helped us do that in the past. I think that it sort of creates a kind of a lingua franca that we can all use and talk to be able to work together. And I think perhaps in many ways AI could help us do even more of that.
Okay, thanks, Marcelo. Next one. Marcelo, you have me feel better about it's not me, but even if it's true, I feel better about the fate of artists and designers in artificial intelligence influenced by design world. To what extent do you see creativity connected to experience in future?
It's a good question. I love actually JB, who's sitting right there. I love his description of creativity, which is to create something that's new, but it's also meaningful. And I think that's really where this is going to happen. I think that we have a role of finding what's the meaning of these new things that we're creating and how they're inserted into a social and cultural context. And I think that that's what creativity will look like in the future.
All right. Well, I think we're going to leave it there. There's other questions. You can talk to Marcelo during the break. We are actually, believe it or not, right on time. Yes. And on time for a break. We're going to break until 11:45, and we'll be all back here then. So thank you.
Cool, awesome.
Thanks a lot. thanks a lot for coming back to the new session. I think there was a lot of discussion previously, and you have again a full level of energy. So now a new technical session on a subject where plastic Omnium is aiming at becoming the world leader. I'm looking to Mark for that, on hydrogen.
So if you consider the wider applications of hydrogen as a vector of energy and as a path to decarbonization, a recent report issued by the Engine, that's a fund that spun off of MIT in 2017, it's estimated that the hydrogen market is going to be about $600 billion by 2030. So hydrogen is definitely part of the equation when you look at green mobility in general. So to help us navigate the questions around hydrogen for mobility, we're delighted to have Professor Harry Tuller with us. Professor Tuller is a world-renowned expert in electroceramics and a professor of material science and engineering at MIT. His research group models, processes, and optimizes energy-related devices such as sensors, batteries, and fuel cells. So he's posing us a very interesting question with this talk. Are hydrogen-powered vehicles a forever technology of the future? Professor Tuller.
Good morning, thank you. It's really a delight to be here. I normally don't speak to this kind of audience, but I think we'll manage. Hydrogen for the future. We've been talking about the hydrogen economy for probably the last 75 years. And for very different reasons. Initially, it was because we thought we were running out of fossil fuels, so we needed some alternative. And the fact that hydrogen is produced largely by conversion of methane, which generates maybe 10 times as much CO2 as hydrogen, didn't really matter because, all right, we need the hydrogen and we'll use it for the future. But obviously, if we want to go forward, we're trying to minimize and eliminate the use of fossil fuels and eliminate the CO2 emissions. So then the question is, okay, can we finally make that transition to hydrogen? If we do, it doesn't make sense to make dirty hydrogen. We really have to go all the way to clean hydrogen. And there's fortuitously some really important developments which have occurred, and that is another technology which nobody believed was going to go anywhere, solar energy, in the last 15 years or so has made remarkable progress together with wind energy, which provides us with that electricity vector. And that's really key in terms of now enabling, we believe, the generation and development and accommodation of hydrogen. And why is that the case? And in fact, if we look at the left here, those sources of energy are intermittent. Yes, they generate electricity, but they need to be stored. And the best way to be stored is in a high energy density form. And if we can use that electricity in combination with an electrochemical device called the electrolyzer, which we learned about in high school chemistry, if you apply a voltage across two leads and a high enough voltage across water, you'll generate hydrogen and oxygen. The question is, can we do that now in an efficient manner? If we can store that hydrogen and use it again in a reversible device, which we call a reversible solid oxide cell, a fuel cell, and when that energy is required, convert it back to electricity and put it back into the system. What that does, however, is also provide the option for using some of that hydrogen for other purposes. For example, the fuel cell vehicle. So the fuel cell vehicle is something in which we use, again, the fuel cell, but rather than using that hydrogen to generate electricity for other purposes, we're going to use it for automotive purposes. And the question is, of course, is that technology already available to us? And the third thing I want to talk about then is in the fuel cell itself, in order for that to be realistic in terms of operating both stationary and under mobile conditions, that device has to be efficient, it has to be long-lived, and it has to be cost-effective. And so all of these idealizations where we take the hydrogen and convert it with oxygen to water, it's all very clean and very efficient. In principle, can we actually make a device that works on that process? So what I want to talk to you about is we have to step back and go into the laboratory and look at the different processes which make these electrolyzers and fuel cells operate, and ask ourselves the question, can we make them last the number of hours equivalently to kilometers? Now, these fuel cells would be needed, particularly in long-range vehicles like buses and trucks and locomotives and this sort of thing. So after halfway through the process, what I'd like to do is tell you about what we feel are some really important breakthroughs in terms of understanding and controlling the processes which limit the performance of these fuel cells. But more importantly, we know they degrade because there are various poisons in the environment which cause these catalytic reactions, which are so key at the interface, to maintain the initial performance. And that's been a real drag on this technology. And we've come up with some new insights which allow us not only to obtain initial high performance, but actually to recover a fuel cell after it's been poisoned. And I think that's perhaps the first time that's been done. That being said, that means in principle, we could either protect the device initially or go back later, and like we do, if you take a truck or vehicle into service, you can service it and get it running again. There's some kind of not so relevant technology, which I'm not sure I'll have enough time to talk about, and that's to we're using light to move ions through the solid and make that material more conductive, which is really key for the electrolyte inside batteries and fuel cells. And we're not sure yet exactly how it's going to be applied, but it's one of those far-reaching observations which I think ultimately, maybe 5 years or 10 years down the road, will have some important impact. So, in summary, these are things we are all familiar with. I want to just go through them very quickly so we see how we're getting to the path of hydrogen technology. So how do we get there? We're going to focus on transportation. Obviously, we're hooked on oil. And then we're going to look at the two electric vehicle options. One of those is already developed at a very, very rapid rate, much faster than we suspected or expected. And it's getting that initial process up the hockey stick, which is really key. The fuel cell vehicle is still down at the bottom of the hockey stick, and the question is, what will it take to move it up that slope? And of course, then I'll talk about now for something different, fundamentals, and that's what I get paid to do. But what I hope to demonstrate to you is by understanding those fundamentals, we can really make progress and make this technology more feasible. Okay, so the first thing many of you have seen before is there's a correlation between how much energy we use and our standard of living. Obviously, that's not only because we drive vehicles, we heat our homes, but all the materials we use an enormous amount of energy. And in fact, there's probably a factor of 100 between those with the highest standard of living and the lowest. What is the impact on vehicle consumption and use? Well, a prime example of that is what's happened, for example, in China in the last 20 years. There's a large population that was always there, but the GDP has been growing at an enormous rate. And in parallel, you can see the enormous growth in the number of vehicles, which went from the order of a couple of million to something like 25 million in just a couple of decades. So those two together, obviously, if we don't change the mode of transportation, we use the internal combustion engine, will just send us out of this universe. So how do we relate that to the overall consumption? So it turns out, we can see here, that transportation directly by itself uses about a third, almost a third, of the fossil fuels. Much of it is, 38% is electric power generation. Now, as I mentioned before, in order for us to get clean energy, we're going to have to use electricity to electrolyze water. So that means we have to clean up the electricity as well. So really, in reality, we have to combine those two and demonstrate the feasibility of getting that kind of clean energy sources. So what's our love affair with the fossil fuel? You pull in and you say, fill her up. and within minutes, the vehicle is filled up. We have the infrastructure for that. For example, in the US, something like 150,000 filling stations, almost 300 million registered vehicles, and of course, many more around the world. And the key is it's low cost, long range, and you only have to spend a few minutes. And that's, of course, one of the potential liabilities of the conventional battery-operated vehicle. And that's where if we can replace this experience with something that's much cleaner, like hydrogen, this, of course, would be very attractive. But the challenges here, as we all know, they're non-renewable, they're strategic, they're contaminating, and so on. So the handwriting is on the wall, both between government regulations and incentives. The combustion engine is going to be a fossil of its own very shortly. Whether it's within the 2030s or by 2050, I think that's going to depend on where we live and where we act. So is there a future for electric vehicles? Of course, the future is here. The adoption of electric vehicles by the battery-operated ones has been astronomical. So just in 2022, it increased by 55%. And now we're talking over 10 million vehicles. I remember just a few years ago, it seemed like we said, oh, here's the first 100,000, and here's the first 200,000, and so on and so forth. And as we can see, here, that mainland China is in the lead. I was there about a month ago, and you could see many, many electric vehicles on the road. And something like 30% of the vehicles sold in 2022 were electric. Europe now has a 26% share, and the US share is close to 10%, but look at the rate at which they've gone up by 72%. So there's no question that the electric vehicle is being accepted and is going to continue to grow at these incredible rates. So what are our options? Of course, we're familiar with the hybrid, and Toyota made a big impact already more than a decade ago with the hybrid device. But now, we're looking very much to the direct complete battery option. People have been very impressed with the performance, the acceleration, the lower costs, and just the aesthetics of being able to drive in that kind of vehicle. The alternative is, for example, the Toyota Mirai, which is also a very attractive vehicle, but as we'll see, much fewer have been sold to date. So if we look at the electric vehicle sales breakdown by type and location, really the key is that most of it is presently for light-duty vehicles, okay, like 99%, something like that. And within the battery electric vehicles, it's really the complete battery option, right? And as we saw before, it's already hit 10 million. However, it's interesting to look to see in terms of the transportation use of energy. We see that light trucks use 32%, cars and motorcycles 21%, other trucks 25%. The key is that while we have so many passenger vehicles, as we said, hundreds of millions, into billions, right? They only consume about 20% of the fuel. Trucks consume about 57%. So that's kind of an opportunity in a marketplace which is not really presently being satisfied by the battery-powered electric vehicle. So let's look at heavy duty. Still today, in terms of heavy duty, it's still, of the electric vehicles, which are much smaller in numbers, we're talking now, instead of 10 million, something like 100,000. Most of them are still battery operated. But you're starting to see some contribution here from the fuel cell. So what is so specifically distinct between the opportunity and the option for the fuel cell versus that of the battery? And it comes down to something called the Rigoni plot, which is actually a former colleague of ours in our materials department at MIT who put this together. And as you can see in the vertical axis, we have the energy density. And so that's how much storage you have. So how far can you go? The other part is the power density, and that's if you're at a red light and it turns green and you want to nail it and power out of that stop sign, that's where you want the acceleration. That's, of course, where the new battery vehicles really excel. So why is it so difficult to get off the alcohol wagon? Well, you can see the combustion engine is way over in the top right corner. That means it has both the range, the storage capacity, and the power. Although in terms of the power, between the engine and the explosions and all those mechanical movements, it takes some time. There's a time lag before it hits the wheels. So that's the beauty of the electric part. It's drive-by-wire. The electrons are moving at the speed of light. But nevertheless, what you can see is what the battery has is the power density, but it's lacking some in terms of the energy density, which means the range is limited. And particularly if you get to now very heavy vehicles, which have to go many hundreds and hundreds of kilometers, that's where the energy density part is important. Sorry. As you can see, the fuel cell is way up there. So there's an opportunity and a need. As we saw, much of the fuel that's being consumed is in fact for heavy-duty vehicles. Okay, so what's the difference between the high-energy density battery and the fuel cell? So I think it's worth making this quick comparison and distinction. Obviously, the thing about a battery is that everything is self-contained, and all you're doing is shuttling chemicals from one side of the battery to the other. And the beauty, of course, of these kind of batteries is you can recycle them, recharge them, but it takes time. So you have to drive into a recharging station, and it might take 30 minutes or an hour, depending on what kind of vehicle you have. And think about now a large vehicle, like a truck, which has a very, very large battery, then those recharging times might be even much longer. So part of the problem, as we mentioned before, is the capacity is limited in terms of range. Acceleration is good. Charging rates is something that people are working on all the time to accelerate that process and allow recharging to occur faster. But at the same time, as we're passing very high currents, there are degradation modes which come into play. For example, for lithium batteries, the lithium starts creating dendrites, lithium metal particulates, which go right through the electrolyte and basically short the device. And of course, this can be very dangerous. And the chemical stability of the electrolyte itself, which is typically now a liquid polymer, and there's much interest in going to solid-state devices. There's also the issue of critical materials. So let me just say, this is not a stagnant field. I think we're going to see that the batteries will continue to advance in terms of their capacity, in terms of their ability to be recharged faster and faster, and to try to reduce the dependence on critical materials, let's say replacing lithium with sodium, replacing cobalt and nickel with iron. These are all being done. So it's certainly not a dead horse, and it's still developments, but there's still other opportunities which we want to focus on in terms of the fuel cell. So the fuel cell, which is most relevant to the vehicular application, is one called the PEM, or polymer electrolyte membrane fuel cell. And the main distinction between the battery and the fuel cell is that at least a good part of the reactant is free from the air. So as we can see here on the cathode, we have air. We do have to carry around our hydrogen, and obviously this is an important challenge, is how to take that hydrogen, which is very light, and compress it, and this is something that Plastic Omnium is doing and developing the tanks to support this development. But the key is, and I want to emphasize that for my subsequent discussion, is there are really three main components of these cells. The first is the anode, where we take the fuel, which is a gas, and we have to convert it electrochemically into a proton, an ion, which goes through the electrolyte, and the electron, which goes through the external circuit. Why are we doing that? Well, of course, we could react hydrogen and oxygen, get an explosion, and we get a lot of energy out. We get heat and light. But what we're trying to do is do that in a controlled fashion. The way we do that is create two separate pathways for the ions, the hydrogen proton, H+, and the electron, which goes through the external circuit. And on the cathode side, we have another electrochemical reaction, which takes that proton and the electrons and combines it with oxygen to form the water. So as I mentioned, the attractive feature of this is it operates at fairly accessible temperatures, the order of 85 degrees Celsius. And, but there's a cost, and the cost is that these reactions don't like to happen that readily, and therefore we need catalytic materials which accelerate those reaction processes. So we're talking about a current flux through the external circuit. That means correspondingly we need these reactions to occur at the electrodes and the transport of protons through the electrolyte to occur at similar rates. And these rates can be accelerated with catalysts, but these catalysts are things like platinum. And some of the challenges associated with these materials is that these platinum particles, which are nanoparticulate and therefore have very high surface areas and high activity, tend to agglomerate. They also are supported on a carbon backbone. That carbon backbone with time deteriorates. So there are issues in terms of ensuring that you can operate, let's say, a vehicle for several 100,000 kilometers without problems. So these are the kind of challenges that we're running into. So there's the anatomy of the fuel cell vehicle. This happens to be the Toyota Mirai. So you can see the main components is the hydrogen tanks. They are in different configurations. In this one, they happen to be horizontal rather than vertical. There's the fuel cell stack, which we were just looking at. A stack is just made up of many of these individual cells. And of course, it has to be hybrid because the fuel cell cannot operate in a rapidly reactive way as does the battery. So you can turn a battery from 0 to max just by cranking up or decreasing the load across the material, across the battery. With a fuel cell, they tend to operate best under a certain flow of hydrogen and reaction rates. So there has to be a buffer between the two. So this is the new Mirai, which I happened to be able to experience while I visited Kyushu University just back in January, and talking there with Professor Sasaki, who's a fuel cell expert. It's a very nice vehicle. It works lovely, but there are only 2,100. We're talking about 10 million vehicles. We're talking orders of magnitude less than that. So we just want to summarize. What are the advantages of the fuel cell? It has the high power density, therefore the long range. It has good start and stop capabilities, the lower operating temperature, and it is scalable to larger vehicles. There are the issues that I mentioned. The catalyst, the polymer membranes. There is active water management required because you're generating water. You don't want that cathode to become flooded. And the other issue is poisons. I mentioned that before, that if you have CO or sulfur, those catalysts can become poison. That's problematic. And of course, we need the refueling stations. Where are the refueling stations? So this comes back to where has hydrogen generally come from before? It's typically been from chemical routes, for example, like coal gasification and methane conversion. And what you can see here are the numbers. So 8 to 10 kilograms of CO2 per kilogram of hydrogen produced by one of these reactions. So really, we have to bypass all of these and just go the electrochemical route, as I mentioned before. So what does that mean? That means we need to develop, upscale a technology which has been around for many years. But as the International Renewable Energy Agency has pointed out, we have to invest a lot, and I know the European community has made big commitments to contributing towards the growth and the development of large-scale electrolyzer systems. So that's the key. We need hydrogen that's low carbon and ultimately green right from the outset. Otherwise, we don't accomplish anything. And that's by electrolysis of water using renewable electricity. And it's the key, as we were just saying, for long-haul transport, shipping, and aviation. So part of that is we have to still lower the cost of electricity. So these sites will be located where electricity is particularly low cost. There has to be reduction in the cost of these plants, and they're proposing that with various kind of scale-up, that in the short term, we can make 40% improvements in terms of the costs, and longer term, 80%. And also fundamental breakthroughs, standardization, economies of scale, but also the kind that I'm going to talk about here. So it doesn't address hydrogen transport, right? How do we get that around? We can't put it into gas pipelines. So I think one interesting option, which I like, is the on-site hydrogen generation at refueling stations. And I'm going to introduce to you a different kind of technology. This is called the high-temperature solid oxide fuel cell and electrolysis cell. It's a reversible cell, which you can operate when needed, as I pointed out earlier. As you have intermittent electricity, you can generate the hydrogen. And when you need the electricity back, you can run it in the fuel cell. But for our purposes here, as I said, we can keep that hydrogen available for the fuel cell vehicles. So what's the advantage of these higher temperature systems, particularly if we can couple it in with some excess heat? A much reduced electrical energy demand. This is really key. No need for costly catalysts. So the kind of catalysts we use at higher temperature, because we have the thermal energy available to drive those reactions, are just relatively inexpensive metal oxides, ceramics. And they're much more resistant to these different poisons. So this looks good, right? We have water, we have electricity, just generated on site. So we don't have to generate the hydrogen somewhere else and bring it there. So the question is, what's the feasibility of that? So I don't want to spend too much time here, but the same organization, IRENA, as I mentioned before, some of the key things they've talked about is, as we said, the reduction in the electrolyzer costs, and the electricity costs have to come down, but important is the efficiency of the electrolyzer. That's one of the things I want to emphasize. And the other part is the lifetime, right? So it's good if it works fine, but if it dies after 10,000 kilometers, that's not going to do us very much good. So that's why I'm going to switch back to where I feel much more comfortable, the fundamentals. And I'm going to show you here again an image, a cartoon of a reversible fuel cell electrolysis cell. The reactions are very simple. As you can see, we might have in the fuel cell mode, I'm trying to use a pointer, I have no pointer. The oxygen in the gas phase has to dissociate into two oxygen atoms. Electrons have to be transferred to the oxygen to make it an ion. And once it's an ion, instead of a proton, we're talking about an oxygen conductor. It's transferred across the electrolyte where it reaches the hydrogen side and reacts to form water. So the efficiency depends on both the external interactions, these electrochemical reactions, and we call those in electrochemical terms overpotentials. That means we need extra voltage processes to drive those reactions. And the other part is the ohmic resistance, just the resistivity of the electrolyte itself. And I'm going to focus mostly on the interfacial one because that's the one that generally limits the performance and lifetime of these devices. So in particular, they are very sensitive, again, to different kinds of poisons. So I'm going to focus on one reaction, which in these fuel cells typically limits the overall efficiency and performance. And that's a very simple reaction I just mentioned before. The oxygen from the gas phase accepts an electron, enters into a missing site, a vacancy in the lattice, and that reaction itself often determines the overall long-term and short-term processes. It turns out this breathing process, oxygen going between the solid and the gas phase, is critical in many related technologies. Permeation membranes, solar thermochemical reactions. I don't have time to go into the details. But let me go to the solid oxide fuel cell. And like all of these fuel cells and all the batteries, each cell puts out some small number of volts. In the case of the fuel cell, hydrogen, oxygen is about 1 volt. So if you want a power supply with 10 volts, you need 10 in series. And of course, much higher current, many of those in parallel. And these are called stacks. So the way you interconnect one cell to the other is with something called an interconnect. And since these are operating at higher temperatures, they have to be resistant to those oxidative environments. And therefore, it's chrome steel. It turns out with time, some of that chrome evaporates, lands on the cathode, and poisons the performance. So to date, the understanding of that has been not too good, but it really does limit the feasibility of many of these technologies. So I want you to keep in mind for the moment initial performance, almost up. Yeah, so let me just quickly jump to what the DOE targets are for the solid oxide fuel cells. So besides the cost and the performance, it's really the lifetime. So right now there's degradation on the order of percent. They want to drop that down to 0.2% per 1,000 hours of operation. So if not resolved, we're in deep trouble. And I just want to point out that we started investigating the surface chemistry of these materials, and we discovered that we could actually control those rate of reactions by 1,000,000-fold in a very reversible fashion. And we could see which materials would act like poisons and decrease the performance, and which ones would act like enhancers. And really, after seeing that, we said, well, what if we have a poison device? Can we recover it? And that's really what I want to demonstrate here. In just a couple of minutes, we did it in a number of different ways. But perhaps most dramatically, you can see the rate at which the oxygen is taken up when you change the oxygen pressure in the gas phase. In a pristine material without this surface coverage. Then when we added certain poisons like chromium, this is accelerated poisoning because we put much more chromium in a liquid form than would come from the gas phase. And you can see rather than percent per 1,000 hours, we're getting a factor of 10 or 20. But most critically, what we showed was if we could go from what we call an acidic material like chrome to a basic material like calcium, not only could we fully recover the initial performance, but achieve performance which are much enhanced over that. So these are just illustrations of different electrochemical means. Most importantly, the fuel cell operation itself. You can see the initial operation had the order of 200 milliwatts per centimeter square. Not the best fuel cell in the world, but just to demonstrate the effect of these additives. That when we added the chrome, it dropped the power by 30%, which would be a killer in terms of a conventional device. But then we were able to recover it by the addition, for example, in this case, of the calcium. So really, what I perhaps should end off here is the fact that we were able to demonstrate with new insight and new chemistry, and of course we have physical models which explain what's going on here, is not only can we get enhanced performance by, in certain measures, by orders of magnitude, but extend the life of devices And by going to better performance, because we've modified the surface material, we don't have to use cobalt, which is a common element inside of these materials, but switch to iron like they've been doing in the battery case. So the impact, we hope, is to accelerate the ability to bring a wide range of technologies to market. And I think I'll stop at this point and just mention that I think that we have quite optimistic in terms of being able to view the opportunity for the hydrogen economy finally to be created and to see that translated into the mobility field.
Thanks a lot, because it was really addressing the key point to make the success of hydrogen. And thanks a lot. You know, I'm a big fan of what you are doing, so thanks for being here with us.
Sure.
I think we will be very short in question, and perhaps
we can take probably two.
Yeah, okay. They should be displayed. Okay. So, because there is the online. So, as H2 currently necessary for some industries, as cement, fertilizer, and potentially decarbonized steel, and as H2 production requires decarbonized electricity, will be enough H2 for the future of our transportation?
That's a great question. So right now there is the hydrogen available through these other sources. For example, for ammonia, and people are talking about even using ammonia as a carrier for hydrogen. But the question is, where will we have the most immediate impact in terms of cleaning up the system? And yes, there is a competition, but that's why the international organization, IRENA, was emphasizing the critical importance of accelerating and scaling up this electrolyzer technology.
Thanks. Next one. Olivier, you...
So why do you see interest of solid oxide for refueling stations? This technology needs fatal heat and makes sense for industrial applications like steel making.
No, that's a great question. So the interesting thing about these refueling stations for hydrogen is these vehicles can go long distances. So they don't necessarily have to be the most convenient locations, but somewhere along the highway. And there's a lot of locations now where there's plenty of excess heat. In combination with these solid oxide systems, we can make this whole process of hydrogen generation much more efficient. At the same time, they're not necessarily on the grid, so we can, create the electricity and store it as hydrogen fuel and use it when necessary, and as well as fuel up vehicles.
Okay. So may I ask Mark to ask the next questions? That is, you need a mic.
That's okay.
That's okay.
Voice usually. So my question is written up there, which is, where do you think we should be in 10 years in terms of efficiency for both electrolyzer and fuel cell? Where is the limit?
So I think the efficiencies are already quite high, and depending on the particular system, they can range anywhere from 60% to almost over 90%. And I think what's really attractive is now it's being demonstrated that even this full cycle between fuel cell and electrolyzer can reach well above 80%. So I think we're in a sweet spot, and I think that's not going to be the limitation.
Okay, next one. Perhaps I will select it myself. I don't know the answer at all. Is natural H2 a serious alternative? Could it change the usability in mobility?
White
hydrogen.
White hydrogen.
You think it will change something, or it's not just a chimera?
So I didn't quite understand. It's a power booster, but...
No. In fact, in terms of availability and of hydrogen for usage in mobility, for example.
Yeah, so as we said, it's essential, I think, for the long haul and for the large trucks and vehicles and things of this sort. And I think that's where its value is really going to come into play initially. But I think, as people become aware of the advantages, you'll see it populate to smaller vehicles as well.
Okay.
Yeah.
Thanks a lot again for your time.
Thank you.
Yeah.
So I know that perhaps you are starting to be hungry. It's the last session before the lunch. It will be a very active one because we will have 5 startup pitching on what they are doing. And before, Olivier, we have a special guest.
Of course. As John mentioned this morning in his introduction speech, entrepreneurs are one of the 5 key stakeholders in our innovation ecosystem. And in fact, they're probably one of the more important stakeholders in that ecosystem. At MIT, we have a number of organizations that support startups and entrepreneurs. There's a very strong entrepreneurial culture at MIT. And the Startup Exchange is one of those support network that entrepreneurs have access to. So with that said, I'm delighted to introduce the director of Startup Exchange, my colleague, Caterina Madeira.
Thank you, Olivier and Alexandre, for the kind introduction. Hi, everyone. I'm Caterina Madeira, the director of MIT Startup Exchange. I'm delighted to be here to present you our program and to kick off the Startup Lightning Talks. Startup Exchange is a program led by MIT Corporate Relations, which is home as well to the Industry Liaison Program, or ILP, as John mentioned earlier. The 2 programs are highly integrated. While ILP primary focus is to take large corporations to MIT and connect them with the institute resources, and this can be faculty, students, research projects, at Startup Exchange, my team starts by identifying and selecting MIT-connected startups, and together we connect both parties to help them explore some kind of collaborations or partnerships based on common interests and needs. Our mission at Startup Exchange is to support startups grow and expand to ultimately help them solve the world's great challenges. So the companies we onboard in our program, they have to comply with 2 main eligibility criteria. One of them is the connection to MIT, for which we call them MIT-connected startups. This connection might come through the founding team, the technology, or the affiliation to some of our peers across campus. I mean, other startup groups vet them and work with them. These startups can originate, from any part of MIT. There are over 60 courses related to entrepreneurship that generate many startups. They can come out from any of the 5 schools and 1 college, any of the centers, labs, programs, and even from collaborations MIT researchers have ongoing with known MIT organizations. And this is what, at the end, allows us to onboard startups in the program that virtually might be working in any sector. Today, we have a network of about 1,000 startups. And these, besides working, besides being sector agnostic, we are also location agnostic. Throughout the year, we onboard about 150 new startups in the program, which means that at the end, we always have the chance to introduce new startups to corporates throughout the year. And the other very important eligibility criteria for us is the stage of development. We typically start working with them when the startups reach pilot stage. I mean, when the startups are formally created, they have a team, which is not student-led, and they have a technology or a product that is ready to be tested or used in a real environment. This is when we start working with them. If they reach to us or when we find them they are in an earlier stage, we direct them to one of our peers on campus. And the beauty of being at MIT is that startup or entrepreneurship-wise, there are over 80 initiatives directed to entrepreneurs, from student clubs to competitions, accelerator programs, training, mentorship, and they all build upon one another. So when they reach Startup Exchange at the end of the curve, they are ready to engage with companies like Plastic Omnium or Group Week or others. So within this broad network of Startup Exchange, there's a group to which we call STEX25, to whom we provide customized support throughout 1 year. For a startup to join STEX25, first they must be referred to us by one of our peers. We interview them all, and we end up selecting the ones that have a combination of a solid team, a strong team, a solid technology, and a strong alignment with corporates. And throughout the year, we work with them. First, they are assigned to one of our team members, and we give them increased visibility and connections to industry. Now, when it comes to value, startups part of Startup Exchange are exposed to a global network of corporates and to its decision makers. And by corporates, I mean mostly ILP corporate members. While corporates that engage with our program, they have curated access to a network of MIT-connected startups vetted by my team. Everyone in our network can participate at events. At Corporate Relations, we organize over 30 conferences and webinars throughout the year. Conferences are still taking place on a hybrid mode and typically include startup lightning talks like today. And while some take place on campus, we do co-design and host events with members, like today, again. And this is one of the most valuable offers we have for both startups and corporates. For startups, because we bring them to the markets they are exploring, they are aiming to enter, and for corporates, because the events are co-designed to help them achieve their goals. Our team also launched calls for startups. These calls are based on corporates' priorities or internal challenges. The calls are featured in our website, and any startup from our network can then apply to it. Usually, a next step is our curated meetings, so we facilitate one-on-one meetings between the selected startups and the corporates, although these might be initiated by your request or the STEX 25 companies. And having said this, I'd like to highlight that our approach is highly customized and curated. I mean, at Startup Exchange, we support startups and corporates that are all different. They're different, they come from different sectors, they have different needs, and what sets us apart is that we don't provide a uniform response to their requests. And so we end up working with them in a myriad of different ways. Our program was created about 8 years ago. And since then, we helped ignite many successful collaborations. These slides features a very small sample of those, but it highlights the kind of collaborations we see taking shape more often, such as the joint development, manufacturing, demonstrations, and even acquisitions. And before passing the word to the entrepreneurs, I'd like to invite you to our upcoming events. At the end of October, we'll be back on campus for our annual Digital Technology and Strategy Conference. Then we're heading to Madrid for our healthcare conference. And mid-November, we'll be back at MIT for our flagship Research and Development conference. You're all very welcome to attend. And if you, by any chance, you can join us in person, you can always watch the live stream. And with that, I'd like to kick off the lightning talks. We've invited 5 startups, all of them with a very important mobility application. And I hope you have the chance to meet them all over lunch. Thank you.
Thank you, sir.
Thank you very much, Katerina. I must say, one thing I'm extremely impressed with all the startups in the Startup Exchange is the quality of the startups. And the 5 you're about to hear are no exception. We've been traveling with those guys for a few days now. I can tell you they're absolutely amazing people and persons, but they also work on technologies that's going to potentially revolutionize and really change the world. So with that said, I'm super excited to welcome on stage Peter Godard. He's the co-founder and CEO of Found Energy, and he's going to tell you what aluminum does with water.
Test. Perfect. Okay, thank you, Olivier. My name is Peter Godard. I'm the co-founder and CEO of Found Energy. Professor Tuller set me up perfectly with his talk. He was discussing the challenges of transporting hydrogen. And this is a really important problem because transporting energy, period, is a really important problem. The world relies on transporting energy in a variety of different ways. And I like to say that fuels are just as important to mobility as mobility is to fuels. We literally move 65 terawatt hours of energy as oil and gas every single day by boat. And that's to connect regions of the world to where you have these sources of energy that have pooled up over the years. Now, as we look to transitioning to renewables, we'll have to move a lot of that energy around as well. There's entire economic sectors and industries for whom renewable electrification is just not practical. And so how are we going to decarbonize those regions and industries as well? And in particular, this is a very challenging problem for a lot of heavy industry, in particular for decarbonizing heat. And for these industries right now, the lack of low carbon fuels that can actually compete with fossil fuels is really the bottleneck. So what we do at Found Energy is a little bit out of the box. We discovered how to turn aluminum into the world's first rechargeable fuel. And I'll explain what this is. So we take metallic aluminum, we get it to effectively rust, which many of you might know is an exothermic reaction. It generates heat. And we get it to do this really, really fast. And we get it to do this in a way that also produces hydrogen gas. That takes aluminum to aluminum oxide, which you can then use standard electrochemical techniques to actually recharge and turn back into that base metal. And this is really interesting for a lot of reasons. On a first principles basis, aluminum would be a great fuel. It's highly abundant. It's actually the most abundant metal in the Earth's crust. It's very energy dense. So similar to Professor Tuller's plot, I'm showing here energy density by volume versus energy density by mass. We see aluminum's way at the top. It's actually more energy dense by volume than diesel. And it's quite a bit more energy dense by both mass and volume compared to methanol and ammonia and some of these other fuels. What's great is we can produce hydrogen as well. Even if you don't care about the heat that we can produce hydrogen at an effective volumetric energy density that's 5 times greater than liquid hydrogen. Okay, so how do we do this? We take aluminum that has been treated with this catalyst that I discovered during my PhD at MIT. And once it's treated with this catalyst, that oxide layer on the surface that otherwise protects the aluminum breaks down and enables the aluminum to react very rapidly with water. And in this video here, which by the way is not sped up, this is in real time, you see a big chunk of aluminum that's literally disintegrating before your eyes, opening up a massive amount of surface area for this reaction to happen. And so therefore we can get power density that's actually comparable to fossil fuels. On Professor Tuller's plot, we would be up in that right-hand corner with those other conventional hydrocarbon fuels. We're using this technology to decarbonize a wide range of industries, from industrial heating to long-haul trucking to even maritime shipping. These are huge economic centers, but also huge carbon emitters as well. So we're getting started by actually closing a loop within the aluminum industry. We are taking low-grade aluminum waste that otherwise can't be recycled, and we're turning that into fuel that improves the efficiency across the aluminum industry. We're taking this low-grade waste, we're extracting the energy, and using that energy to decarbonize thermal processes within the aluminum oxide industry. We then are actually producing aluminum, smelter-grade aluminum oxide that can then offset about six tons of bauxite for every ton of scrap aluminum that you process. And we're doing this all while ensuring that these companies will not pay more for their energy costs. If you look at this waterfall diagram here, we can actually get the net energy costs for these aluminum oxide producers down to the cost of natural gas today, about $45 a megawatt hour in this region. So we are still an early stage company. We were founded a year ago. We've been growing very rapidly. We have a 10-person team, and we've scaled our technology about 100 times, and we're now producing power at the 20 to 30 kilowatt scale. We would love to find partners to pilot this technology or just even educate us on some of the problems that this technology might be able to solve. So I'll be outside after this, so please find me. I would love to chat, and that's time. Thank you. I'm back.
Yeah, you're back because we have 2 minutes of questions possible for you. So let's take the first one immediately. Okay, so you have the answer, not yet, for the European. Did you identify an European partner yet?
Yes, so likely our first pilots will be in Germany. Can't say that yet.
Like teasing. So how scalable is your solution, Peter?
So long term, because of the abundance of aluminum, it can scale to basically replace all fossil fuels.
Small ambition.
Yeah.
Olivier, last one for.
All right, last question. What are the help you need next? What do you need? What can this audience help you with?
So we would like to just understand how best to bring our technology to market and find partners to do that, and then also manufacturing partners to help build out the ecosystem required to use this new type of fuel.
Thank you.
Okay, great. Yes,
Thank you.
a lot. No
All right, we're gonna move forward. By the way, who in this room remembered that when you react aluminum with water, you get hydrogen at room temperature from chemistry? I didn't remember this. I know David did. Yeah, okay, good. We're gonna step now into a very different world, the world of super perception. And we're delighted to have with us the CTO and co-founder of Ubicept, Tristan Swedish.
Great, thank you very much. So Olivia said, I'm Tristan Swedish, CTO and co-founder at Ubicept. And today I'll be talking about our super perception for a world in motion. Now, things that move in the world are everywhere. I mean, we have planes, trains, automobiles. We're at a mobility conference. It's an incredible part of how the world works today, how we interact with it. And most of us can see the world. And there's a reason. Vision is incredibly important. It's important at a fundamental level. At Ubicept, our mission is to deliver computer vision, which recently has had incredible advancements in the last few years, to bring it everywhere. So today, computer vision works astoundingly well when you have a well-lit photo without any motion blur, the light's not too bright or not too dark. But in situations that are the most important, where we don't want humans to be, those conditions are not well suited to our computer vision. So we want to bring the power of computer vision to those environments. This is going to be helpful for active safety, quality inspection, automation, and industrial process control. And we have some active engagements in those spaces. We're founded by leading experts. We have MIT roots. And I'll talk a little bit about our brief history. So Ramesh and Andreas, about 10 years ago, a little over 10 years ago now, showed this really amazing result where they showed a pulse of light moving through a Coke bottle. So they had the insight that time is much different when you look at light moving through the world, that we're used to timescales that are much longer than that. And they use this technology to see around corners. So if you can see light in flight, you can see light as it bounces through a room and reconstruct views as it, you can basically turn a wall into a mirror. It's incredible. Andreas went to University of Wisconsin-Madison. He connected with some colleagues there. They used a time-based method of tagging light to be able to see and remove motion blur, and matured the seeing around corners technology so that we can do it in real time. So at the top there, that's myself. Sebastian, we came together and we asked the question. We were both finishing up I finished my PhD. Sebastian was closing his postdoc. And we asked, despite these incredible advancements, and we enable them to see machines at the limits of physics. And what our insight was, all of the techniques that I showed in that previous slide, seeing around corners, removing motion blur, it uses a technique which counts photons. So rather than a conventional camera which fills a capacitor and you measure the charge, we're actually forming images by counting photons. This allows us to have the best computer vision allowed by physics. We're capturing as much information as we can. And this leads to better safety, quality, and reliability. So we think of this as the next generation of vision sensors. But more importantly, it's not just the sensor, it's the vision perception stack itself. So by co-designing the sensing system, the sensor with computer vision, we'll have improved results. I'm going to just say that something that's unique about our technology is we can see things that are moving fast in low light and with high dynamic range at the same time. No other modality can do that today. And I'll show some videos to highlight that. So this is an example where we have a conventional camera on the left, and we have our camera on the right. And with a conventional camera pointing in the side of a car at night in a high dynamic range environment, you have motion blur and difficulty seeing things. By using our technique, by counting photons, You just get a fundamentally better image. In scenarios like manufacturing, particularly fine mechanical details, it's difficult to capture fine motion with a high-speed camera because you need lots of light. And light's a problem because it heats things up. So if you heat up metal, particularly different types of metal, it will completely screw up your measurements. On the left, we have a conventional approach which uses a flash. And on the right, we're using our approach. And I don't know if you can see it, but this spring on the right is moving slightly. And that's really important to understand that motion. Here's another example with a conventional camera. You have motion blur, and you also have dynamic range. And we're able to take these sensors and reconstruct a video in slow motion with this high dynamic range. Okay, so one last thing is everything I showed you was with just looking at ambient light, just turning these, using it like a camera, using our technology like a camera. If we turn the laser on, if we used an active source, kind of like a LiDAR, we can project a pattern in front of us and use that technology I alluded to before to see around corners, to be able to detect motion and basically turn our light into a way of seeing around corners in real time. So that's something I'm just going to allude to. Definitely come and talk to me after this. Would love to talk about pilots, joint development. We have an evaluation kit where you can collect data today and evaluate your use case. Thank you.
Thanks. So let's have also a few questions to you. I hope they will be displayed. Yeah. In which intelligent transport organization are you active for the crossroad application? Do you know the French VDECOM? So I'm looking to Steve, I'm sure.
I would love to learn more. So we're talking to people across the mobility transportation space. There's really two areas where we can help. The first area is looking towards making more robust vision for operations, autonomy, moving towards autonomy, and so on. The second thing in the more near term is inspection. So looking at the quality of the infrastructure, being able to see infrastructure moving faster through the environment, and in the case of automotive, infrastructure for manufacturing.
Okay, thanks.
One more question. What do you think, or do you have existing pilot installation in factory end of line?
So this is an area where we've been doing tests and collecting data, but again, I would be excited to talk to people who have particular ideas. We started 2 years ago, and our evaluation kit was available as of 6 months ago. So we're getting to the point where if you have a particular idea, we're ready to help you.
Thank you, Tristan.
Thanks.
All right, third on stage, we're going to move from super perception to what we call intelligent and functional biomaterials. And we're super excited to have Verge Can with us. Welcome, Verge.
Hi, my name is Verge Khan, and I'm the CEO of Primitives Biodesign. We're a materials company that's based in Silicon Valley, California. I'm also an alumni of the MIT Media Lab, where I did my graduate research on stimuli-responsive biomaterials for industrial design applications. At Primitives, we produce biomineral additives and engineered materials made from sea urchins. That's right, you heard it, sea urchins. In order to address two key environmental problems, kelp conservation and waste reduction. Because of climate change, the oceans are warming. This has led to the emergence of the wasting disease, which has killed off major predators of sea urchins. As a result, these sea urchins have proliferated, and they're destroying kelp forests all over the world, including the coast of California and European coasts from France to Spain and Norway. I'm a scientific scuba diver, and I collect data underwater. If you were to come scuba diving with me in a vibrant, healthy kelp forest, what we would see together is this: an abundance of fish, wildlife, and macroalgae of all kinds. But unfortunately, what we're more commonly seeing today everywhere are these sea urchin barrens. That's because kelp are the forests of the sea. So with the forest gone, the fish and wildlife are also gone. Kelp also play a central role in mitigating climate change because they sequester carbon from the atmosphere, converting CO2 to biomass. We've been working with global environmental nonprofits like the Nature Conservancy and regional communities of urchin divers to remove these destructive urchins so we can restore the kelp forest. This is viable because kelp is actually one of the fastest growing crops in the world. So by removing the urchins, this allows for rapid reforestation of the kelp and the marine biodiversity. We make biomineral additives using these sea urchins, but beyond that, we're also reducing commercial waste. Sea urchin waste is actually an abundant, untapped feedstock in the seafood industry, so we're not gonna run out. We use these biomineral additives and we're leveraging sea urchins as a biofactory to grow a rich library of compounds, pigments, and minerals like calcium carbonates for use as additives in paint, coatings, building materials, and plastics. This approach also requires less energy than traditional mining operations. At Primitives, we have expertise in chemical engineering, polymer science, digital fabrication, industrial design, and materials engineering. So that means we can also develop custom formulated materials and products. So this is what you see here is a suite of materials that we develop using a zero waste approach. By taking the waste product of one material for use as another, enabling us to produce 4 distinct products. We've isolated and stabilized a unique class of pigments called spinochromes, giving us 3 different colors. We've produced 3D printing filaments using these sea urchins that's printable using standard 1.75 millimeter nozzles. Our additives can be incorporated into flexible film plastics to enhance their processability, mechanical, and moisture barrier properties. Our additives can be incorporated also into engineered stone and composites. And in this example, we can achieve comparable tensile properties as natural marble, and they're fluorescent under UV light. So if you're a potential partner that's interested in what sea urchins have to offer in this vast array of pigments, compounds, and minerals, I'd like to invite you to collaborate with us and explore how these additives and engineered materials can enhance your product's performance and environmental impact. And when you're working with us, you're also working close to the source, not just to replace an existing ingredient or create a new material, but also to take part in sequestering carbon, enhancing biodiversity, and also reducing waste. So I hope you'll join me on our journey to reshape the material landscape of our modern economy and to build a future that we actually really want to live in. Thank you.
So thanks. So the questions are appearing. Yeah, perhaps which kind of polymers can you do? We have a high interest in polymer.
Yes, so great question. So thus far, we've explored a variety of different thermal sets, and we're looking for actually partners to support and research and development into thermoplastics as well. So using thermosets, we have demonstrated that we have comparable properties as these engineered stones. So that's not diminishing. And also we can work with companies to fine-tune their particle size, purity, and morphology to achieve their target applications.
Thanks.
How big is your team at Primitives?
So the size of our team, we have 7 people. Right now, we're an early stage startup, so we're seed stage.
Okay. I see one question. Okay, yes. What do you need from VC, venture capital?
Patient capital. Because one of the challenges, I think, of working on large-scale environmental problems is you don't want to create a situation where your product relies on an environmental issue to exist. So with that, you need to, which is why we're working with conservationists and environmental nonprofits to collect data as we're undergoing. So, yeah. As well as also support, I think, VCs into specific markets that I think would be able to be compatible over the scale, like gradually scale throughout that lifetime.
Okay, thanks. You are very convincing. So.
Thank you.
Thank you. I hope you see a common denominator from all those wonderful speakers is the passion they have for what they do. And the next speaker is no exception. We're delighted to welcome on stage the CEO and co-founder of LunaWave, and he's going to talk to us about cutting-edge antennas and ADAS sensors. John Chin.
Good afternoon. you guys hear me okay? Yeah, okay. So my name is John Shin, and I am co-founder, CEO at Loonwave. So we are founded in 2017. We're a radar-based machine sensing company that's really currently backed by about 12 institutional VCs and 4 strategics, including the likes of BMW I Ventures. My CTO co-founder got his PhD in 2000 in applied physics in MIT. I myself came out of Carnegie Mellon, but I did spend the summer at MIT's Media Lab. In addition to our incredible, talented team, we were very fortunate over the last few years to welcome some top executives from, especially from automotive. A couple of years ago, we were able to welcome Mr. Peter Schwarzenbauer, who spent many years on the board of management at Volkswagen, as well as BMW. So at the heart of our sensor solution is a patented process to not only design, but also fabricate what's called a Lumberg lens antenna. And for many, many years, it's been considered the holy grail in the radar community. And that's really part of the hardware secret sauce, if you will. So a little bit about the problem we're trying to solve. So as you guys know, all the automakers focusing a lot on ADAS and with a roadmap towards self-driving cars. Of course, the different sensor modality. The challenge is no system that really addresses the needs of performance, reliability, and cost efficiency. Now, radar has been utilized for quite a bit of time, but 2 problems. One, what we call poor angular resolution. So simple analogy, my eyesight is really bad. So if I take out my contact lens and I get behind the vehicle, that's today's radar. Second, perhaps more importantly, it's what we in the industry call tunnel vision. So if you go to all the tier 1 suppliers, great companies, but the traditional technology, and also pretty much all the startups, if you look at their data sheet, they'll tell you, their front-facing radar can detect, let's say, 90 degrees, 120 degrees field of view, right, coverage. The reality is everybody is using what's called a planar phased array. And what that really creates is right in front of the radar, 15, 20 degrees, you get the distance detection, whether it's 300 meters, 200 meters, and the resolution the data sheet claims. As soon as you move outside that 15, 20 degrees, distance detection and resolution gets significantly worse. So how does that impact automakers? So the OEMs essentially have to install at least 5, 6, sometimes up to 9 for lower level of ADAS systems. And if you talk about L4, L5, forget about it. We're talking about a dozen or more to make L4, L5 a reality. So this is where we come in. So with our Lumberg lens antenna, feel free to pass it around. If you can find me afterwards, I'd like to get them back. These are mock-ups, so if you really need to keep it, that's fine. But combining with the antenna technology plus the proprietary algorithms, we basically enables every single vehicle on the road, longer distance, better resolution, most importantly, that uniform performance across 360 degrees. That's extremely important in obviously from a safety standpoint, from a self-driving car standpoint, from a cost standpoint, from a simplicity of vehicle integration standpoint, you name it. So quite a few benefits. So since 2018-19 timeframe, we developed 4 different generations of radar. Our maturity right now is B sample in the high imaging radar space. Like I said, learned quite a bit, tremendous amount from OEMs and other partners, both in the passenger vehicle, commercial trucking, agriculture, construction, mining vehicles. As of late last year, we won 2 RFQs. One with a premium German OEM. The other one is one of the largest OEM that's based in US. One is focusing on L3. The other one is focusing on next generation of ADAS. From a partnership standpoint, I do want to thank all of you for taking the time and for the invitation by Plastic Omnium. I don't take this for granted. I did spend quite a bit of time in my career, management consultant, then corporate Fortune 100 company doing innovation investment. It takes a village, as they say, to really make the technology a reality. I am not naive. We're very bullish about what our technology can do, but we understand our limitations. No amount of money that I can raise is going to help me to truly commercialize a radar technology in the automotive space. So I think we have the knowledge from the OEMs, and we're really in the very thorough process of identifying the right tier 1 suppliers to really work with us, continue to work with us to progress the technology. And, you know, again, speaking on Plastic Omnium specifically, I'm quite excited because on the bumper area, on the vehicle surface area, that's a tremendous opportunity to really deliver innovative, sensor solutions. And again, I had the opportunity to speak with some of the engineers already for 4th or 5th times already. So we're excited. I think we're talking about in the next 2 to 3 weeks to come back to have some brainstorm sessions as well. So thank you again for your time, and have a good day.
I think you have time for two minutes question if you want.
Of course.
So don't give us all the secret, yes. First question is this technology affected by dirt, dust, ice? What are the limitations in terms of?
Yeah, I mean, obviously, if you, I think radar in general, because the physics, longer wavelengths, you function much better than other sensor modalities. But that's just radar, so we're no different. So millimeter wave radar, so whatever this car's already using on the road, that's what we do. So we just do it better.
Would your system be affordable to get more safety stars on entry-level cars?
100%. I think when we first started to think about the application of the Lumberg lens antenna, theoretically, you're like, let's do 360 degrees. Robotaxi, the reality is that will come, but it's a bit a ways from a mass production standpoint. So the mandate for this technology is to be able to have comparable BOM at a unit level as the other tier 1 suppliers, but to deliver better results. That's what we do. So the B sample that we have delivered used basically 4 chipset, that production-ready chipset that other tier 1 suppliers are using, and delivering better results. So BOM-wise, cost, yeah.
Okay, perhaps the last one, if you want, any military application and future regulation constraints?
Yeah, one thing I noticed application-wise, obviously in this space is more applicable on the automotive, but if you think about using radar technology to be able to see the world around you, whether that's passenger vehicle, taxi, trucking, drones, robotics, tanks, whatever the case may be, certainly has the application. From a regulation standpoint, there's really, we face the similar situation as your traditional automotive radar, so there's nothing special. So,
okay.
Thank you.
Thanks.
All right, so our last speaker before we head off for a wonderful lunch is going to tell us about tactile intelligence, and we're absolutely delighted to have Patrick Stack with us, Principal Software Engineer at GelSight.
Hi, I'm Patrick Stack. I'm Principal Software Engineer at GelSight. I have over 25 years experience creating surface metrology applications. I'm also a former member of the ASME B46 Standards Committee on the classification of surface texture. The GelSight technology was invented at MIT by Professor Ted Adelson as a novel method for digitizing touch. The world has created sensor technology to mimic human sight and human hearing, but until recently, not human touch. Well, GelSight has done just that. It has created a tactile sensor that mimics the sense of human touch. The sensor itself is a soft elastomer covered with a thin layer of reflective paint. When it touches an object, The reflective paint closely conforms to the shape of that object. This sensor, combined with a digital camera and computer vision algorithms, can be used to create a 3D model or height map of the surface. I believe the easiest way to explain our technology is to simply show you how it works. You can see here I'm pressing my finger against the sensor. It's very fast. It responds quite quickly. Now I'm going to take a scan of a coin just to show you the details that we can measure. Draw what we call a ruler on the interface to measure the distance between 2 points. And as quickly as that, I can measure an object. So what can you do with this sensor? Over the past decade or so, there have been tremendous advancements in AI with computer vision, but vision alone is not capable of providing a full understanding of the physical world. Combining the power of AI with the technology of GelSight is leading to solutions for a wide range of applications. Here is a sample application where we have created an AI model by training the system how to recognize sandpaper of various grades. About 100 scans of each grade of sandpaper were taken with the GelSight system to train the AI model. Once the model is created, a user that can simply scan any sandpaper sample and the system can recognize it. I'd also like to point out that the AI model can be created by the end user of the software, not necessarily a GelSight employee. You can see here that the software indicates the sandpaper grade along with a confidence score. Obviously, this is just one example of how we can replace computer vision with tactile touch AI. As you can see here, we already have a wide range of products. We have our small, lower resolution sensor, the GelSight Mini, that is commonly mounted on the robot to simulate human touch. Our flagship product, which I have here today, is the GelSight Mobile. And our most recent product is the GelSight Max. The GelSight Max is the highest resolution sensor of our product line and is ideal for measuring surface roughness. In fact, it can measure a RA value down to about 0.2 of a micron. GelSight systems are fast, mobile, and versatile. And by versatile, I mean a few things. For one, the sensor is surface agnostic. And by that, I mean the sensor works equally well on many types of surfaces, including dull or reflective surfaces. Reflective surfaces are often quite difficult for optical systems to measure. Surfaces such as glass, reflective metals, and black paint can all easily be measured with the GelSight system. And two, the system is not dependent on the environment or the ambient lighting. The only lighting needed takes place within the sensor itself. These benefits provide the ability to take a measurement on the factory floor, and this can save hours and sometimes even days compared to conventional inspection methods. We are looking for partners with companies that can benefit from our Tactile Intelligence platform. These may be companies in the aerospace, automotive, manufacturing, robotics, and many other industries. We're always interested in new applications and especially the quality control of surfaces where the sense of human touch is critical. Thank you.
We have some question to you. Yeah. Just waiting. That's the pop up. So can you detect one skin effect on painted parts? I think it's specifically for our bumpers and others.
That's a very good question. I am not sure. I've heard of the effect on painted parts, but I really don't know the answer to that question. But I could find out for you.
It sounds like a good test that you need to do with your system. So next question, what's your next development and more miniaturization?
Well, our most recent development actually is to build a bigger sensor that has higher resolution. It's not much bigger in form factor, but just a little bit, and it can measure down to 2 microns in X and Y, and it's sub-micron resolution in the Z-axis. We also do have a small form factor sensor in development as well.
Okay, and last one, any work with robotics company to have unmanned control?
That's a good question. That's the part of the company that I'm not very involved with. I do the surface metrology part of the company, the software. The robotics, if you want to get in contact with me after the talk, I will put you in touch with the person that can answer that question.
Thank you, Patrick.
Yes, thanks a lot.
Thank you very much.
So now it's time for lunch. So we start at 2:15. I think we have a small margin of improvement compared to the previous break. So 2:15, we start again the session. Thanks a lot.
bon là.
Welcome again for this afternoon session. So I hope you enjoy again the discussion and the food at noon. So now we will start with new technology and the emergence of new technology. And I will have nothing to do because we have a specific host for this session. The host is Philippe Devost. Philippe Devost, since co-founding Wanadu, the European #1 internet service provider, Philippe has been successfully launching consumer services, software startup, publicly funded ecosystem, and corporate transformation program. And recently, it was also working for the next generation as a CEO of EPITA, which is one of the famous French school for computer science and software engineering. So, senior advisor for executive and VC funds. He published recently a book, and I see one exemplar on his desk. So, Philippe, welcome.
Thank you. Thank you, Alexandre. Good afternoon, everybody. Who got coffee? Raise your hand. Who got enough coffee? Okay, so the challenge is very, very big. So we have, you had this morning extremely interesting lectures and demos and discussions with startups. Now we will dive into conversation mode, looking again at this very profound change that is happening in the mobility sector. And that is, in a way, reshuffling and blurring lines between what we thought was a model with given roles. Now everybody is trying to do everybody else's business. And there are also newcomers who had nothing to do with the industry, who are now erupting and changing the rules. So before gathering the best players and the best testimonies in the field in this conversation, we figured that it would be interesting for you to have a lecture from Professor John Carrière. John Carrière asked me to spell his last name exactly this way. He has an extensive experience in systems dynamics, and for those of you who would still be prone to go sleeping, you will miss, if you sleep, you will miss a unique moment that would help you change your perception of how beer should be moving. So please welcome John Carrière.
Thank you, everyone, and good afternoon. And a very short bio on me. I was born in the New World in a small French outpost by the name of Detroit, Michigan. I'm a chemical engineer, and I came to MIT I focused on control systems. And when I first came to MIT, I started working on expert systems, as Patty Mays discussed earlier, for control systems. I said, I'll never graduate if I do this, so I went and did classical control work, which we're going to discuss a little bit today. And what I really focus on is helping organizations. First, I started with teams, then organizations, and now supply chains, help make faster decisions better. Make better, fast decisions, and then make course corrections as needed. That's really what my focus is. And I did discover a little research. My forebear, Pierre-Jean Carrière, came over from France in 1687 as part of Louis XIV's military. And it turns out we have a family crest. So since September, I have been following amour, labeur, ingeniosity. And so far, it's working great. So I want to first talk about the power of a framework. So I'm actually going to use Pablo Picasso as an example. I'm an American. We have a lot of world and European art experts here, so you test my knowledge. So this is obviously a picture of bulls, right? And it took me really many years to understand why this is such important. Is as you're all looking at these bulls, you're all picking out your favorite one, right? Is that what's going on there, right? And the reason that's important is if I showed one specific bull, some people would like that bull, and some would say, well, that's not the bull we had on our family farm, or I'd like a different one. And what this picture really says is if you get to a level or framework or abstraction, you can simply show the abstraction, and everyone will join that framework. So what we're going to do today is we're going to talk about a very fundamental framework around decision making that you can take and apply no matter what part of the supply chain you're in. And actually, a lot of that work was done at MIT, so we'll touch on that too. Back to the control systems is, I'd love to first start out with Pierre-Simon Laplace and Napoleon. They're French, I understand. I did not speak to them myself, but from what I understand in the studies is, does anyone know the relationship between Napoleon and Laplace? Pierre-Simon Laplace was Napoleon's instructor in artillery. Okay, and if you think what artillery was all about in the 17th century was I'm trying to launch a projectile and pick the exact initial condition that would lead to a perfect result, right? And you know how difficult that is because you have all the changes once your decision has been made. And Napoleon, he was actually quite the opposite. He was an expert in actually realizing the situation that was going on and making rapid decisions to make improvements. And also in terms of mobility, it turns out his carriage was actually fitted out with maps and all other information inside, so he was traveling back and forth from battlefield to battlefield. He was getting the best information. So I hope your mobility system works as well as his did. And the one thing I would also like to raise the point here is we're all familiar with Laplace's demon. He was really focused on, I want to pick the perfect initial conditions before we get started. So then I can get the perfect result. And Napoleon actually hired him as the Secretary of the Interior. And he fired him 6 weeks later. And he fired him because he said, Laplace, all he did was kept playing with the initial conditions and he never got started, right? So what this is really all about is it's not only do we have to get the best information we can, but we have to start quickly and take action. And finally, Leonhard Euler. The reason why Leonhard Euler is there is because of iteration. So how many of you heard of the whole concept of pivoting your startup, the Eric Ries work? It was originally done by Euler. Okay, it's 200 plus years old. He did what was called backwards integration. All it means is when you get started on something, you take your best knowledge and you pick the slope you're headed on, and you actually stop and check to see if during time that you're deviating. And you make a course correction. And that backward integration is actually the initiation really of negative feedback into our thinking, into management operations. And that is still playing out today, even if you think about neural nets and concepts of backpropagation. These concepts are still fundamental and being used today. And to the MIT connection, now Edward Lorenz, I did actually meet and speak with. He was the one who really developed and coined the term the butterfly effect. And essentially, he was trying to solve some differential equations to predict the weather. And he realized no matter how good you got the initial conditions, after about 4 or 5 days, it always decayed, right? And that was because tiny differences in your starting position over time leads to massively different results. And so this actually provides us with an opportunity, because if we actually knew where those sensitive points are as we're making business decisions, we could actually intervene at those points. And I think that's where startups are very important, because it's not only the new technology the startup develops, they have to actually join into the company at the right set of conditions so that the organization can incorporate and benefit from those technologies. And now into the 20th century, this goes to Henry Ford, and this is from his biography, My Life and Work. And I just wanted to show you this key realization he had during his journey, was in a 1905 car race, there was a crash, and Henry Ford picked up a small part from the French car, and it was a valve stem, and it was very light. He's like, wow, this is very light. And what is it? And it was vanadium steel. And he essentially incorporated vanadium steel into the Model T, which was really important in the development of the moving assembly line. And he also made the statement that the auto industry should be about making cars lighter. This is back in 1905. Anyone who's seen an American car in 1970s, we did not get the message. But this message about making things lighter and faster goes back to Napoleon's army, it goes to Henry Ford, and it's still being carried out today. And that's actually, when you look at plastics, Omnium, its founder was based on the same concept in 1947. He found 47 ways to put plastics into cars to make them lighter and more efficient. Okay, so when you start to think about lighter and faster, this actually extends to other regimes and regions. And I'm going to take you to 1953, which is during the Korean conflict when jet aircraft were first being used. And essentially, Colonel John Boyd studied what determined the success of a jet aircraft in a conflict. And he basically came up with the concept is you can look at all the different individual parameters of how jet aircrafts perform. Horsepower, turning radius, ordnance, range. But what really matters is the overall time it takes for the pilot to make a decision and take an action. And he broke that down into 4 steps. So that time frame, which is by Tau S, it's broken down. First, make an observation. Second, once you get that observation, orient it to your current condition. Does this make sense? Is this where we need to go? Put a frame of reference. Then make a decision. We're going to take an action. And then finally, we take an action. And I would say most organizations and companies I work with jump directly to D or A, and we don't spend enough time making that early observation. And I think it's quite uncanny that many of the startups we saw today were around getting a better, faster observation. If you do that, your next 3 steps will speed up and become very accurate, and then you will serve your customer better than your competitors. And directly applied to business, this is Jack Welch. He made the observation that if the rate of change of the external environment exceeds the rate of change in your organization, the end of that organization is near. And that's why when you go to purchase new technologies, work with partners in your supply chain, you should always be focusing on reducing the time it takes you from start to finish so that you can deliver to your customer, again, faster than your competitors. So I want to take this and extend it to the concept of vertical integration. And when we think about vertical integration, the classic is the Henry Ford and the Highland Park plant where they built the Model Ts. Does anyone know what color the Model Ts were offered in, Henry Ford? Yes, any color you want as long as it's black. And does anyone know why he chose black? It's definitely cheap, right? And second is it would dry twice as fast as the other colors. So so what Henry Ford did very successfully, and this is basically his learning curve, is he was able to drive down the cost by a factor of 5 after making several million vehicles. And that was very successful until customers no longer wanted Model Ts. So Henry Ford was the master of process design. On the right is his son, Edsel Ford. He was the master of product design. And you'll see that is Edsel Ford standing with his father, standing next to the Model A, which he designed, right? So Edsel Ford was a designer, and this Model A saved the Ford Motor Company. In fact, at this point in the curve, the organization closed for 9 months to retool to go from process to product design. And now we're on to the Alfred P. Sloan, which is the name of the school I'm at. And he approached this whole verticalization, centralization, decentralization question a little bit differently when he designed the General Motors organization. This is called the M form of the organization. Has anyone seen this graph before? he essentially drew it in half a day. And this graph basically set the design of organizations for the 20th century. And the key part of it is he separated the control function of the organization, finance, HR, and the higher administrations from the parts that actually dealt with the market, which are the car companies, Chevrolet, Buick, and Oldsmobile. And he played a very important role by maintaining the dynamics between the corporate center, which actually controls costs and the sustainability of the institution, and the branches, which made sure that they understood what the customers need and worked quickly. And by the way, the reason why Alfred P. Sloan actually was able to overcome Henry Ford was because they figured out how to make faster drying paints in different colors. Does anyone know what company helped them do that? The DuPont company, right? So there's another French tie here. So again, partnerships where you might not expect actually help drive the basically the 20th and into the 21st century. Now I'd like to step into the key framework here. Jay Forrester was a professor at the MIT Sloan School, as well as a professor of the electrical engineering department. And after he invented magnetic core memory, which made more money for MIT than any other patent since, he decided to come over to the business school because he said all the important work in computers is done. This is 1955, okay? And so he actually was approached by a General Electric, some people from their manufacturers of refrigerators, stoves, and washers and dryers, and they had a problem. The problem was they're running a factory in Kentucky, and they learned that, even though demand for white goods is pretty smooth, right? It shouldn't be very seasonal. It shouldn't change too much. Some months, they'd be running 3 shifts, and other months, they barely had enough demand for 1 shift, right? And so Jay said, okay, how can I help you? When would you like? He said, we're coming up next week. So what Jay did was develop basically a very simple simulation of a supply chain on a picnic table, roughly in 1958, which every business school plays today. And he came up with this amazing fact, is when you start out with a system and you're at the retailer end and you're looking at customer demand, if you have small fluctuations as represented here, what starts to happen as we go back into the supply chain? Now remember, we're adding time delays, right? So every time you add a time delay, you actually incorporate this phenomenon that it will also start to oscillate. So what starts to happen in supply chains is as you move backwards through the supply chain and you get longer and longer time delays, you start to get massive oscillations at the factory, right, or at the production level, and it's not represented at the demand. And that creates incredible losses in costs, wasted materials, and frustration for everyone in that supply chain, which many of us experienced during COVID. So one thing I would like to provide how technology can help you, you can never get out of the beer game. But what you can do is reduce the amount of oscillations your chain has by shortening those time delays. So there are many ways to do that, but what one key focus is new technology, particularly Industry 4.0 and information, can help us shorten those time delays if we use it correctly. Okay, and I do want to say that's a 60-year-old example. I want to actually move that forward today. This is a real example I actually worked on, and this is Dutch beer, if we have a Dutch contingency here. And let me tell you the problem they had is their Mexico brewery was capacity constrained. They and were looking to invest $20 million in new bottling lines. And when I actually work at a factory, we have a phenomenon that's called hidden factories. And it means that 30% of what's going on in any system, nobody actually knows what it is. And that actually produces slow products at low quality and keeps people waiting. And very shortly, the way we were able to help them with this is we said, why is it waiting? Well, it was actually waiting for information. And I heard, we heard the fact earlier that electrons move with the speed of light. They've never been to our accounting department, right? I can tell you that. And so we're able to reduce the waiting time from 6 hours to 15 minutes primarily by moving some handwritten spreadsheets online, right? Of course, when it was pitched to the higher level of the organization, it was called AI, right? But really, it was actually shortening the speed of those electrons. And then finally, this actually produced 1 million cases of beer per month during their top 4 months of production. So it's quite a success story. But that's how much leverage shortening time can produce in your supply chain with already well-established technology that you can implement quickly and cheaply. I'd like to just wrap it up quickly on today, because if you read the paper over the next week or two, you will find examples of exactly what I'm talking about. So I'd like to show you through that exercise. This is in the bottling. So I'm going to talk about soda bottling, so think of the major soda producers. And what they tend to do is they own the syrup and they own the marketing. So if you think about those major companies, that's what they're half syrup producers and they're half marketers. That's what they do. Unfortunately, you have to bottle it and ship it to sell it. So why don't we get somebody else to do it? Because it's capital intensive, low margin, and they're price takers. So what we're going to do, Wall Street will love us to split it apart. So we'll split it apart, we'll realize all this value, then we'll let these independent bottlers run it. We'll squeeze their margins, they'll stop maintaining it, it'll fall apart, and then we'll go back and buy it at low price, and then we'll repeat this cycle again. If you don't believe that, I was able to pull that straight from one of the New York Times of how the Coke and Pepsi and all the major bottlers or major soda producers play this dynamic game with their supply chains. Another, and this a little bit just interesting example, this was last week. So Boeing, major aircraft maker, they have a supplier in their supply chain, Spirit, who makes the fuselages. And again, capital intensive, low margin, and they're also a price taker. So what's unfortunate is Boeing is going to actually not be able to produce enough planes for its next quarter, which has got Wall Street's attention. And here's some of the reasons why. In April 2023, improperly installed parts. And then in August, at their supply chain partner, improperly located holes drilled in the fuselage. I'm not an aeronautical engineer, but that's probably not good. So all of this rework was created by not really understanding the right level of cooperation and pressure that you should put on your partners in the supply chain, and that's completely avoidable. And like I said, I took this from the paper last week. This is not a new phenomenon. This is a cartoon from 1941. Have anyone heard the phrase, back to the old drawing board? Well, here's where it comes from, the original source. And it's basically showing that it's clearly someone testing a new aircraft, and the happiest person is the designer, because they're going to get paid to redesign it. So what that means is you must be very careful as you align reward structures within your supply chain. It hasn't changed in 100 years, and it will still be the same in 100 years. So as you think about your framework and degrees of verticalization, I think companies have to make their own decisions on how much to verticalize. I also think it's dynamic. And you'll have to determine your own principles to maintain your own culture, your respect for your customer, your reason for existing. But ultimately, I would think about a few things. Is you want to keep that time frame between when the customer wants something to when they get something delivered very short, while at the same time making sure that you don't allow others to get in front of your customer, right? That relationship is extremely important. And also, if you start adding different parts of the supply chain, how does that affect your organization's learning, and how does it affect those cultures? So not only taking the short-term thoughts of cost and speed, but also those longer-term timescales on customer relationships and learning is critical as you think through this process. And I would just like to end with Donella Meadows. Remember, we had the opportunity to look at Edward Lorenz's work, who did the butterfly effect, and he said systems can be very sensitive at certain points to setting initial conditions. Donella Meadows was a researcher at MIT. She worked for Jay Forrester. She actually came up with a list of 12 key points of where you should intervene so that you can produce the maximum result. of change in an organization and achieve the best results. And I just wanted to point out a few here, and we will share these slides with you. I would actually cut this out and put this next to your desk for the next week or two and think about it. It's so profound. But ultimately, think about the lengths of delays in your system and the slow negative feedback loops, that if we could speed those up, we could go back to that world of Euler where we're making fast decisions quickly and correcting for the best result dynamically. And then finally, I'd like to end with number 2 is ultimately what determines the state of our supply chain is our mindset. And if we don't have the right framework and we're not thinking correctly about what's right for our supply chain, not only our organization and our partners, we're not going to, in the long term, we're not going to end up where we need to get. So those are really 12 key points that I wanted to share with you on how you can make, with small changes, make major impacts on large organizations. And although there's a lot of new exciting technology, these traditional concepts still hold, and combining those two is going to produce a much more powerful result than you could get on their own. Thank you.
Thank you very much, John. They are all awake. That was both inspiring and enlightening and dynamic. So now with no delay, I would like to welcome on stage the participants of our panel. So Félicie and her team, her teammates, come on. So in order to keep things dynamic, I will ask each of you to introduce himself or herself when you answer the first question.
We need another seat, I think.
So,
it's
just spicy. I'll be staying.
It's okay.
I'll be staying. Have a seat. Okay. So as you've understood, this mega trend that we all observe across the sector is revolving around vertical integration, hence the name for this panel. And it's a lever to displace the value chain and to try to speak to others' customers, which is also a challenge. And what's interesting in this mobility world is that this vertical integration goes far beyond software and is now involving atoms. It's involving the physical world. We've seen this morning that the physical world and the IT world are blending through the MIT lectures we got. And the immaterial and material worlds, in a way, are starting to blend. And what this raises is the question of value control. Let's use the right words. We are not here to talk about how great the world is and how great our companies are. Your challenges to each of you is to keep a tight grip on value control. Right. Am I wrong? No.
Absolutely not.
So we will just talk about real things across this discussion. And I would add, because this is what we discussed with Félicie while preparing the panel, that this challenge for value control is moving to the edge and to the very edge of the physical envelope of the vehicle and of every physical system. And so this is why we will articulate between the verticalization and edge. I do thank the speakers to have accepted to have a quick, bouncing and vivid conversation with very short answers. And with no delay, I would like to ask you, Félicie, as Managing Director of Plastic Omnium, you mentioned during our preparation round that how important you viewed vertical integration as a challenge and as a crucial strategic challenge for you as a Tier 1 supplier to a whole industry. Could you give us an example, and could you explain to us why this is such a challenge for you?
Sure. Thanks for the question. I mean, we mentioned several times, quickly this morning, we made a reference to a company not so cold anymore, so small anymore, which is called Tesla, who in our industry clearly has taken a very disruptive approach to verticalization. It happens before, but it was really the first one to really take this path. And I think as an industry, first of all, not so many players were believing it could actually happen. And this is part of the reason probably why they also went that way. It's because they had to went alone. But as the time has passed, they clearly built up a great differentiation from that. So really making vertical integration, so both forward, so which is with the distribution, garages, and the sales, but also backwards, so producing some of their own components and also revisiting the way they were assembling cars. So that slowly but surely has clearly changed the way the whole dynamic and the whole industry is structured. We came from a really well siloed, structured industry to something where still people, some of the players who are still finding our way and how to deal with that and how to be the one capturing the value and not having it taking away from us. And actually today, I think our teams, there's not a single customer meetings where none of them are asking us, how do we benchmark versus Tesla? How can you help us to improve, to bridge the gap? Obviously, they all have their legacy infrastructures and organization, but how can we improve and be a partner in getting there? We see that also as, I would say, went a bit even further because of the scarcity of some material and also from the disruptions that we have in the supply chain. We have seen some OEMs like Volkswagen, GM investing in mining to secure some of the material, but also some OEMs like Volkswagen creating their own software house, or I would say even people like BMW investing in their own microchips capacity. So this is changing a lot, and obviously we have engaged in the same way in some vertical integration and we want to accelerate over time. So the decision that we have taken, we have created our OptenSoft activity also, so really to build and be in a position to provide some the software layer to our hardware components, again capturing some of the value, but also using that as a way to engage closer to the Omnium. You were saying you want to be close to be the one closest to your customer. It's a way for us to do that. We have also invested in lighting. So we have a brand new lighting activity, which first it's to benefit from the growth on this specific market, because lighting is taking more and more space in the car, but also because now we are in a position to really to master and design. If you take the envelope of the car, if you take the front or the rear, we are capable of providing a full integrated solution for the front and the rear of the car. And that, again, we want to use that as a way to benchmark and to differentiate ourselves from the company. And we have also taken some other stance, like having some partnerships with Verkor for battery access to battery cell, or with Total Energy to think with the other players outside our market on how to develop recycled materials in that instance.
Wow, thank you. What's interesting is that, I mean, that gives you a better view of how a Tier 1 supplier is just not a Tier 1 supplier, but expanding and extending beyond its original spot in the value chain. You're not alone, actually. You're not alone in. There are other industries where vertical integration has played a strong role, and you're not alone. Also, I like the parallel you made with Tesla, because in a way, Huawei in 15 years ago in the French telecom space was like Tesla. Why? Because it was an illegitimate player. When telcos started to be pressured by the financial crisis and said, well, we need to find cheaper solutions, Huawei said, well, I can do that. And telcos, I was with Orange at the time, said, well, I mean, you're in China. The Chinese market at the time was a very small one. You know, we have tens of millions of customers. And Huawei said, well, I can serve 60 million customers smoothly across a whole continent, and I've been doing that for years. And Orange said, where did you do that? well, in the only place in the world where you did not consider there was a market, Africa. And actually, Huawei was already running very large markets in Africa at the time. And this is where you all of a sudden became almost an incumbent in the game. But what very few people know, and this is why Ming-Yang, I like to hear you, is that you not only provide telecom equipment, you are going much, much beyond there.
Yeah, actually, we're talking about a lot vertical here. So maybe I can, come from there. But more than 15 years ago, actually, it's something like 36 years ago, in 1987. So when Huawei, as a startup, started to work on really a vertical, a silo, I remember that we started as optical transmission provider, product, solution on that. And step by step, of course, these different area from the telecommunication, actually, after the optical transmission, and then we have wireless, and we have also the intelligent core network, efficiency, storage, and etc. So we can see from a development point of view, Huawei is starting as a startup, and step by step, years and decades after we become a kind of ICT global provider solution and product and solution. Okay, from there. Now I come back. Actually, we talk about a lot the vehicle, the electric, the cars, etc. So more recently, Huawei developed from something like 2018, 2019. We developed 3 new activities. That's why we are here today. These 3 activities. One is the Huawei Cloud. Of course, we talk about a lot of digital technology and all the functionality, all the smart something. We talk about smart always, smart cars, smart cities, smart everything. So, cloud is the base. So this is one, and the other one we announced in 2019 is the intelligent automotive solution. So that's really relative to the mobility, to the cars. And of course, we have also announced in 2018 new activities that we are talking a lot, especially in the last 24 months, the energy and the renewable energy, and we talk about here what we call digital powers. So all those 3 activities, every activities it's a silo, but actually there's links between. For example, we take advantage of our know-how and technology expertise to develop all of those activities for cloud and also for the intelligent automotive and also for the digital powers. So linked together, we have today we talk about in the same time vertical, because actually we have to take care of all those supply chain up to the customer, but also we need to think about how to integrate together, how to get together all those different technologies and to provide the better and the best solution to our users, our customers.
Thank you, Ming-Yang. One of the pillars that that I heard a few times in your talk was about how you leverage digital technologies and software and even go into cloud businesses, which is a perfect transition for Corinne, who is the CEO of Microsoft France. And when I started to twist my question, I dared to say, well, beyond Windows, if I may, above the surface, if I may again, and beyond Azure. I don't know how we say that in English. Azure. Cloud services. How would you describe Microsoft's approach to such vertical integration? I mean, you master hardware, you master software, you master cloud services. How do you combine them together?
Very interesting question. When I thought about this, we tend to think of, horizontal integration, usually ecosystem. So I thought it was interesting to think about vertical. Now, on one hand, the very history of Microsoft, if you look and you describe it, is going from a software company, and then you have the hardware with Surface, as you say, and then you go on social network with LinkedIn, and then you go on open source with GitHub. But beyond that, when you think about vertical integration, is what do you need, to continue to move forward? And one very important thing that I don't think people think of, immediately is the energy independency, when you are moving forward and developing data centers, which is a kind of the backbone of our industry. We have 300 data centers worldwide in 34 countries. The most important thing you need to get access to is really energy. And by the way, renewable energy, because when you make big commitments to be carbon negative in 2030, you better have 100% of your energy supplied by renewables. So interesting, because coming from a software industry, when you start to work on the energy piece of it and look at what is your energy efficiency. So we've been working at, building data centers which are more efficient from an energy standpoint. We've been working at putting, underwater some data centers, like one project we had in, close to Scotland. That improves the cooling and reduce the heating. We've been looking at like what we've done in Finland. How do you reuse the energy to heat a district and a city? So all of this, including building dams. So interesting when you think about Microsoft, you certainly not think that we work so much in terms of the energy. We actually buy a lot of PPA, purchase power agreement. Last year it was close to 6 gigawatts. So there's a lot of time of our team spending on this, and we probably one of, I'm not sure the one, but one of, the biggest consumers of energy renewables worldwide. So that's one interesting thing. The other thing is that, you say, what's going to, slow down my development? Well, it's the access to the GPU and to the chips, and this is where, one of the very important things is that you build very strong partnerships with those companies like NVIDIA. So those are two things. I thought the energy one was interesting because I'm not sure this is the one you're going to think immediately in terms of vertical integration.
Thank you. So maybe the next motto for Microsoft in a few years would be the energy to move forward or something like that. But except that moving forward is something that is branded by Michelin, if I remember well.
Nice transition.
If I remember well. Could you tell, Michelin is seen, for some French people, Michelin was seen as a services company when it came to the Guide Michelin for going to restaurants, but most of your business is revolving and is perceived by your customers as being experts in atoms and in shaping atoms and in delivering things that make cars move. Could you tell us how you are moving up and trying to expand above and beyond and under this physical envelope of the tire?
Yeah, so maybe, as you say, it's natural for us to start on the tire itself because it's still a big part of the business. So here on the vertical integration in a market which is really having to transform in terms of sustainability of the product, circularity of the product, it's important for us to partner both up and down the supply chain. So yes, protecting things like natural rubber supply, which is a critical resource, but maybe more interestingly down the supply chain, because without collecting the end-of-life product and being able to reclaim the materials from the end-of-life product, we will not have enough food stock, raw materials to supply the market in the future. So when you think of 100% recyclable or renewable materials, this is going to be a critical topic. So partnerships with recycling and recapturing those end-of-life materials is going to be a critical topic when we think about the mobility of the future from a tires perspective. And then I think on the beyond tires, let's say around and beyond tires, it's exactly the point you made at the start about capturing and protecting a bit your value. You know, one of the problems when you have a tire which is black round with a hole in the middle is it's very easy to commoditize this type of product. So how can we be more involved in the usage phase of the product, maximizing the value that the fleet or the consumer extracts from that product, and therefore allowing us to capture maximum value from this as well. So tires as a service, like many products as a service offering, is about how do you offer the full mobility package to the fleet, using the expertise you have as a mobility operator, taking away the stress from their side, and being able to capture the value by this more longer vertical integration as well. So that's the kind of two major areas I think is interesting for us. And maybe, Felicity, it's a little bit the same for you. In a way, we're playing the same game, supplying the automotive industry with parts, cars, trucks. So I don't know if you see some similar dynamics in your business or the impact that you have on Plastic Omnium.
No, definitely it's impacting our product offer. Well, first of all, it's the complexity I was talking about earlier. It's something our customer needs to reduce, and we are happy to do that because it's value that we can capture, more responsibilities that we can take. But it's obviously also, we need to think about verticalization at the product level and not among the value chain. So how can we now, on the lighting, so I said component, subsystem, but also with all of our other activities, integrate also electronic software, and making really from design to end of life testing, provide a solution, a different solution to our OEM. Obviously, it means that we need to also grow in terms of expertise. So that not only impacts, I would say, technology on the product side, but also the way you organize, the way you recruit, the way you train. So it's quite a change at the company level. So that's complexity product. And obviously, we also want to use that to play a prescriptive role in our capacity to push new products. That's what we're doing in the field of hydrogen. We were the first one to certify the Type 4 high pressure vessels, and also to come up with a new design for long and thin, substituting to battery pack, and obviously giving the choice to OEM to provide something different. We are also seeing some interesting new routes. We've investigated a lot about digital twins when it comes to how to optimize in the plant, but you also can do that on the product themselves. So now we will be gathering data from our battery system, from our hydrogen systems. So how can we use that with the digital twin to really provides right from design phase, incorporate the data that we capture, and be in a position to provide more diagnosis upfront. So it's really about, yes, how do I structure myself, get organized to get into this new ecosystem, new supply chain, but it's also what kind of product line can I offer to my customer.
So, Chris, are you satisfied with the question you asked to Felicity?
Absolutely.
Okay, great. Okay, we have a challenge, which is time. John Carrier told us about time compression. If we want to leave time for some questions for the audience, I will now ask you to answer questions with a maximum of 2 sentences.
Okay, that's a challenge.
Shall we try? Okay.
We can try.
Okay, well, you can try. So you'll be the first one. The second part of the panel was supposed to be on edge, the physical envelope. But edge is also a buzzword about edge computing. Do you see a contradiction or an opposition between cloud computing and edge computing?
Okay, 2 sentences is going to be tough, but I can summarize. It's both. I mean, you did both because, of course, the cloud computing gets you things at scale, but the edge is super important because you go close to the car, close to the factory if we talk about automotive, and we have cases like this. And this is true for AI. If you think about the artificial intelligence, generative AI, that everybody is talking about, I'm sure you talked this morning, you need the capacity of computing at scale in the cloud, but then you need the edge technology as well to develop and to deploy the AI services at the car at the factory, so you get the best of it, the less latency, the speed, and everything that you need on the edge. So that's both, and we work on both.
And you do both. Okay.
And we do both, and we work on both too.
Great.
That was short.
Yes. So, Félicie, same challenge, 2 sentences. How would you describe an intelligent bumper?
Well, I think we have a bit the same philosophy as what somebody from the MIT this morning said. We want it to be greener, safer, unique, and also more connected. And I mean, there are very different ways to that. First, greener. We can increase the part of recycled material that, and we are working on that. And it's something that also we have to push to OEMs because it's feasible today, but they not always want it. And it's the way you right from the start, you design your products in a way that we are using less CO2 emission and also more easy to dismantle and recycle down the road. Unique is not just about what we put behind the envelope of the car. It's also playing with the part itself. For the bumper, for instance, we are working on some nanotechnologies that could help the bumper to self-repair. So those are the types of things that we are looking at.
Don't you fear this will increase the number of crashes? Because if people know it can get repaired without insurance, just
yeah, to a certain level. I mean, it's not a miracle technology neither. But safer, obviously, it's very important. And I mean, we've seen the startup this morning, Loonwave. We have the same kind of innovation projects going internally that we could integrate within our plastic parts. So a lot of options and ways to really make this envelope of the car much more intelligent and help us in this connected world of today.
Great. I'm being told by the organizers that there will be only one question taken. So please prepare your questions, vote for them, compete for the one who will ask one question. And please, in your question, say to whom it will be asked, because there will be only one answer to the question. Okay? Are you okay with that? Okay. So back to Chris. When we talk, isn't there a contradiction between trying to put intelligence at the edge, so in the physical envelope, maybe even sensors in the tire, and this other emerging trend of trying to have pure materials that enable recycling and reusing, but if you need to separate silicon and oxides from rubber, how do you deal with that?
In fact, I would say it's complementary if we treat it correctly. I think in any product you have 2 parts of it. First, use the highest percentage of recyclable, renewable materials you can in the physical product itself. Then use the intelligence to optimize the use phase of the product. So in the tire case, stick a rubber pocket, stick a tire-mounted sensor inside the rubber pocket, maximize the use phase of the tire, allowing predictive maintenance, i.e. you only look at the tire when it needs to be changed or serviced, not all of the time. Still, you can remove the sensor to retread or recycle the tire and put the sensor back afterwards. So I think it's very complementary. Just you have to think of the way that you are managing a market with multiple tire manufacturers, multiple sensor providers, and multiple software providers. So it's a little bit like VHS versus, CD versus hard disk drive. We need to find the right way to capture the data, and then the value is in how we use the data, not how we capture it. So I think the 2 is very complementary.
Thank you. Quick question for Mingyang on a slightly opening topic, because you're probably the most high-tech advanced player when it comes to wireless, to hardware, and to you're competing with Microsoft, but you have a better experience in hardware, in my view, because you're still making smartphones and so on. But that's nothing personal, Corinne. Nothing personal. My question is for
I understand it's not open for debate, so.
My question is, my question is, are there emerging trends that we are all missing in this room that we haven't seen or talked about that you would like to mention to give them and to give us further thinking?
I'm not, thinking from that angle. But I would like to share just, some ideas in this area, especially in the intelligent automotives. We talk about the vertical. We talk about a lot of innovation. I think the most important thing is that, of course, innovation. That we need to invest. For example, for us, actually, we can provide a global solution for an intelligent and electric driving. So I mean, I'm not using the car because we are not making the car. We are. How do I define Huawei as high tech, as all those things? I think that in one word, Huawei is an enabler of the intelligent automotive solution. So we actually, our solution is including all those parts of the power management and the smart driving, everything, okay? Every part inside of the cloud, of course, we talk about the edge, we talk about the cloud. All those things together, the objective of the innovation is first in automotive is the safety. So we push innovation, always innovation. Since 2019, we launched in this area. Actually, we already up to end of last year, we already invested $3 billion already only in this domain. So compared to the 25 billion that we invested last year, is a small part. Okay, but still. So here I think that we need to keep really open-minded and to reach even higher safety. I will, if I have a chance, I can explain a little bit more what we are working on for the near future.
Yeah. You might have questions from the audience during the break about where exactly, to what limit you put safety. Corinne, I'm absolutely sorry. I was teasing you on purpose because I have the same question for you. In a way, you are the hyperscaler of this panel.
Yeah.
In a way.
Looks like.
Yeah. And so, I mean, Mingyang came up with safety, which was a word that I very seldom heard across the day. Are there other concerns, or is there something else that we are missing and that we should pay attention in this room for the next decade?
Well, I think
the energy, but there is maybe
the most. I mean, the trend which is coming like a wave, and I'm sure you realize, but I don't know to which point everybody realize, is the artificial intelligence, generative AI. It's just mind-blowing. It is at the same scale than what we've seen with internet when internet came. Same kind of wave. It's going to change everything. So it's no longer, I'm coming from the industry, so for me it's easier to talk about this as well. Spent a little bit more than 28 years in the industry. It's not confined now in the IT department, and it's not about technology for technology, it's about usage. So the speed and the wave of the generative AI is super important because it's going to change the way we work, we collaborate, it's going to change everything in a company, the way you sell, the way you market, the way you're going to be resilient in operation. I was looking at the forecasting and the demand and what you were presenting just before. I mean, generative AI is going to have a huge impact, positive impact in the way we're going to do this. So it's, I'm saying that because it's important every company, and being French and being European as well, I think it's important we don't miss this wave because that's going to be critical for the competitiveness of our economy, of our industry as well. So if I have a final word, I would say, well, get everything you can, learn about it, be familiar, get your employees, trained, understand what it is and what it is not, and work on concrete things, because concrete things can help our economy, our industry to be more competitive.
So thank you, because I think this gives Félicie a topic for the next edition of this symposium, which will be generative AI and safety. How do we make Gen AI safe? How do we make Gen AI work for safety? I think
sustainable.
And sustainable.
And sustainable.
I think you have something.
And responsible.
Before we see who won the question in the audience, is there one last question you would have loved me to ask you and I didn't dare to ask?
Well, maybe in the sense of sustainability, I mean, all of the topics that we have discussed, I think, goes into the sense of adding more technology and complexity, finally, at the end of the day. And there's also this target ambition to be more frugal and more sustainable. So we see that basically there are two paths to growth and to technology. And I guess we have not really explored the second one, which is in this context, how can we be frugal, more frugal, because it's not really the path that it's taking.
Well, we could debate on this one, but there are actually paths to use technology to be more frugal as well, you know, to rationalize, to optimize, to solve some of the big problems we have in terms of climate change as well.
So that will be
I
for
mean,
next edition.
I'm sure we have many topics for next.
Can we see the question? Can we see who won the question challenge? How many votes? Okay, 11 votes. Okay, so that's for Philippe. No. I want the one with 11 votes. Sorry.
No, but
we play the game. We play the game. Okay, so that's for you, Félicie. Vertical integration, we go up to service offering, data services, etc. Products are smart and connected. So when are you starting this activity? So and I mean that question is anonymous.
Anonymous. Yeah.
Anonymous. So is the person who
well,
asked
it's going to be that's going to be a quick one.
hand?
We can get another one, I think.
Okay.
I mean, first of all, it's definitely an ambition, but first of all, we have to make sure that we provide the service that we need to our businesses. And I mean, we are in this moment where we are stabilizing the team, delivering the first projects, and that will be very important to really make sure that we have the best expertise and offering. And then the time will come, hopefully, rather sooner than later, that will be in a position to also offer different services to external customers and using different types of also input.
Okay, so and as Félicie is the boss, she asked another question to be coming up.
Yeah.
So where is the other
maybe
question?
to one of our
Okay,
friends.
that's a question for whom? Automotive value chain setting this. Okay, but who will own the customer relationship? OEMs, GAFAM, telcos, energy companies.
Huawei would be.
Yeah, Mingang,
maybe if you want
would you
to
pick?
comment on that.
That is a very easy question, right? So, no. I think we talk about here for me a little bit. When we use the word disrupt, we use all those things. I think today what we are. My understanding for this panel we discuss is, of course, to prepare everything, just like the last question we talk about. It's important for all of us to moving forward. We discussed the last question is about the technology, whether it's a solution to to optimize, to give us, or of course, to work on the different issues in the world. And in the same time, I think today we are talking about moving forward, adding intelligence in the automotive solution. Then I think that the traditional supply chain today, what we saw already, some of them is moving in this direction. So there is no, one side we have traditional, and if the traditional is moving forward as well, then we join together. So there is no question on who will be the responsible for the customer services. Just like the autonomous driving today, I can say actually for our perspective, we pushed in the market a level 2 plus So for level 2 plus, this is something just under the level 3. Okay, the level 3 you don't have to put a driver. But however, we still put only a level 2 plus because we need to have a driver. Why? Because actually the whole environment is not defined yet. So this is a moving situation. The moving situation, I think that everybody, including Huawei or all the companies, I think that we need to catch up. We need to move forward together, and I think that's the best answer from my perspective to get the responsibility.
No, I can I can give you my perspective, right? I think our positioning, at least at Microsoft, is that we don't want to own the final customer relationship. We consider we are a technology provider. We enable our customers with technology that we will not enter into, because you can think behind this question, are you going to enter in the camp of, insurance, of car industry, that's not our positioning. Positioning is to enable through technology. The customer relationship will be even, I would say, augmented by technology if those companies use, technology, because you go more and more personalization. There is a demand for personalization. I'm someone different. And that's what technology can enable. So definitely, to me, the one who's going to own the customer relationship is going to be the ones, who integrate the technology in its services, its product, but not necessarily, not the GAFAM, and not... that's not the positioning.
Okay, so Corinne has the final word.
One thing I think that very important. Of course, I'm not talking. When we talk about the customer relationship, it's an end customer relationship. In this perspective, as I explained, actually all the technology providers to aim the new intelligent cars. That's why I push the safety. So this is very important. And after that, the whole environment needs to make a legal environment, how to define who is, the responsibility. Define clearly the responsibility, and then we can talk about the customer relationship.
Okay, so we will ask Thierry Breton. Thank you so much. Big round of applause. That was great. We are almost on time.
We're perfectly on time.
Pardon?
We are perfectly.
I think also, John, please come in the light to say
yes.
And thanks a lot for this session that was very, very active and good for the afternoon. So now a break, 1 quarter, a bit less than 1 quarter. We are back at 2:45 to 3. Oh, already.
again. So I think we are going further down in the agenda. And after this very interesting and let's say active roundtable, we attack for the last technical session on materials. Materials is key for plastic Omnium. You hear the question before. So Olivier, who is coming?
All right, so we're first going to step in the wonderful world of nanoscale research. And to help you conceptualize what a nanometer looks like, so if you take a human hair is about 50 microns. So you divide the diameter of a human hair by 50,000, and that's the scale our next speaker is working at on a daily basis. I think that's pretty amazing. We're delighted to have with us Professor Carlos Portela this afternoon. Carlos is a professor in MIT Departments of Mechanical Engineering. His research lies at the intersection of materials, science, mechanics, almost, and nano to macro fabrication with the objective of designing and testing novel materials. And when you hear his talk, it's going to flip your assumptions on specific materials' properties. It's pretty amazing. So Carlos, we're delighted to have you with us. Come on in.
Okay, good afternoon, everyone. First of all, thank you very much for still being here. I know it's been a long day, but I promise that we will not disappoint. So it's my time now to have fun, and I have fun by really telling people about the exciting research that we do in our lab. And really, honestly, what I hope you get out of this is really to rethink the way we consider the materials, what materials should look like, should feel like, what they should behave like. So this brings me, there we go. I think a little technical comment. So you'll see throughout my talk a couple of these QR codes. This is something that we worked really hard in my group throughout the pandemic. We couldn't go and give talks and show people our materials. So instead we said, okay, what if we come up with an augmented reality framework so that people could scan these codes and get a sense of what these micro and nanostructures actually look like. So you'll see that if you click down in this little corner, you'll be able to actually drop the material in front of you and even walk around it. I guess you're in your seat, so don't worry about that. But hopefully it gives you a sense of what these materials actually look like. So let me start off really with this concept. Imagine that I tell you that we have a slab of material, but it is 99% air. But still, it holds its own shape, and it's somewhat sturdy. So then the obvious question, okay, so it's 99% air, but where is the 1% of material? Hard question, right? But we definitely know what the answer is not, and it is not that it is all in one corner, right? That's the worst possible design for this. So, but this is the question that we're asking ourselves every day when we do our research. How do we put this 1% of material throughout this slab so that it actually has interesting properties? And this is where we arrive at the question, so okay, what is an architected material then? And this is where I like to start with examples from nature. Human bone, to us, feels like a homogeneous material, but in reality it is not, right? If we look at it under a microscope, we see that it has this interesting microstructure, which is actually what gives it its high toughness and strength. There's other examples in nature, such as the sea sponges. In this case, these are hierarchical architected materials. And what I mean by hierarchical is that at different length scales, you can start zooming in deeper and deeper and still pick out different structural features that each serve a mechanical purpose. But of course, we're in the city where the best example of something that is architected actually resides. And this is, of course, the Eiffel Tower. But I apologize in advance, but I'll tell you that the Eiffel Tower is not an architected material. Instead, it is just an architecture. And what I mean by that is that if we look at one of the struts that makes up the Eiffel Tower's leg, and we say that it has some length L, and we compare it to the actual width of one of the legs of the Eiffel Tower, we see that L and W are kind of comparable. What that means is that even if you're really, really far away, you can still tell that the Eiffel Tower is kind of heterogeneous. So it's made out of air and some metal. So then what is an architected material, a man-made architected material? Well, is one that has some overall length scale W that is significantly larger than the intricate little microscale, which can have some dimension L. And of course, we can broadly categorize these architected materials into three groups. First one is this stochastic architected materials. Best example here is a kitchen sponge, nothing too fancy. Yesterday in the tour of Plastic Omnium, we saw a very interesting type of architected material, which are fiber-based architected materials, such as composites. And what we'll talk about extensively, or in some parts of my talk today, are these ideas of lattice architecture material. These are heavily used in the aerospace industry. Basically, think of them as 2.5D extrusions of a given pattern, but you can also think of these in 3 dimensions. So, okay, now that I hope we agree on a definition for what an architecture material actually is, you might be asking yourselves like the question, okay, why do we even bother with architecture materials? Well, the first question, I think I already answered it. They can be very lightweight, right? If a lot of this percentage of this material is actually made up of air, that means that they're super light. And if we want to keep putting probes in different planets, or if we want lighter cars, lighter airplanes, this is one of the ways that we can achieve this, right? Making sure we organize the material in the right shapes. The second aspect that makes it worthwhile for us to study architecture material is this, what are called size effects, and in particular, nanoscale size effects. What I mean by this is that materials at the nanoscale behave nothing like you would expect them to behave based on what you know from the macro scale. An example of these are ceramics. So this is an architecture material that is a ceramic, but we've shown that you can deform this material by more than 50% of its original height, and it actually recovers when you remove the load. Right, this is really would change the way we think about ceramics altogether. They don't need to shatter. Maybe they can be a little bit more ductile. The third aspect, and I think this is very relevant to a lot of the problems that we've been discussing over the last couple of days, is that architecture is one way that you can dissipate a lot of energy from some impact event, for instance. This is a neat example where some material has 2 stable configurations. One is in a collapsed state, the other one is in an extended state, and it takes energy, of course, to go from one state to the other, meaning that you can stop an egg from actually breaking if you actually have the right microstructure, right? And this is just an example. You can imagine, you can design better, smarter, intelligent car bumpers. You can paint them green if you want as well, so that you can absorb a lot of energy and not necessarily have a permanent deformation in these bumpers. So if we can take a step back and look at every single material that we know of and we use in every single application out there, this is what appears. This is what we call an Ashby plot. It's basically we're drawing a cloud around every type of material that we know of. In this case, I'm showing you the stiffness, or the Young's modulus, against the density of the material. And what I hope you're realizing is that there is some untapped property space in this plot, right? So we are lacking materials that are very lightweight, but at the same time very stiff, potentially very strong. Well, that is exactly where architecture materials actually lie. So what we can do with architecture materials is decide what properties we want and then come up with the right microstructure that really allows us to get into that space. One comment that I'd like to say, so the stiffness, it really is our comfort zone in our field. But in my group, we're trying to push beyond just the stiffness. Let's think about more interesting properties. Let's think about multifunctionality. Let's think about energy absorption. So this plot, of course, we can change the y-axis however you want. I guarantee you there's going to be a white space that only architecture materials can actually achieve. So, okay, architecture materials might be interesting. So how do we fabricate them? And I'll describe how we fabricate them at 2 scales, the 2 length scales. So at the micro to nanoscale, we basically use a very advanced form of 3D printing. And we can make materials that are actually solid struts or also hollow with some interesting coating. So I said this is just 3D printing, but it's not just any type of 3D printing. It's actually the highest resolution 3D printing that exists out there. It's a process called 2-photon lithography. It's actually quite simple. It consists of a substrate where you put a gel or your photoresist, and then you focus a laser inside of this drop. And you trace this laser in 3 dimensions, and wherever this voxel, this laser traces in 3 dimensions, that's where you're locally solidifying the material. Once you're done tracing whatever 3D geometry you want, then you wash off whatever you didn't want, and you end up with your micro or nanostructure, depending on how you designed it. Now, to make these materials hollow, how do we do this? Well, we start with these polymeric nano or micro lattice, and then we go through some conformal coating process. In our case, we use an advanced process called atomic layer deposition. We're literally depositing a layer of atoms at a time. We typically do this for ceramics, and it gives us really nice conformal coatings that are extremely thin. We end up then with a composite, a core shell composite. But I've said, okay, I want to make these lightweight. I want them to be hollow, so I need to remove the polymer somehow. So we do this by cutting some sacrificial beams out of these lattices, and then we put them inside of an oxygen plasma chamber, and we remove all of this polymer out. So what we end up with is something that is, again, 99% air or more, that is just hollow on the inside and has these very nice intricate shells on the outside. At the macro scale, you know, this is now the more classical type of 3D printing, and I'll say that in our lab, you know, these are some of the nice materials we've been able to print, but these really are just toy 3D printers that we're using to do research, right? But there are many industrial types of 3D printers that really could get you closer to fabricating parts that you can start implementing into products. These almost all 3D printers might work with some process that allows you to pattern 2D layer by layer, and then once you move a print head up, you start removing the part and getting these nice 3D shapes with the right resolution that you want. Now that we make these architected materials, the next question is, okay, how do we then characterize their mechanical properties? At the macro scale, nothing too crazy. Everybody must be familiar with something like this. We have some cube of material that we're interested in characterizing. It has some overall length L. It has some cross-sectional area at the top that we can call A. And then we push it with some force, right? And this is basically, we want to destroy it. We want to understand its properties. This allows us to define our stress in the material. And once we deform it, we can come up with an expression of our strain. These are just normalized metrics to make sure that we can compare materials across different length scales. So what we usually get out of these mechanical tests are these stress strain curves. And you know, it looks kind of complex, but really all we're going to extract, there's a couple of things that we extract. We extract the stiffness just by taking this slope, and we also want to predict when these materials start to permanently deform and start to get damaged. And this is what we define as our yield strength. And we can come up with many more metrics, such as the energy dissipation in these materials, but these are just the basics. So okay, this was at the macro scale. But as Olivier said, we also work at small scales, and we also want to characterize these materials at small scales. So how do we do this? Well, we work a lot with microscopes, necessarily, because otherwise we won't be able to see the materials that we're making. So we basically have a testing machine that fits inside of a scanning electron microscope that allows you to probe these materials while at the same time you're looking at them. So let me zoom in a little bit more. Here you're seeing our nano indenter. This is the tip, a flat punch tip, that's actually going to come in and start compressing our material, but you can't see it yet. We have to really zoom in for you to see the kinds of samples that we actually test to extract all these properties. To give you a sense of scale, again, back to the analogy of the hair, this is what a human hair would actually look like next to one of these samples. So I hope at this point you're asking yourselves the question, okay, Carlos, this is nice, this is great, but why? Why do you do this at the microscale? And that's a fair question, and I'd love to answer it. Well, the first part is we really want to enable a lot of these properties that have not been possible yet. And sometimes we just can only achieve this by having nanoscale features. So that's the first part. The second part is that sometimes the applications do require you to have these small scales. An example of this, so this is a Lunenburg lens. We saw a mention of a Lunenburg lens earlier. If you have a microscale architecture, that means that you're interacting with the kilohertz regime pretty well. It means this is basically sound. But if you want to start working with ultrasound, and this enables just many more applications, such as medical ultrasound, which is something that we're actively looking for and learning more about and trying to apply our materials to, that means that you need to work at the megahertz regime, and you can only do this if you have microscale architectures. Now the last aspect, and I think this is probably the most important one that I hope you take away from my talk today, is that if we're not working at the nanoscale, that means that the properties that we're getting at the microscale are still relevant to the materials that you're actually wanting to apply, even if it's at the meter scale. What I mean by that, as you saw, we use normalized metrics. So every force, I'm going to normalize it by an area. Every displacement, I'm going to normalize it by an overall height of the material. So that means that the properties that I'm going to get with these experiments are the same as if I had done the experiment on a larger cube. The difference is that in an hour, I can print you 100 samples, 100 different prototypes. And in another hour, I can already get the data and I can already analyze it. So this will enable high throughput characterization in experiments that is not really possible if you try to do large scale testing at the macro scale. So as you can imagine, over the last 10 years, this field is somewhat new and really has exploded over the last 10 years. As a community, we've been able to really play and look at all sorts of different geometries of microstructures and start to write papers about how these different microstructures might give you different properties. And some of them can look quite funky. I'll talk about this one and this one a little bit. But anyways, the design space is huge. And as you can imagine, these different architectures have done what I've told you that they should do. First thing is that they're all lightweight. You saw that their large portion of them is air. They also are really good at absorbing energy. And in some cases, depending on how we fabricated them, they're actually quite good in terms of enabling nanoscale size effects. But again, one of the issues still has been that all of these samples have remained at the microscale. So we can learn a lot of mechanics and really extrapolate a lot of this knowledge, but if we want to apply it and scale up the fabrication, we're still not quite there yet. So what I'm trying to say is that if I were to put all the work that has been going on in the field of architecting materials in these two axes, so this is the length scale associated with the materials, here is the deformation rate, or how fast I'm actually pushing and testing on these materials. This is all quasi-static, just as if I were pushing on it with my finger. This is where most of the works actually exist. But we're trying to push the boundaries in my group at MIT. And two things that we're trying to do is, first, try to understand how they will behave once you deform them in realistic conditions, right? These materials will get dropped. They will sense impact. And we need to understand how these materials actually behave in these conditions. To scale them up and scale their fabrication, really the dream is that I want to have nanoscale features and all these interesting properties, but I want to do so in a material that I can actually hold in my hand and give it to you so you can apply it somewhere. The way we're doing this, and this is where I now start saying that forget about additive manufacturing. This is where we're actually looking at self-assembly of materials to really attain interesting morphologies that in a matter of an hour you could print something, or you could obtain something that otherwise would have taken weeks to print with the right resolution. Now, going into this time regime or deformation rate, one of the things that we're looking at is how waves, vibrations propagate through these materials, and we're doing this at the microscale because we're interested in certain frequency regimes. We're also looking at extreme conditions. Now, at the centimeter scale, we're looking at how carbon lattices, about this size, are good at being able to mitigate energy from blast. And also, we're looking at how these types of nanomaterials might be very efficient at dissipating energy from microparticle impact. So let me split up into the three main points that I'd like to discuss today. But this whole graphic can be summarized in one sentence. In my lab, we really want to enable this game-changing potential of architecture materials. Right? I'm not happy with just saying that we do great research in a lab. We want it to go out of the lab and start getting applied into realistic conditions. To do this, we need to make sure that we can tackle three problems. First is that we can scale up the fabrication of these materials. Second is that we can understand how they behave under extreme or realistic conditions. And the last aspect is that we want these materials also to be resilient, meaning that I can deform them to large extents and they don't necessarily have to break and shatter. So let me start off with the first point. In terms of scalability, I already said maybe 3D printing really is not the way to go. So we're starting with polymeric emulsions, self-assembly. Think of this as oil and water. If you mix them, they'll want to start separating again. The difference if you do this with polymers is that at some point you can polymerize them and then you freeze this certain condition, this certain morphology, and you are able to obtain these foams with this interesting microstructure. And as I said, this only takes about an hour or so, and now you have cubic centimeters of these material that have the right resolution. So we can look at a pie slice out of this puck. We can see that these nice pores all around. These pores are on the order of about 10 microns. But I'm still not happy with that, and we want to make these materials lightweight and very resilient, and we do this by then depositing these nanoscale coatings of a ceramic. And then we remove the polymer, because the polymer to us is just the nice thing that gave us the morphology. And then we remove the polymer, and we end up with a material that now is back to 99.9% air. And this is the nice microstructure that we get. So you can think of this as a very nice network of eggshells, but they're all interconnected and nicely curved, and this is actually going to give us very nice, interesting mechanical properties. So because we're in a mechanical engineering lab, we do a lot of mechanical experiments, and this is honestly one of the coolest videos that we've been able to get while working on our research. So what I'm showing you here, again, is a 99.9% air material, but it's a ceramic, okay? But the ceramic is extremely thin, just 11 nanometers thickness. So that's about just 4 DNA helices wide. But you can see it holds its own shape, and it looks nice and robust. So then we come in with our nano indenter, and we start deforming this material while taking a video. What we start seeing is that this ceramic actually doesn't shatter or break. It actually just buckles, wrinkles, and then it recovers. And we can keep doing this over and over again. And to our surprise, we started seeing that there are no cracks that start propagating through the ceramic, or at least it's not visible to us. And we did this for many, many more cycles, and we saw that this behavior actually held. Now, this is what architected materials at the nanoscale allow you to do. Beyond that, we started to look at what if we could actually change a little bit the way these pores form and the way this self-assembly process actually took place. Well, we computationally designed a variety of these different morphologies that you could envision getting them through self-assembly processes. The only thing I want you to pay attention to here is that we artificially made them change the preferential directions of these walls. So yeah, qualitatively they look different. What we decided to do was to do simulations to really predict what properties is this little weird morphology going to give us. The main representation that I'm going to show you here is this colorful surface. Is basically a representation of how stiff this material feels depending on how you probe it. So this means that this material is extremely stiff if I probe it in this direction, but very compliant if I probe it in these other directions. And it's actually way better for the same amount of mass compared to a lattice that normally we would have printed. So a self-assembled material in principle could be better than a lattice that actually takes a lot of time to create. We can look at all these different morphologies that I'm proposing here, and the main takeaway here is that we really could play with whatever properties you want to get, depending on what the final morphology you get. So you see all these different elastic surfaces, they all look different. That means that they'll be stiffer depending on how or different stiffness depending on how I probe them. The key takeaway again here is that in the samples that are isotropic, so these are the ones that are closest to the puck that I showed you at the beginning, where we actually did not enforce any directionality in these morphology, the key takeaway here is that they are stiffer in all directions than a lattice that we thought was the stiffest thing that we could make for many, many years. So you don't have to design this material. Nature will do it for you. You don't need a printer. Nature will do that for you, and it can be stiffer in all directions. So that's quite a remarkable achievement that we arrived at. Second aspect that I wanted to mention is extreme conditions. And I'll start with something that really isn't that extreme, which is just wave propagation. And again, in the megahertz regime. This is why we're doing it at small scales. A couple of very interesting examples recently are that mechanical waves such as ultrasound can be used for biomedical imaging. This is an example of imaging a tumor. Recently, last year, a colleague at MIT showed how you could have a sticker of ultrasound that is able to monitor your organs, image them for 48 hours nonstop, which is game-changing applications. Now, why do we want to get into this regime of playing with ultrasound? Well, this is an example of how ultrasound can be used to also move cells within a medium. So you have water flowing with some bacteria, you create a standing wave in this channel, and you see that the bacteria actually will segregate based on the ultrasound. But in a sense, this is a very simple way of just using ultrasound waves. What if you can actually focus it by using the right materials that allow you to focus sound, maybe prevent some frequencies from traveling through it? So that's exactly what we've been doing. In this sense, we basically made a three-dimensional battery, but it's actually a material that morphs its shape. So the way we did this was fabricating, printing this structure, then making it conductive, and then depositing silicon on top of it. Once we charged this material, we saw that it actually changed shapes because a lot of these struts actually swelled up because you're now doing alloying process on these struts. The material has nowhere to expand, so then all you can do is just buckle and create an interesting pattern. This is a sped up video of this process actually taking place. You see that this pattern that we designed starts emerging, and you get different domains with different morphologies throughout this material. But so what? Okay, sure, you change shapes. What does that mean? Well, we're talking about ultrasound. Well, we can do this computationally. All I want you to take away from this plot, this is what we call a dispersion relation. Each of these lines basically means that this is one mode in which this structure can actually vibrate. So what I wanted to look at is, if I look at a horizontal line in any of these plots, if I cross one of these modes, that means that I can definitely propagate that frequency throughout. What we started seeing is that once we changed the morphology of the structure, we now started seeing regions that had no modes propagating through that region. What that meant is that these frequencies just will not get propagated through this material, will not be supported. We created a band gap. This means that if you excite this material at the right frequency, you're not going to get anything on the other side. And this is all solely due to the microstructure that he actually designed into this material. And you can see that you can pick whatever geometry, you can back calculate what is the right morphology that gives you a band gap in the frequency that you're interested in. We're talking about megahertz here, but this concept really holds across frequencies. If you're talking about kilohertz, you could also do that at that scale. In my group currently, so what I showed you was computation. We're now trying to do these validation experiments. You know, we're talking about microscopic samples, so we really have to come up and develop the methods to do these measurements. We're looking at ultrasound transducers as one way of exciting these materials, something we're very, very excited about. It'll be out in about 2 weeks. We've been able to develop a method of probing materials without ever touching them. We basically use lasers to excite them and then measure their vibrational signatures, and from that I can tell you everything about its mechanical properties, which before, again, I had to touch them and I had to push on them. So it's very exciting. So now let's go more extreme conditions. And for extreme conditions, I need to also think about better materials, potentially things like carbon beyond polymers. So we've been able to make nano-architected carbon, but also centimeter scale carbon. I mentioned these at the beginning. This is a red blood cell for scale compared to one of our nano-architected carbon materials. So you can see that these unit cells are extremely small. Today I'll focus on the nanoscale carbon because we saw that it has very interesting properties and we were able to do very interesting impact experiments. So up to now, before we did this study, we were very limited in terms of understanding how lattices or architected materials behaved upon impact. So we saw that some people try to do some experiments, but again, separation of scales isn't there. So this is not an architected material. It's just two plates that are kind of separated by some struts. Recently, we've also been able to see some other researchers have done these high energy or high velocity compaction. They get beautiful images, but these experiments are done at a synchrotron, very complex to do, and we're still lacking mechanical understanding. The problem that we're very interested in, and with the length scales that we're working at, is that of micrometeorite impact. So if you're familiar with this, it's basically this problem that we see a lot in space where we have tiny specks. We can think of it as a paint chip that travel at velocities of up to 10 kilometers per second, but can hit a window of a spacecraft and create significant damage. Currently, the best solution there is that of Whipple shields, which are multiple layers of material that are supposed to try to spread the kinetic energy. So we asked ourselves, okay, how can we work at these length scales, try to make a material that is actually energy dissipating and potentially be a good solution for coatings, for protective coatings, for very advanced applications such as aerospace. So we were able to fabricate some of these architectures, again, with our polymer printer, but I said carbon, right? Carbon is ultimately what we're interested in. Well, we get carbon by basically pyrolyzing this polymer. So we do this in vacuum at 900 degrees Celsius. We also get some shrinkage involved with this polymer. So this is what they look like before we pyrolyze them and after we pyrolyze them. So of course you have to play a little bit so you don't get full warping when you do these kinds of pyrolysis experiments. What the key thing that we were able to achieve is a shrinkage from 10 micron unit cells. So again, compared to the size of a red blood cell, we ended up with 2 micron unit cells, which meant that we're now at strut dimensions that are in the order of hundreds of nanometers. So then came the fun part. Okay, how are we going to shoot these materials at high velocities in the lab? Well, this is, again, we need to go to a custom technique. So this is the laser-induced particle impact test, which basically consists of a way of shooting microparticles. Again, let's compare it to the size of a red blood cell. And we can shoot them at velocities of up to 1 kilometer per second and also use a high-speed camera to look at this impact process in real time. So here you see the sample. You're about to see the projectile coming in from the top. This will be at a velocity close to the speed of sound. What you see is that these particles come, form a crater, actually get rejected from the material. And we can do a lot of post-mortem characterization. We see that the craters are actually indeed formed. We can measure the volume of these craters. And we know that there is a particle rejection regime that stops at a certain velocity. Because what we started seeing is that once we did it at higher velocities, so this is now about twice the speed of sound, we saw that these particles start going down into the material. There's some craters, some ejecta, some material gets broken, but we actually were able to find the particles actually embedded inside of the material. So this is what we call the capture-dominated regime. But this begs for a comparison to real materials, and this is exactly the point that we wanted to be able to provide. We do these experiments at small scales, but how does that translate to what you could do with these materials if you had tested something that is much bigger? Well, to do this, we'd look at how much energy we dissipated in this impact, and this is by measuring the velocities of these particles, and we normalize it by the amount of mass that we destroyed, right? So this is the mass that I'm going to account for, is basically the volume of the crater that I created. And I can compare this to impact experiments on classical materials, such as stainless steel, aluminum, or PMMA polymers. What we see here, and I promise you, this is the only equation that I'll show today, is that all of these experiments on these, I'll call classical materials, actually lie on this line. So this should look a lot like 1/2 mv squared. That's kinetic energy, right? But I'm normalizing by the mass, so we end up with just 1/2 v squared. What this means is that all the energy from these particles actually goes into accelerating the material that's right under the particle. So there's no interesting mechanisms of dissipation. We start seeing interesting mechanisms when we look at things like Kevlar composites or Spectra composites, which is a lot of what we use for bulletproof vests. Now we start seeing that there is some separation from this line. And all we need to understand here is that there is some mechanism that is giving us this additional energy dissipation. This is what we also see with all other interesting nanoscale materials, such as multi-layer graphene, also nanoscale polystyrene films. So the question is, where are these lattices? Well, these lattices actually were able to perform on par with what these nanoscale materials actually do, with two benefits. One is that the density is significantly lower than everything else that we're showing on this plot. And the second aspect is that, in principle, we could scale up these lattices. If you make them thicker and thicker, you can continue absorbing energy. So this doesn't hold if you actually try to stack more and more graphene, because at some point you just get carbon again, and that is brittle. So now to the last point, and I'm almost at the end of my time, is this idea of resilience. And here, we're going to change completely the way we've been thinking for the last 20 minutes or so. We want to think about materials that are also very compliant. Let's forget about stiffest, strongest, most energy absorbing. How can we make something that is actually very compliant, deformable, and doesn't break? Well, we were inspired by textiles, or a hammock. And where the building block is really just a curled three-dimensional fiber, what if we take this as a building block and then tessellate it in the right 3D dimensions or orientations so that we get a building block that it is fully woven? What's interesting here is that we can make these effective beams or struts now helical out of 3 different fibers, and also that these nodes are nice entanglements of fibers. What do these materials actually do? Again, this would be a side-by-side comparison of these woven materials compared to these monolithic materials, and we're going to start pulling on them. First thing we start seeing is that these woven materials actually behave like ropes, right? So this is the same material, same amount of mass. This is a brittle polymer that definitely broke. This one didn't break. It behaves like a rope. It actually starts rearranging into the direction of loading. And also we prevent catastrophic failure. But then we can start compressing the material as well. And what you start seeing is that in this case, for the monolithic materials, we get into a lot of permanent deformation. Whereas in these woven architected materials, you're able to deform them significantly, and there is no permanent deformation in these materials. So you could reuse them and extend them and compress them all over again. So this is a form of summary. As you saw, so my group is really interested in, again, taking materials beyond the laboratory into real applications. And we really are looking at mainly 4 focus areas with our 3 main skills, which are the modeling, the fabrication, and the experimentation, meaning that we need to come up with the right testing techniques. We want to fabricate our own materials, and we want to design them and predict them before we actually go ahead and make them. So the 4 main areas are, again, self-architecture, because that's the way that we can scale up nanomaterials. In terms of multifunctionality, I showed the ultrasound applications, but with my colleague Ariel first, we're actually working on water filtration using these materials as well. So we really are not limited to just mechanical applications. We want to understand how architecture gives you a lot of energy dissipation, and ultimately, how can architected materials also be extremely compliant? And again, you saw that the road ahead is not easy. We know that these materials can do a lot for us, but we need to look beyond just stiffness. We also need to look beyond the length scales that we're working in. Again, the dream will be, let's take nanoscale features to the centimeter scale or beyond. If we can translate these ceramics that are a ceramic mug that won't shatter, but actually can deform. And ultimately, we know that these materials, if we want to apply them, they're actually going to go see harsh conditions out there. Let's understand how they behave in these harsh conditions. With that, I want to thank my group, my students that are the ones doing the hard work, and of course, Plastic Omnium for inviting us, ILP, And thank you very much.
So I think it's, so what we, a small joke, I think nano is big. No?
Oh, sorry?
Nano is the next big thing.
Nano is the next big thing, correct.
I prefer to say it because normally you don't catch joke from me. So, first question, where are you regarding carbon nanotubes, MIT specialty, e.g. for cathodes?
So carbon nanotubes are indeed a great material. Unfortunately, what has been hard is to really use carbon nanotubes in the right applications from a mechanical perspective. Nanotubes are great for multifunctionality, and we see a lot of my colleagues are really using them for conductive applications. A colleague, Brian Wardle at MIT, is using them for composites. So you put nanotubes at the end or in the edges of carbon fibers so that the adhesion with the matrix is significantly better. We really don't need them yet, or we don't have good ways of really putting nanotubes in the right orientations. But definitely, they're there for what you mentioned, right? Cathodes, energy applications, just not 3D architects materials quite yet.
Okay, thanks. So what scale miniaturization can we reach in a realistic 3-4 years agenda for industrialization? And what is the order of magnitude of the overpricing? If it's, or down pricing.
So, okay, I will tell you. Again, if we're looking at scaling up and making this cheap, I think self-assembly is still the way to go. And just to give you a sense of scale, so to make these pucks that I showed you, and this is a very crude estimate, it's going to be somewhere around $2 to make something like this, which would be, orders of magnitude cheaper than if we had to print this material. So in the next 3 to 5 years, I think it's not crazy to say that we can talk about maybe tens of centimeter areas of maybe thin films that are protective, that have these really nice ceramic properties. There's also, the other thing I will say, is at these small scales, even if we're talking about 100 micron cube, there's a lot of tissue engineering applications that some of my colleagues have started to look into. You have a compliant 3D substrate where you can seed cells that feel the right tissue stiffness, and you can then take these biocompliant scaffolds and use them as implants. So it really just depends on what application you want. I think some of these materials already can be applicable.
We have no more feedback on the time and on the screen, just for the information. So I see the visual feedback that we have to stop.
I know there's still a lot more questions, Carlos,
yeah, sure.
but we were able to capture all the questions, including for the previous speakers, and we'll make sure that you have access to them and you're able to answer them. So thank you very much.
Thank you.
So now it's time for the last speaker of the day, and for sure it's at the best spot on the agenda. So we are delighted to welcome on stage Ariel first.
And maybe a quick story before you come on stage, Ariel. A couple weeks back, we had a conference at MIT on sustainability, and Ariel gave a very inspiring talk. And I was sitting next to an industry member, a big water company, and the person leans over to me and says, with her research, she solves 90% of my problems. So with that introduction, we're super excited to have Professor Ariel First. She's a professor of chemical engineering at MIT, and she's going to tell you a lot more about her work on the biological molecules and cells and harnessing the inherent capabilities of those. All right, thank you, Ariel.
Thank you. Thank you, and I know I am keeping you from alcohol. So I promise 0 equations in my talk. So before I go into the science, I wanted to show pictures of the people who did all this work. I can take credit for 0 of this. These are the people who are in the lab every day, who are doing the work and sending me all of the awesome data I'm going to tell you about. So now you get to go back to school. What do we see in this picture? What do we notice? Where's the light? Exactly. It's in developed countries. The global south is pretty much dark. So basically 1 in 10 people globally to date don't have access to electricity. What this means is about 2.5 billion people rely on dirty fuels to cook their food and heat their homes. And so all of the projects I'm going to talk about today, they're generally in the realm of human health, sustainability, and clean energy. But we're motivated by energy equity, which is the idea that historically disadvantaged and marginalized communities have been significantly more impacted by industrialization than the rest of the world. And that in order to achieve true equity globally, we have to intentionally design technologies for everyone, right? Tesla is not an equitable technology. Even everyone in this room can't afford it. So we need to make technologies that are easy to use, don't rely on power grids, and are accessible. So, how my lab approaches these challenges is by taking inspiration from nature. We're going to have another quiz. Does anyone know what this is? Velcro, great. So, Velcro was actually inspired by the interaction between seed coatings and animal fur. We can see on the top that for hundreds of years, humans have taken inspiration from animals. This is pangolin, and this is a suit of armor from 1500 AD based on its coating. How about this one? Excellent, you're the first one to get that. This is shark skin, and this is 3D printed fabric that was used in the last Olympics for swimsuits to improve the speed of swimmers because of these architected structures. So, my group likes to use what biology has already given us to develop technologies for human health, sustainability, and environmental remediation, and I'll focus on the second two today. And specifically, what I was interested in talking to you about is how we've thought about the plastic challenge. So we produce 380 million tons of plastic each year. It's about 6 kilograms of CO2 produced per kilogram of plastic. And just incineration of plastic that we don't want anymore, that's waste, will result in 2.8 gigatons of CO2 equivalents emitted annually by 2050. Additionally, the plastic problem is not distributed equitably. We can see here locations on the globe where plastic waste has the most significant impact. If we recall, those are pretty much the inverse locations to the places that have access to electricity, right? Those are also the opposite to places where we generate a lot of waste. What we've shown here is how much waste is generated. The darker colors are where more waste is generated per capita. And we can see that's generally in developed nations. So developed nations are making plastic waste and shipping it to the global south. Additionally, when we think about plastic remediation, the majority of strategies right now generate microplastics that end up in the ocean and end up in our ecosystems and even in our food and harm human health. So what I'm going to tell you about today are two platform technologies that my lab has developed. One is our ability to put proteins that can do activity onto cells as a very inexpensive way to make bioscaffolded materials. And the second is how we can actually protect whole microbes to enable them to do activity. And so together, what these two technologies can do is circularize our plastic economy. These enzymes can degrade plastics, and these microbes can repolymerize them. And along the way, I'll show you some other applications, because my goal is to kind of get you thinking about what these technologies would be useful for in your industries. So we're going to start with depolymerization. These are the students, postdocs, and even undergraduates who worked on this project. And so again, what we're doing here is we're taking enzymes, and we are basically chewing up plastic. Before we get into the plastic degradation, I wanted to show a couple other applications that we can do with this. So generally, this is a platform technology where we can pick a protein, stick it on the surface of E. coli, which is basically just the main microbe we use to engineer, and then we can freeze-dry the microbes and kill them. But our proteins remain active. So I can make 100 grams of this material for about $10 in my lab today. And what we can do with that is we can take things like environmental contaminants and degrade them into inert products. And so what we've been able to do to date is PFAS degradation, those are forever chemicals, NDMA, which is a water purification byproduct, We can also do things like rare earth element recovery and lithium recovery using proteins that can specifically grab those out of complex mixtures. And importantly, we can degrade things like PAHs, plastics, and organophosphate pesticides. And so the first story I'm going to tell you is about organophosphate pesticides. These are about 50% of the pesticides used globally, and they look a lot like these chemical warfare agents. That's because they behave on insects pretty much just like these chemical warfare agents behave on us. And we can see here in the back that the people spraying these should have all this PPE, but 90% of the people who are responsible for distributing these pesticides don't have access to that level of PPE. So what we were able to do is to combine enzymes that can degrade these pesticides with microbes that can detect them into a platform that allows us to both detect and degrade these materials. So how did people detect these before? Well, in nature, enzymes had evolved to take these pesticides and cleave this bond to make this inert product, which is called p-nitrophenol, or PNP, and it's bright yellow. That's great, right? We can detect this by absorbance, UV vis. What we can see here, though, is that our limit of detection is 5 micromolar. That's enough to kill a horse. So that's not an especially good detection method for us. So we decided to turn to biology, and we engineered microbes to fluoresce in the presence of that degradation product. We can just see that visually here. With that degradation product, they're bright green. Without, they're less green. But that less green is what's called leaky expression, which means our sensor turns on even when we don't want it to. So we turned to pond scum. We turned to microbes that were isolated from Lake Onedensis in New York, which is shown here. They're called Shewanella onedensis, and they have this really unique way of breathing. If there's no oxygen around, they can actually spit out electrons onto things like metal oxides. So they can deliver electrons extracellularly. And they can do this using these wires, shown here, as well as these proteins that span their membrane. Those of you who remember biology from high school, membranes are normally insulating, right? So electrons shouldn't be able to go through them. These proteins allow electrons to flow freely. But what we can do is we can actually engineer these microbes so that we turn off their ability to spit out those electrons until we want them to be able to do that. And we can put that under control of that p-nitrophenol. So what we see on the right is charge, which is basically the electricity we're generating as a function of the concentration of that p-nitrophenol. And what we see here is not only do we get detection, but we get quantitative detection, which was even a surprise to us, down to 500 nanomolar. So we're 2 orders of magnitude, 100 times lower than UV vis, using a system that costs us 50 cents. So what we've been able to do is to take these microbes and to use them as a chemiresistor integrated into a standard commercial RFID badge. So now, when there's no p-nitrophenol around, when there's no pesticide around, we get no signal, but we get a detectable signal which we can read by a cell phone with a free app in the presence of these degradation products. So not only have we increased the sensitivity of detection of these pesticides by 2 orders of magnitude, but we've decreased the cost from a UV vis down to an RFID tag. So now let's turn to plastics. We're going to talk about fast fashion. So about 60% of clothes today are made out of polyesters. 81.5 pounds of clothes, at least in the US, are thrown out each year per person. And as I mentioned, 60% of those are polyester. And the majority of those break down to microplastics that end up in the ocean. In fact, 10% of ocean microplastics are polyester. So, if we remember our bioscaffolded enzymes, we can now take an enzyme that can degrade polyester, and we can visibly degrade polyester in a very short amount of time. So this is a 1 centimeter by 1 centimeter piece of polyester plastic. And this is after 24 hours at room temperature. We can see the degradation. That's great, right? But two questions: how fast can we do it, and what does it make? Because if we're making microplastic like most other methods, it's not really helping, right? Well, what we found is we actually degrade this down to the monomer to tetramers, which are all materials that we can repolymerize. So what we're doing is we are breaking down plastic into chemicals that we can use to make virgin plastic again. We are not making microplastics, and we are not making long-chain oligomers. This also happens really fast, and we can control the rate of depolymerization based on the temperature. So shown here is just two different sizes of polymers. So things as long as 45K are generally pretty hard to degrade. We can get 100% degradation in a couple weeks. This is at 50 degrees Celsius. Since then, we've bumped it up to 80 degrees, and we can get 100% in 3 days for both 45, 14, and as well as 80,000 mass units. This is also very general. So far, we can take polymers derived from all of these different monomers, and we have efficient degradation with all of them. So, again, just to remind you what we've done with this technology so far, we've been able to degrade plastics, which I showed you, and we're not taking these to microplastics. We're taking these back to starting materials that are useful and profitable for companies. We've been able to degrade PFAS, NDMA, and organophosphates, as well as PAHs, and we can also recover elements from complex matrices like mining effluent and battery waste that normally would be inhospitable to microbes. And so the key takeaway here is because those microbes aren't alive, we don't have to worry about that. So now we're going to move on to the second technology, which is how we can protect microbes to enable them to do things like this repolymerization. So my group has developed these nanoscale suits of armor. They're self-assembling materials that form two-dimensional networks on microbes. They're composed of things like green tea extract and tannins like what you find in wine, as well as natural minerals. And all of the components are generally recognized as safe. And the reason we care about microbes is because microbes are the only reason that any of us are alive. They're essential for pretty much all life on Earth. They help protect us as well as plants against pathogens. They help with carbon and nitrogen cycling, as well as degradation of organic matter, and they can actually produce natural products. The problem with most microbes is that they're very delicate, and so if we take them out of their native environments, we can't manufacture them. Well, what we've been able to do so far using these coatings, and again, this is a platform technology, is to enable the development of accessible vaccines. We've been able to develop a version of the tuberculosis vaccine that we can store and transport at room temperature, negating the need for cold chain storage. We have seen 150% higher seed germination using protected microbes for agriculture. We've been able to perform self-healing in cement using microbes, and what I'll talk about at the end is how we can improve synthesis of both catalysts for CO2 reduction and polymerization. So, I said these coatings are easy to form, right? How easy is easy? That easy. You mix the components together in the presence of microbes, and they form, and you can see that in this blue color. When we image these microbes by TEM, we can see that these coatings form homogeneously. So we're not getting patches or incomplete production. And we can see that these coatings protect against a variety of stressors. I'm not going to show you data for all of them because it's the end of the day, but to give you some idea, green microbes in each of these pictures are the ones that are alive after whatever we did to them. We can see here that we can freeze dry them, put them in high humidity, high temperatures, UV light, high or low pH, solvents that are non-aqueous, high salinity, and even oxygen exposure for anaerobes. And we get up to 10 million times more live microbes out of our system. So what are some of the applications of this? Well, one of the applications is regenerative agriculture. So chemical fertilizers are terrible. One of the ways we can actually reduce their use is by delivering microbes to the soil that can do things like nitrogen fixation. The problem is these microbes are very sensitive and can't be manufactured. So if we take our microbes and coat them and freeze dry them, we get 150% higher germination than even using the fresh microbes for all of these different crops. And we can see that here. This is when treated with our coated microbes, and this is with the fresh microbes. So, how does this apply to materials? We're going to switch to a different type of pollutant, CO2. I'm sure I don't have to tell anyone in this room that CO2 is a problem, and the majority of it is generated from human activity. How can we think about using microbes to help remediate this challenge? Well, I'm going to tell you two different ways we can do this. One is by using native microbes. These are called diatoms. We can see these are little calcium carbonate structures that form around them. And the way this happens is they can take CO2 from the atmosphere and calcium, and they can fix that CO2 to make these calcium carbonate structures. So what we've been able to do in my lab is incorporate these directly into cement because we have these protective coatings. And we can see these are the bare microbes by SEM. This is after 1 day of exposure to calcium. And we can fill these macroscopic holes. So this is a 1/2 centimeter hole, a 5 millimeter hole, that we can fill in a week with those microbes. But what if we don't want to just fix CO2, right? What if we actually want to use it as a 1-carbon feedstock? So CO2 is abundant, and I know this is an oversimplification, but if we shove enough electrons into it, we can make it into valuable chemicals, right? One way we can think about doing this is with electrochemistry. So if we take things like clean energy and combine it with CO2 and water, we can electrochemically convert that into things like methane and ethylene, which are value-added products, and can be used as starting materials for things like jet fuels for tough-to-decarbonize industries. The challenge with this is that the amount of energy it takes to turn CO2 into things like carbon monoxide, which is the first step in this process, is about the same amount of energy it takes to split the water that it's in and generate hydrogen. And that means that a lot of our energy that we want to go towards CO2 reduction is being wasted. So we're going to take inspiration from biology now. We're going to come back to microbes, but now we're going to take a detour into DNA and think about how we can use DNA as more than just the genetic code. So everyone here remembers structure of DNA? 2 complementary strands that come together through hydrogen bonding. It looks a lot like Velcro to us, right? The electrostatics that hold Velcro together are very similar to the reversible hydrogen bonding interactions that DNA has. So if we modify one strand of DNA with something, and the complement with something else, we can force those 2 things to interact. And one way we can apply this is by taking catalysts for CO2 reduction and forcing them to stick to electrodes. We get 100% efficiency for hybridization with this. And what we see is significantly improved stability, decreased energy input, and significantly higher rates of catalysis. So let's talk through this data. So this significant increase in our current is basically a catalyst demetalliting. So this means you're losing your catalyst and your electrode because you're basically plating it onto your surface. Very unstable, not great, right? Well, even just by adding single-stranded DNA to that catalyst in solution, we increase the stability. And when we stick it to that surface with DNA, we increase the stability from seconds to days. Additionally, we decrease the amount of energy needed and increase the Faradaic efficiency of these catalysts. That was a lot of words for the end of the day. What I mean is, so Faradaic efficiency is basically a measurement of for how many electrons we put into a system, how many molecules of product do we get out. So with conventional catalysts, with a lot of energy, minus 1.5 volts, we get 20% Faradaic efficiency for carbon monoxide, the first step towards ethylene, and 20% for hydrogen. That means we're totally wasting 60% of the energy we're putting in, and only 20% is going towards any product we actually care about. With our DNA scaffold catalysts, we can improve our Faradaic efficiency to 100% total for chemical products, with 80% for CO and 20% for hydrogen. What that means now is we've quadrupled the efficiency of this reaction for our target using 30% less energy. And finally, we can also speed up this reaction. So this is a log scale of the turnover frequency, which is just basically how many reactions happen in a certain amount of time. For the free catalyst, it's pretty low. For the single-stranded DNA catalyst, also pretty low. We see 100 times faster reaction rates when we scaffold it with DNA. And this is fantastic, right? But we don't really care about carbon monoxide production. So, can we do better? Well, the gold standard, actually the copper standard, for carbon dioxide reduction is controlled copper faceting. So, based on the crystal that's exposed in a copper catalyst, you can control what product you're getting. And that's fantastic, but it's been a challenge to actually control faceting in a way that you can access all of these different crystal faces. So this work started by 2 undergrads in my lab who looked at the reaction to make these nanoparticles. And generally what people do is they throw glucose in with a copper salt in a solvent with some capping agent, and it makes some unpredictable particles. Well, they thought, if we change the sugar and we change the salt, it's basically cooking. And what we found is by just changing the sugar we use, we can significantly change the 3-dimensional structure of the particles we get. And each of these has different crystal faces. And that's fantastic, right? But we still require solvent and chemicals. And so we actually had a high schooler in my lab this summer who looked at Shewanella, those microbes I talked about at the beginning, and said, well, they spit out electrons. It's basically the same thing the sugar's doing. What happens if we throw microbes in instead of reductant, instead of the sugar reductant? And this is a mix of the copper nanoparticles that he synthesized with the microbes in water. So now we can control we can control the facets of these particles using microbes in a green reaction. And using that, we have some preliminary data that shows that based on how we actually set this reaction up, we can control the ratios of carbon monoxide produced to methane to ethylene. So, back to plastic. How can we use these to make plastic? Well, is anyone here familiar with ATRP, radical polymerization? Anyone? No, okay. So, oh, thank you, John. It's a little bit of chemistry we'll talk about here. Basically, it's a polymerization that's based on generating a radical. These reactions are very unstable. They generally have to be done in solvent, and they generally have to be done anaerobically. What we found is that we can use these microbes called bacillus, and we can set this reaction up in open air because these bacillus can first make that reaction anaerobic in aqueous systems and then do very rapid and controlled polymerization. So what we see here is if we measure the oxygen content, we can see that first the bacillus basically decrease the oxygen and then they start polymerizing. And we get 100% polymerization in 12 hours, which is on par with the best catalyst for these reactions. Not only that, but we can control the rate of polymerization based on changing the species. So all that's shown here is just how fast we're polymerizing and a bunch of different strains of microbes we looked at. And what's important about this is for radical polymerizations, the monodispersity, or how uniform the polymer is inversely proportional to the rate of polymerization. So if you don't care about how uniform your polymer is, you can use one of these microbes that'll do it in an hour. But if you want a very uniform product, you can take one of these microbes, and I think our longest takes about 18 hours, but we get monodispersed polymers that are on par with the best catalytic reactions. And again, this is done aerobically in water. And so I hope what I showed you today is not just that we can use microbes and bioengineered systems to both degrade polymers down to useful chemical monomers, and then repolymerize to useful polymers using challenging reactions that had previously been difficult to make green, but also that these technologies are both very generalizable and that we're interested in solving problems that people have. And so with that, I'll thank my group again and thank Plasticomics for the opportunity to present, and I'm happy to take questions.
Very impressive, Ariel. I will change my opinion on microbes now. So for sure, we will have a lot of questions. Yes, so the first one. So we have in Europe a PFAS ban that will dramatically impact batteries and fuel cell or even tire pollution. Do you show the light to avoid this to happen, or?
I mean, if the ban is just for release into the environment, then yes, because basically we can degrade the PFAS after it's used. So far we've done PFOA, PFOS, and GenX, which are the three main components of PFAS in the US at least, and we can defluorinate them. So we can remove the fluorines that are problematic.
So you put light into our tunnel. Huh?
Hopefully.
Next one, please. So what are the trade-offs of using microbes versus chemical or mechanical recycling?
That is a great question, and generally what people think of as the trade-offs are having to keep the microbes alive. Our advantage is because we don't have to keep the microbes alive, we can do these under harsh conditions, so high or low pH, very high temperatures, high salinity, all those things that you normally wouldn't be able to do. And the advantage is you don't have to use things like solvent, which you do for chemical recycling. Mechanical recycling is also very energy intensive and results in microplastics. So we avoid both of those problems.
So are you not becoming intimate with your microbes? So why don't the microbes get destroyed by the polymerization?
That is a great question. So the polymerization, the microbes are actually used to generate an active catalyst for that. So we generate an active copper molecule using the microbes. And so the microbes can kind of sequester themselves from the actual polymerization process. And they maintain, they're 100% viable after the polymerization.
Right. I look to the visual feedback, okay. So what are the energy costs for separating microbes from monomer and mixture?
So that's the best part about this. You can pellet the microbes out. So there's actually two different ways depending on what you're going to use the monomers for. You can either use a chemical extraction or you can remove the microbes physically. They're pretty large compared to the monomers. They're on the order of microns, so 1,000 times larger than the materials Carlos talked about. So they're pretty big and pretty easy to separate out.
Okay, so no issue in fact beyond. Yeah. And what are the scaling limitations of this approach in terms of production? And
so that's honestly the best part. I like to tell my students that the reason we developed this is because I'm lazy and I hate protein purification. And so we have to skip all those steps. Basically, once we have the plasmid, for those of you who are familiar with protein expression, all we have to do is put the molecule in that tells the microbe to make the protein. And then we have our materials. That's it. So in the lab, we basically remove the liquid and then dry them. And we can get 100 grams of dried material for about $10.
You are already big guys being interested by your research and taking it in the industry? Or?
I mean, we're hoping to. We don't have any specific collaborations yet, but like I said, we're interested in solving problems. So if there's a material you need to degrade, we're happy to discuss that. The great thing is microbes have evolved proteins to degrade pretty much everything.
So I hope in the room that there is people interested, for sure. So should I buy microbes today to make business tomorrow? Yes, sure.
Personally, I think so, but you don't have to buy them. So the coolest microbes have been isolated from places like pond scum and soil in your backyard. So just go grab a bucket of soil.
Perhaps a bit of work to make it, let's say, useful, as you have done.
Just a little.
Okay, so how far is your group from the first application in, let's say, big scale?
So we have gotten mining tailings from collaborators to test in the lab. We're still looking for partners to actually deliver these outside of the lab, but we can make enough material to do pilot scale testing now.
Okay, great. I think that's all. I don't know if there is a question in the room. Oh. So thanks again.
Thank you.
For a very interesting speech.
Thank you very much.
Olivier, please come on stage with me right now. I don't know for you, but I think this day went very fast, and we have now completed the final technical session. And I would like to call on stage to join you Yannick Reynaud, Scientific Director of Plastic Omnium. For the ones that don't know him, in fact, without him and the interaction with Olivier, and their strong interaction, I would say this event wouldn't have taken place. So a big round of applause to them.
Thank you. Thank you to everyone. To make the key takeaways, okay, I will take from here. Thank you, Alexandre. What a travel we did together past 6 months, I think, since we start discussing this topic, and try to make together this agenda. And I hope it was nice for you. I think it was quite dense in terms of what I would call tough tech. And I would like to ask Olivier, what is the MIT definition of tough tech, and did we make a good tough tech symposium today?
Well, thank you, Yannick. And I just want to say before I answer the question that it's really a pleasure to work with you, because you guys don't see this, but we've had so many interactions over the past few months to prepare for this, and it's been an absolute pleasure for you and your team as well. And Yannick also organized for us yesterday a super nice visit of AlphaTech, which for all of us in the faculty I know was enlightening in terms of the capability of Plastic Omnium, how you are thinking about the future. And at AlphaTech, you could see the future in action with a lot of the labs being revamped and the rooms being prepared. So thank you, Yannick. Okay, back to tough tech. So tough tech is a subset of what we call deep tech. And what we mean by tough tech, we really mean about hardware-driven research that's difficult to addressing problems that are difficult to solve, that will take probably years to generate results, but potentially the outcome is very significant. And I think what you saw today with the startups is a very good example of tough tech. And I think one of them had the comment of waiting for patient capital, because it's going to take time to mature. But you can understand the impact potentially is very significant, including from what we just heard today from Ariel, for example, or Carlos, on the impact of their technology as well. A first key takeaway maybe that I get out of all the discussions we had today is how multifaceted the problem of innovation for the next generation of mobility is. It's a problem that really takes a lot of different disciplines to solve. And it's, I think, also, Yannick, a problem that takes a lot of different functions to solve. So I was happy today during the talk. I met people from the HR department. I met people from QHAC. This is exactly how to approach it. I think that's a very good, it's not only about the technology, it's about the cross-domain and cross-functional approach to this problem.
Yes, safe, clean, inclusive. I think what you developed this morning in the mobility initiative are very, very close. I see David in front of me to the purpose and the values Plastic Omnium is establishing in his management and throughout all the organization and the 40,000 employees. And back to the mobility initiative, I was very pleased to see how global MIT as a partner is for us. You're studying what's happening in Beijing with the robotaxi of Pony.ai, and that's what we are looking for, a global partner. But also, we had this feeling that we need to look at the people and social equality on top of this. We mentioned, I mean, John mentioned the strike which is hitting in the US, and also will we be able to drive into Paris, or shall I have $100 to get in Paris? So it's not affordable, it's not equitable, and that's nice that also we take as management, as business, this type of equitable and inclusive reflection.
Yeah, it's a great point, and that's exactly what I was mentioning when I said multifaceted. It's the next generation of mobility is as much a technical question as it is a societal question, really, and you have to look at the problem in its entirety. I also want to emphasize something that John started with this morning when he talked about the pendulum effects of those trends. I think it's important to understand how the trends might impact you, but you have to realize that some trends might go the other way as well. So understanding that pendulum, I think, was also a key takeaway I got out of this morning's talks.
And the big word of today, the buzzword I should say, was about AI, generative AI. But what was nice, what we heard from Patty and from Marcello, is that we are not going to replace human. Back to us, back to human. It's how to augment ourselves. Okay, how to upskill? I think Felicie also touched it a little bit during the roundtable. How to use this tool? So I hope I could have the memorando tools and click on my no, I don't have it. So I still need to.
You don't need it. You don't need
to think about it. And what is going to change AI? How to get a trusted AI and how I think she clearly show. Our basis we can put in the learning, and basis that we have in our mind when we are using this. So really, it has the possibility to change for the better or for the worse.
Yeah, it's a very good point. I guess we could have generated this wrap-up using ChatGPT, but we didn't. You and I spent a lot of time on this during one of the breaks. A key takeaway from Patty's talk, and that's very strong for me as well, is the shift from artificial intelligence to augmentation of intelligence. It's a very strong point, and I think the example that Patty shared and that also Marcelo shared with us were very striking to me. A clear message was also that designing AI systems to work with people is as critical as anything else we do with AI today.
Yeah, clearly we started with Industry 4.0 to use machine learning and a bit of artificial intelligence in order to control the quality of some parts. But I was very delighted to hear GelSite and also Ubicept, because there are still a lot of research in this area, how to control, I don't know where is Stefan, but the quality, I see Abla there, the quality of the painting with unmanned, also for the high pressure vessels. Can we have internal control of the vessel at the end of the process? These are still key topics that we can tackle with your startups, maybe. Yeah, there is another point I would like to tackle also about the artificial intelligence. We have been creating since 1 year a software factory which is called OpenSoft, and the first application of artificial intelligence would be to generate code. But for our customers, for internal customer or external customers, we are also thinking other application together with our partners Capgemini in order to create documentation, to create certification, in order to use better this code and to reuse them. And then the big second part of the morning was about hydrogen. So I'm going to touch on it with Ari Tuller, which gave a comprehensive lecture of the market in the US and how much energy are used, how much CO2 is produced just to create energy. So 27% goes in transportation, while 38% goes in creating electricity. And on the 27%, 57% of it goes on heavy trucks. So I think that we at Plastic Omnium, with a new energy division, we have the right technology here to decarbonize this type of long haul. And I think we had a great presentation about SOFC and SOE in order to produce this hydrogen and how to avoid this drift during the usage of solid oxide electrolysis.
We also continued the day with, or started the afternoon with a very interesting talk from John Carrier on vertical integration with a very systems dynamics approach. And system dynamics, when you study at MIT, is super ingrained in the way things are taught. You tend to see control loops absolutely everywhere. And I think you saw a few examples of that with the great talk we had from John. I think it was also interesting to see how in his talk and on vertical integration, how that can lead to very practical, tangible results in your production as well. And that's another thing, you know, working with you, Yannick, and you, Alexandre, also at Plastic Omnium, that I find super interesting is both the long-term thinking you have, but also the short-term reality with production and things that need to be delivered. And I think managing that complex balance is tough, but you do it extremely well.
Yeah, this is the motto of Mr. Favre every time, how to have the short-term and the long-term strategy. So, yeah. Well, this panel discussion was also great to say that, yeah, vertical integration was or is the new normal post-pandemic, but the discussion rapidly shifts to sustainability. All these big groups, big corporates, Huawei, Microsoft, Plastic Omnium, Michelin, of course, can be more sustainable. So that was unexpected in the preparation of the talk. It was more about industry, product, how to become more integrated. But then it was really, we care for people. We as entrepreneurs need to put first the sustainability. And then we touch a bit the balance, again, between cloud, edge, and how to bring more function in the outer skin, I would say, of our vehicles.
So we finished today with two extremely inspiring talks as well. From the first one from Carlos, who gave us a very interesting perspective on architected materials and all the potential. And you saw the videos, how ceramics can deform and get back to their shape without breaking. And all these things, hopefully we need to do everything we can to help industrialize these types of topics. And I hope next year, Carlos, you can come back with a huge block of architected material with you so we can pass it around. And then we, of course, finished with a great talk from Ariel as well, and we're excited about this.
Yeah, this was really the technical masterpiece of the afternoon. Thank you to both of you. And I think the last speak about Ariel with the circular economy of polymer, about biomimetics. How can we think out of the box? We say most of the time, but here you go. So let's look at nature, what nature does good, and this good we do it again good for people.
So we promised to be finished at 5:15. Look at your watch. We almost delivered. We have one more minute, but we want to hand it over to you, Alexandre.
Thank you for the takeaway.
So my job is always easy. And after these key takeaways, I would like first to thank Laurent and Félicie to spend the whole day with us. I think it's how it's complex in the type of agenda you are having every day. So let's have your thought about your day, the day that you spend with us, and getting your feedback.
So, as you rightfully said, Yannick, I think it was really intense and a lot of very interesting topics. I really like the format of moving from concept to really concrete application, going from big picture lecture to more deep dives on some topics. I'm sure you're much more knowledgeable now on hydrogen, on materials, on AI, so very interesting. I think for us, you were talking about navigating the short and long term. For us, a day like that is always really good to step back, to take the time, because obviously innovation for us is really important to anticipate better, understand better how the world is changing, because we are changing. We are focusing every day on changing our business, our industry, but things are moving also on the side. So we still have to catch up and be connected to that. And I think it's the whole point about the innovation, open innovation. We are really happy, at least I am really happy about this first format. I hope we will have new ones, and it's very interesting to be able to connect all of this ecosystem.
And if you are happy, I'm happy by definition. But no, I want to thank you, Alexandre, to organize that. It was really a pleasure for me. I hope it was a pleasure for all of you as well. I didn't know what to expect today, but it was higher than my expectation. A lot of energy, a lot of inspiration. Also a good point to, for a certain period of time, to disconnect with the short term, which is important because the short term today is not really nice. What's happening outside in the world is not always very inspiring. And I think it's really important for us, for all of us, for Félicie, for myself, but for the complete PO team and for everybody, to look at different things which are positive, inspiring, and engaging as well. It's also the way we want to engage our people, basically, because at the end we want to engage the 40,000 PO employees. Many, many thanks to the speakers, starting with the MIT. The good point is there are a lot of Johns in MIT. Therefore, I can say thank you, Johns. Therefore, I can capture at least 50%. Olivier, thank you very much as well. Many thanks to the other speakers. The startups were great this morning. I think a lot of good ideas and also a lot of energy, also very inspiring for us. And also many thanks to the speakers from Microsoft, Michelin, and Huawei as well, because I think you had good discussion on that, Félicie. For the PO people is please get inspired and continue the journey. What we are doing with Félicie, with Alexandre and Yannick is just to encourage you to open your eyes and to connect with different industries, with MIT or different kind of universities as well, because again, everything around is changing very fast. There are a lot of opportunities, but we have to be much more open-minded for innovation and for new ideas. Therefore, for us, it's a kind of kickoff, and we want to motivate you, to encourage you to continue in this journey.
And I'm sure, I mean, there are many questions that left unanswered. We will make sure that we work something that we can share with everybody because that's a bit part of the frustration. You could not raise your question or get into some specifics, so we will cover that. And we will have another innovation event in November to present our second year of the Innovation Challenge. It will happen here. We will have 8 persons group projects that got together they are gonna pitch on the future of energy for mobility, and 3 of them will be reward and hopefully helping us also to come up with new opportunities to develop in the future. But before that, we invite you to have a glass of champagne.
Last word, because thanks a lot for, sorry. I wanted to jump in also to thank the people that nobody see, but they were totally instrumental to the success. So I would like to name Ilham from the communication team that was spending day and night to make it feasible. Sophie, also. Sophie that was taking care of the organization. Parvin, and Marilyn also, that perhaps nobody has seen today. And I can refer also to Frédéric that was helping for the setup of the marvelous product from Omnium today. The people from Omnium in AlphaTech that were receiving also the professor at MIT, and the whole team of communications that is supporting us on this event. So thanks to all of them. Thank you.